imię, może dać tam wszystko. Ale teraz nie ma. Lokal, tak, 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 tak. Morning. How are you? Yes. So, all presentations, I will just switch. I was working 2 days right. My contract was 2 days right. Oh, I was. What's up? Oh.
No, it was good. It was good. Yeah. Got my membership and everything, so I'm good there. And then I spent some time downtown.
Okay.
So, yeah. Went back around.
Tokyo or somewhere else?
Shimashi.
Shibashi, okay.
Yeah, I like that.
Are you flying out?
Tuesday. I guess, where you leaving?
Oh, Monday, Monday. The main chart of the
Okay.
I got some
Just in case you need Kaplan. So
after the conference or after the micro?
after the micro conference. He's got my right next door.
Oh, okay.
And so I'm gonna go over there.
Oh, we can do later, but it would be nice if we do it today.
Yeah,
Okay.
definitely. As soon as I finish my little thing, I'll message you and find out.
Drop me a line.
Yeah.
That would be great.
Okay, I'm gonna set that. Okay.
Kojarzy mi się z tytułu.
The open document.
Open document as a full presentation.
If it will show the notes, another presentation mode.
I don't think so. We were able to open it.
Okay. No. Yeah, usually use the presentation mode.
Oh, okay.
No, it's okay. I've got them. Yeah, I don't really need them.
generate yet message more, but I suppose that they will be visible.
Yeah, no, it's fine. I don't.
Okay.
It's nice to have.
No. Yes. No.
Yeah, we've spoken a bit, but I don't think officially. Yeah. We've been at conferences, I've just never spoken. Working with Josh. Yeah, this evening, with security, like, he did some security interact. Oh, yeah, he does this.
Raz, dwa, trzy. Słychać było? Can you hear me? Podejdź go do głosu. Just a second, because we have some audio problems.
So that was 19, but
I think we're talking
Testing 1, 2, 3. Hear that? Testing 1, 2, 3. Test. No.
We'll start shortly when we solve problems with audio, because as we know, the remote audience is not able to hear us right now.
Test, test, test. Got it.
Can you hear me, Maciej? It's okay. Okay. I think that we can start. Welcome everyone at the System Boot and Security Micro Conference. First of all, big thank you for all sponsors, because this event would not happen with them. So this is very important that we have great sponsors. Please follow the code of conduct. Of course, we like tough technical discussion, but please be polite. This is very important. Maciej, who is here, will be driving with me this micro conference. We have a lot of good talks. Some of them are scheduled back to back. So presenters, please keep on the schedule. We have one catch box this year, and this catch box is followed by camera. It will be in the middle of our room, because the camera will be looking at the crowd. And if you want to ask questions, please take catch box and speak to them directly, because otherwise the remote audience will not hear you. So this is important. And of course, please keep it close to your mouth. This is important. I want to make you aware that we have only 15 minutes break, because we have a lot of presentations and we didn't want to miss any. So that is why we decided to shorten our break. Are there any questions before we start? Okay, we don't have any. Welcome again. James, stage is yours.
The slides here. Okay. Okay, good morning, welcome, konnichiwa. I'm James Morris. I have a background as a kernel developer and maintainer. I've been working a lot in security, various parts of the security subsystem in the kernel. I've been a manager for a lot of the time in recent years. I've temporarily escaped from that to come and give this talk. So in this talk, we're just going to give a very brief high-level overview of the Ultraviolet project. This is a work in progress. It's an early work in progress. And the purpose of this is to seek early feedback from the community and to encourage collaboration. And we want to try and make sure that what we're doing here is in line and that we are working in a consensus. The general topic is, how do we approach code integrity more generally in the operating system? We also, to note, I won't have a demo for this today. The project has been slightly delayed for reasons, but that's okay. I think in this time, we would only really have time just to do this discussion anyway. So what is Ultraviolet? It's two things. It's firstly an architectural model for the OS that allows you to implement full coverage code integrity, and I'll get onto what that means very soon. And we also have a reference implementation. And we want to be able to demonstrate this end-to-end and work in the community. It's rawhide based and it uses Particle OS. And again, I'll cover that in more detail later. But it really is a kind of an architectural model that is not specific to any particular technology. I will note that it is kind of extremely systemd shaped, but it's not necessarily requiring that fundamentally. Also, the scope of this, I want to limit the scope of this project to we just can't solve every type of general purpose computing problem with a strong security model. I think, we need to do some scope limitations. So for the purposes of this talk and the initial model, I want to limit this to a scenario of a minimal container host, which is used to host hyperscale infrastructure. This seems to be a fairly common use case. And one of the reasons for this is that I know at Microsoft, we've been doing this, and there's a lot of groups out there working on the same thing and essentially starting with the same building blocks and then having to invent their own approach when you finally come to do more integration. So the idea here is to try and bring some more commonality and architecture into the ecosystem to support this. And this just extends at a very high level, it extends existing image-based Linux efforts, particularly work coming out of the UAPI group and related to that. And as I mentioned, it's technology agnostic, and it supports what I will call launch time code integrity in a generalized way. So this is the code integrity of a piece of code that you've installed on the system. So a binary, a script, firmware that you're injecting, and we're also limiting the scope of this to the OS, so it depends on having a secure boot and a hardware root of trust and attestation, but the UV model is really limited to the OS. And by launch time, this is specifically when you go to run and execute and you're effectively in the kernel and the kernel's deciding to execute the code on your behalf. It will also need to cover, obviously, kernel modules and BPF and other types of execution. The threat environment, so this is not really a full threat model, but just to sort of iterate here that generally in hyperscale, whether that's a public cloud or a large social media company or other organizations, often there's like very high value assets and a large scale of assets. So there's like a lot of businesses have important information there. People are looking to protect all kinds of intellectual property. And the threat level generally ranges up to the highest kinds of levels, very sophisticated, well-funded attackers. So another issue is that deployments are at really global scale. We're talking millions of nodes, potentially even another order of magnitude if you're looking at devices out in the field, phones, IoT, that kind of thing. So the overall complexity is very high. And so trying to approach this, we're looking at trying to reduce complexity and be able to reason about what's out there. And this is where code integrity becomes important. We also want this to be really policy driven, and fundamentally, this is how you scale and reason about complex systems. If you have declarative policy for a system, and then you can group those together and you kind of know what's supposed to be out there, and then you can measure and attest and verify that it matches what you're expecting. And it also then makes it more amenable to detecting violations and problems. So part of this is about being able to define your integrity goals and security goals for the whole system by some sort of analyzable policy, rather than just say having this embedded in your file system configuration. Okay, so I will provide a working definition of code integrity launch time here. And again, if people have input or different ideas, please feel free to raise that. For the purposes of this talk, I'm talking about at launch, the code, we know where it came from. So it was signed by somebody holding a certificate that we know about, we know who they are, that the code at that point is also unmodified, and it's also correctly authorized to run in that context. So there's some subtleties here. You can have signatures that you trust and provided by somebody, but it could be an old version which is known to be buggy. So you have to watch out for things like rollback attacks, and also authorized in that context. So it could be signed for production use. And you don't want, say, development signed code, if you have that, to be able to be enabled in production. So it's about correct authorization. So the goals of this, to enforce this, is we want to essentially extend the trusted boot process. And it's common now, we're seeing common now people bringing up, say, a pinned root file system, which is verified, a user partition, which is using deemed verity. But we want to sort of extend that more generally to essentially everything that's on the system that can be or needs to be verified. So for code integrity, we're talking about compiled binaries, scripts, kernel modules, loadable firmware, BPF. We need to enforce integrity of the configuration of that code if it can alter the behavior of the code. And there are other kinds of subtle attacks like living off the land, people getting code and combine it in ways you weren't expecting, or being able to modify configurations so that it effectively changes the behavior of the code and makes a web server do something that you weren't expecting it to do and act in a different way. There are also some other attacks where you can put strange things in config files and then have that become an exploit where there's some sort of execution of that code. So we need to be careful about this if we're looking at code integrity. And for dynamically generated code and JIT code, often this just simply is not possible to sign it before it gets on the system. There are trampolines, there are all kinds of other things. So it's in this, the basic goal would be to have control over this as to what on the system is actually able to, for example, JIT and load dynamic code, or you can block it. So as I hinted at before, the general requirements are, we're assuming that there is a trusted boot process, a hardware root of trust. We need to also protect the integrity of the underlying system. So in our model, we will be using SE Linux and other mechanisms. We need protection against runtime attacks for all of this to be meaningful. And we also use an assumed breach model. So we assume that the system gets breached and then what happens after that. So we want to be able to constrain an attacker using least privilege and other mechanisms. We want to really importantly prevent persistence. So if somebody does get in, if you can reboot and clear it and know that it comes up back in a good state, that's helpful. And then also to be able to ensure detection. So being able to be as sure of the logging as possible. So getting the logs securely off the system as quickly as possible when they're generated. That kind of approach. So these are general requirements that are needed. There's probably more, but this is sort of a very high level overview. And again, it's not a full threat model, it's trying to introduce. So in the UV model, we kind of assume that we have a container system where you have like the base OS, which I guess everyone in this room would be familiar with, using a minimal image-based system which has AB updates. And that would essentially not be modifiable usually by the end user. This is something that you would deploy and have control over. Then there is like a container runtime of some sort, whether that's normal containers or systemd or whatever you have. And then you would have everything else in this model is then containerized. So including things like control plane and your applications. And I've sort of put these into different categories because this can also help simplify the overall security design if you have different categories. But again, that's, so some of these will need to be more privileged than others. So we basically have, most of this is out there, or essentially what I've talked about so far, it theoretically is out there. So what I think we have missing in the broader community is state separation. And I think what happens is that a lot of us keep reinventing this from scratch when we go to build a system and think about a system. So I'd like to sort of get some discussion happening about extending the existing efforts around standardization, say in the UAPI group efforts, and container runtimes, and think about really fully separating how applications handle read-only data, configuration data, and then writable, mutable data, and how then they interact with other containers. And the goal here is we want to basically protect the base system and then strongly enforce that because it's not really going to change very much, and then allow more flexibility within the containers and have because that's really where security becomes difficult, is trying to cater to all these different use cases. And also having strong isolation between the containers and then controlling how they share. So you have declarative policy about if they have to share a file or if they have IPC, and you can set this up, and then the policy will already exist on the system, and it will just be configured for that particular case. So after spending some decades on projects around SE Linux and doing this at scale, really the lesson I've sort of come away with here is that we need to look at increasing security abstraction and hiding the complexity through abstractions, so through kind of natural system boundaries like container boundaries. DM-Verity images are also very useful because this becomes a signed file system that is verified as you load it, and you can encapsulate all kinds of things within that, and you can bind mount, and you have a very powerful kind of primitive with that, and also FS-Verity. So the proposal is to try and get some sort of consensus or discussion happening on a model for state separation. And that's essentially within we assume that the code is running inside a container and that we have some sort of container model for that. So this would be, there's been discussion recently, like Dan DeMeyer talked about potentially a new container model. It is well defined in terms of its functions. So is it a control plane container that is, needs privileged access, or is it simply an app that needs to have a web server do something? We want to have strong isolation between the containers and that we have the separation of the read and write. And in particular, that really full separation of read and write, it's a bit like trying to bring in privilege separation. That has worked fairly effectively in terms of privilege management. And this is similar. We want to be able to then have a standardized way where we can use something like DM-Verity more broadly across the system, and then use policy, top-down policy to then define that. So we have essentially had a version of this running in production for about 5 years, and it's scaled up to multiple millions of nodes. But again, it's a custom system. We're also, and that was discussed by Luca Bacassi. I have some resources back here. It's called Azure Boost. And what we're trying to do is sort of bring some of the learnings and the technologies from that out into the community and socialize them more. There's a more recent version of this, OS Guard, which was discussed at scale. And also I've been looking at Lennart's new security model for systemd, which we would want to leverage in this kind of thing as well. So I've got links to these projects, and we have down the bottom, what does it look like? So in our particular case for this reference version, it's basically Rawhide running Particle OS. And at the starting point is basically bringing in all the latest pieces and then using IPE, which is an upstream kernel module, which we used developed for Boost. And we want to bring in some of the newer technologies that are currently in development, like script integrity. So yeah, that was kind of a lot to try and fit in. I think we started a few minutes late. Do we have discussion or questions? Oh no, okay. Is this well, we have to shut down. James, keep going. Yep.
You mentioned BPF.
Mhm.
How does this work integrate with the efforts to do BPF signing?
So that's actually a really good question. So I attended those talks, and I know the people working on this from our team. So what we really need here is like control over this, and then that's the first thing, is to make sure that there is some sort of model, and we can let's say in our case, we wanted to make sure that we only had static BPF, which I'm not saying we would. We'd want to be able to enforce that. But we need to look at this model and how it would integrate. But that's a really good question, and I don't have a concrete answer on that. But we want to do, work with the community and integrate with that work.
I wanted to ask about the state separation stuff you talked about with containers. So okay. I guess I'd like to hear more about how you see that sort of thing working in practice, because at least from like the application containers side, you could theoretically see something like that working. Though I think that, there have been several attempts over the many years that we've had them where people have tried to come up with designs where you'd be able to have this separation, and I think none of them have really caught on, is my impression. And then for system containers, you could imagine, I don't know if Leonard and Christian have an opinion on this, but you can imagine a situation where you would have, basically you would mirror the way that you set up the system to have a similar kind of separation inside the system container. That seems more doable. But for application containers, because people build whatever they like and they put it on Docker Hub or whatever.
And that's partly why I'm trying to limit the scope to infrastructure hosts. Trying to solve this for the general third-party case is very difficult. That's what the OS Guard thing is, and they're looking at, with that, essentially taking OCI images and rearranging them, re-signing them, and do all kinds of crazy stuff. We kind of potentially have the luxury here to define something newer. And I think one of the goals of this system would be that it doesn't preclude somebody bringing in a legacy container. You just have a lower security boundary. But that is the core problem, in fact, that we're trying to solve. And so we have done this in a custom system, but it's not something we can generalize because we have the people writing the workloads conform to a particular set of behaviors, which is not generalizable and not something, we would do a,
Question.
And I'll be around later, we can.
Continuing on this question, a naive question, why portable services in the systemd semantical context wouldn't fit as a solution for the state separation standardization?
It would, yeah.
Okay,
and so I don't want to be, I perhaps should have made it clearer that it can be a Docker container or it could be a systemd portable service. It's really the architecture. It's not the specific implementation. Okay. In fact, it is very largely systemd shaped at the moment.
Got it.
Thanks.
Thank you.
Okay, so let's move on. Today I would like to talk about future of platform security measurement in Linux. I'm Maciej Pijanowski. I'm engineering manager at FreeMDeb. We care about this topic because we are developing open source firmware, firmware Dacharo, which is based on mostly Corbu TDK2, mostly for Intel AMD x86 boards. So that's why this topic is of interest for us. So what we will talk about today, we will first talk why should we even care about this topic. We'll have an overview of across the ecosystem. We mostly focus today on the Linux approach proposed by FWPDHSI community. And what are the possible problems and possible solutions with this approach. Why it even matters. Firmware is the foundation of security of the platform. So if we have a problem on the firmware level, on the hardware configuration level, even the greatest OS security may be malfunctioned this way. So that is why we need some form of assessment of making sure that our firmware, our platform is configured correctly. This is really getting really complex. There are dozens of security features out there, and they must be configured correctly, because due some misconfiguration, we may lose the security properties of the system. There is user awareness gap. User can easily get lost in those multitude of features. They don't know what kind of features are supported on their platforms, or whether if they even are there hardware-wise, are they configured correctly? It's very complex to get to know that. And there is also enterprise compliance requirement. There might be some IT policies that mandate some specific security configurations. And we can see that having a OS enforced firmware quality assessment would be beneficial for all of those users. So let's have a brief overview of how it looks like in the ecosystem. So for instance, in Windows, we have this device security page where you have various features that Windows utilizes, and they believe they are important for the security model. So there is like a security processor, which is essentially a TPM. So you can see if it's configured correctly, if it's there, what's the secure boot state. There is also this secured core PC, which is the highest score you can get on a Windows platform, which utilizes also the DRTM technology underneath. Then another example, we have kubectl, which is a virtualization-based OS based on Zen and Linux. And they also have some similar window. It's called kubectl Security Report, where they list a number of features they depend on, which with a simple binary metric, either they are working correctly or not. So a user can see what's the security posture of your device. Then in regular Linux distributions, we have following approaches. We have in a non-desktop environment, we have this device security window as well. So we can see the secure boot state. In this case, we can see it's active, and we can see also this protection state, we can call it. In this case, it's protected. It says it's protected. It's like a nice green color. If it would be worse, it would be like red or orange. So protected corresponds to HSI level 3, which we'll see what that means in a moment. And for KDE, we have similar firmware security window. It's a bit more raw in the outputs. We simply have a log from this FWPD HSI tool, which is listing a number of features and whether they are checked correctly. So we have a green color, or incorrectly, then we would have a red color. And in this case, we also have this HSI 3. It is the same platform, just showcased on different desktop environments, how this is presented. So just for completeness, what FWPD is anyway, it's like a tool for applying firmware updates from Linux vendor firmware service. Beyond updates, they also propose this HSI scoring to have some security report of the platform. And this HSI has been proposed mostly by FWPD maintainers, so Richard, Mario, but also some partners. It's still in progress. You can see the specification in the last link. So how it works, very briefly. So we have a number of levels. It's like a layered approach. So if we can to achieve the higher level, for instance, HSI 2 and or HSI 3, we must meet all of the requirements from the lower level layers. So for instance, if we do not meet any of the HSI 1, like TPM presence or SPI write protection, then Even if you meet all of the from HSI2, we cannot get HSI2. We must meet all of the lower level requirements first. That's the approach they are proposing here. So the colors doesn't work in this table. So I'd like to now focus on the inputs. So what kind of interfaces are being used by this FWPD toolkit to learn about the security properties of the platform. As you can see, there are a number of interfaces being used here. And as an exercise, I've been trying to categorize them to indicate which are, I would say, are using the proper interfaces for user space applications, or which are a bit more hacky, and maybe there is some improvements on the kernel side to expose such informations to user space more easily. So my goal was to categorize it, to assign some colors. The colors doesn't work after uploading to BBB, it appears, but we have like a couple of, on the top are greens, then we have a couple, two in yellow, and the last one is in red. We'll see them in the next slides. So let's go through them one by one. So firstly, we have those I call the proper user space interfaces, like SysFS. So one of the requirements is to see if we have TPM, what is the version of the TPM. So we simply read some file, and we already can see the TPM version. Another is about supported suspend mode. So we can also easily learn that from the SysFS. What are the supported modes? What is the active mode? It's very straightforward. Then we have ACPGA tables. We do read some information from that as well. So we read from SysFS firmware ACPI table, and we check some flag. That's also probably fine. We also read some UEFI variables for assessment. That's also very well defined user space interface to read those. For instance, to learn about state of the secure boot, or if it's configured correctly. Then, so that should be yellow. Apparently, it's changed all of my colors to green here. So I would say this is not perfect. It's probably maybe something to be improved here. One of the checks is that we read MSR registers for Intel platforms. For instance, to maybe let's go through this flow. So we open the dev CPU MSR device. We read from specific offsets, and then on these specific offsets we get the register value, and we must parse this. Check the specific bits in those registers to learn what is the configuration, if it's correct or not correct. So the problems, we need like root permissions, we need MSR kernel module, we need low-level hardware knowledge, because we need to know in user space what is the layout of this debug interface register, for instance, what are the bits and which bit we must check to confirm that, for instance, this debug interface is disabled, or this memory encryption is correctly enabled. So possible improvements, possibly kernel could parse that for us and show us in SysFS some attributes. Example might be AMD, where we have a PSP PCI device exposing this debug log on, and TSME status, which essentially show us the state of debug interface and memory encryption in more user space friendly way. Another one is Intel Flash descriptor. So for some checks, we need to check various attributes of IFD as well. So how it works, we must open the dev mtd0 device. We must read some start of that, parse the structure, and also check some bits inside to assess whether it's configured correctly or not correctly, secure or not secure. Again, problems, we need root permissions. We need to parse this low-level structure, which describes how firmware is laid out in the BIOS SPI flash. We need to support multiple IFD layout versions because there are 3 right now. Maybe there will be more in the future, so it's all in the user space. And we, again, need to parse those individual bits, check those individual bits to see if the write protection states are configured correctly. Again, this could possibly be done by kernel once and simply exposed as some sysfs entries, possibly. Another one that was read in my slides initially before converting, before uploading to the BBB. So another method FWPD uses is that we parse PCI configuration space registers of selected devices. So in this example, we have the Intel PC-H device. So we open its config space file and we read register at offset, in this case, DC, which is BIOS control register. And then we check for the specific bits in that register, like write protect disable, BIOS lock enable, SMM BIOS write protect, to see if we have properly locked the firmware flash, if the OS access to the firmware flash is correctly limited. Again, this is quite low-level stuff, and possibly it's not the way that it should be done. Maybe the kernel could do that also and simply let us know what is the state of those flags. Another example is PCI. It's again parsing PCI config space, but this another device is management engine, not PCH as previously. So again, we open the config space of selected device. In this case, it's device number 16. And we read registers. In this case, we have 6 of them, not just one, at specific offsets. So we need to have those offsets in the user space. We need to have layouts of all of those registers in the user space. There are different layouts depending on the management engine versions. FWPD currently has 2 sets of layouts for 17 and older, and for 18th version of ME and newer. But in reality, we would need more, because right now we would need 4 or 5 to be very specific. And with each new Intel processor, we have new ME versions and different, again, layouts of those registers. Another problem is that if we disable the ME, some users want to do that. We have false negatives because, for instance, we use this to check the Intel bootguard state, and Intel bootguard can still work. But if the management engine is disabled, we cannot really, from the OS, learn if it's configured correctly as it was supposed to be. Again, possible improvements. We could possibly parse it in kernel, those status registers, and simply expose the relevant security flags about management engine or Intel bootguard configuration as some sysfs flags, which can be read from user space. Going further, what we could imagine, maybe we could have like some centralized security posture API, which is reusable across tools, so not only FWPD. You could maybe make your own policies, your own ranks, what you care about, but you would need some the low-level details already sorted out in kernel, possibly. No need for root privileges to check them. That's also another benefit we could have here. So yeah, in general, it could be simplified, and we can say maybe a similar pattern to some extent already exists. We have this CPU vulnerabilities already in kernel that says that provides some simple metric. For instance, I can check if my platform is vulnerable to some meltdown or some different kind of vulnerabilities. It already says affected, not affected. So it's very simple to end user. Maybe you could have something like that for some firmware configuration, for some hardware configuration problems. Okay. What are people supposed to do with this information? With which information? On the HSI report in general? I'm not sure if I get this question. The question is about what are people are supposed to do with this information.
By the time they can see this,
The HSI stuff. Okay, so the HSI stuff in general, as we shown in the initial slides, it can even drive your so one way is that you have this information in this GNOME FWPD report, and for some of the stuff you can actually take some actions. You can maybe configure the secure boot properly if it shows it's not configured properly. Maybe you can do some other configuration changes. Maybe you can apply BIOS update, and maybe in the next BIOS update some problems are fixed. Maybe you can complain to your hardware vendor that it achieves HSI 0, which is terrible, and the competition is having HSI 3, which is better. It can drive purchase decisions as well.
I'm guessing the point is that you can't use it as a security thing, because obviously if you don't have this, if there is a security issue with secure boot, you could end up with a kernel that lies about what parameters are. I think that's the point, effectively. So, like, you couldn't have like a security policy based on what the output of these tools are, because if the kernel is if the system is vulnerable, you could boot a kernel that lies about what actually the system is providing. I think is the actually he says that was the point he was making.
Okay.
Yeah.
These reports are not helpful or effective because you can't know whether they are truth or lies. So what is effective? How can we?
the way to solve this, other than making vendors alive.
It's a way for checking some stuff, right? The checks are documented. The specification is documented. There are very specific checks like making the BIOS. Yes, we have a question.
I think HSI was invented just to put pressure on the EOM, right? It is nothing
Yes.
more than that. So
Mostly to have
statistically, even if the kernel is attacked, even if you're lying on the HSI level, not every laptop out there will be lying on their HSI level. So you will be able to drive buying decisions to improve security.
to have some like, as I said, easy metric for end users to see if device is, what is the more or less security of this device. Is it bad or is it good? And as you said, to have like some comparison between vendors, that this vendor can achieve HSI 4 and this one only HSI 2. So when I get my new laptop, maybe I want to get this one, which has better security level, so to speak. Yes, that's the point here. Yes. Okay, so we have one more. Is there something where these reports are uploaded so people can do research ahead of time, because purely local reports aren't quite enough for pressure? I'm not sure if you can get them from LVFS right now. Definitely, if there is a place, it might be in the LVFS. There might be some information about that. I'm not sure. Right, I'm not 100% sure if there is like a statistics of that right now.
So going back to this firmware security interface idea, is there a database of things like you are on a known Intel management engine firmware that has CV, blah, 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 and so on, that you can actually, well, say, yes, I should upgrade because my Intel ME is compromised? Is this something we can do today? Is there a centralization of this information?
I'm not sure if I got it. You are referring to Intel ME versions?
So the kernel currently today offers vulnerabilities for CPUs.
Okay, yes.
The kernel knows if your CPU is affected by some side channel thing of the jour. Can we do the same for firmware vulnerabilities, such as Intel ME or AMD PSP vulnerabilities?
Well, in that case, you would, if you say about specifically vulnerabilities of some specific ME versions, that you would need to have some kernel database of those versions. That's probably not the place. But here we are talking about some configuration issues that we have. Maybe the BIOS is accessible from the operating system, which is clearly a security problem, right?
Okay, so it's out of scope for.
Yeah, I think it's more to the like firmware software bill of materials, and those we can get in LVFS perhaps. Yeah. So we have another one. This is ours.
Okay, cool. Hey everybody, I'm George Wilson. I lead the Linux on Power security team at IBM. I have 3 major sub-teams. We work on cryptography optimization, secure boot, and kernel hardening. And this is a bit about the secure boot aspects. And I'd like to thank my co-authors, Nana, Avnish, and Nageshwara, for contributing to this. Let's see if I can. The arrows don't seem to work. There we go. So with Daniel's admonition to make this interactive, towards the end, I intend to make it very interactive. I'd like to do a quick review of our stack. We are one of the odd IBM platforms, maybe even odder than S390X. But Just to review, IBM Power servers nowadays all run Power VM, a type 1 hypervisor that provides an abstraction layer on top of the hardware. We run these LPARs, these logical partitions that are strongly separated VMs in which the actual operating systems execute. And the partitioning, IO topology, and other aspects of system management are done through a host management console, separate machine. Each LPAR has an open firmware instance, which is called partition firmware. And that it's a IBM-specific implementation of open firmware. And it's been around for quite some time. OS boot is initiated by partition firmware loading a client program, as it's called in open firmware. In our case, that's currently the core.elf for grub. And it resides in a special well-known partition called the prep partition, which doesn't have a file system, it's just a bare partition. Or it's downloaded currently over TFTP in the case of network boot. And then control of all this is managed by open firmware variables. We have trusted boot to measure and create artifacts, and secure boot to verify the client program before handing control over to the OS. And we have this weird thing called client architecture support, where characteristics between the client program and the firmware are negotiated. So things like how much memory you have to load the kernel, the bootloader, what kind of page table you're using, whether you're big, little, Indian, all kinds of characteristics like that. There are many of them. And importantly, some of them can cause reboots. And that's fun in some instances. So here's a little diagram that depicts that. We actually got into situations where this CAS negotiation caused boot loops. So grub negotiates some memory, the kernel comes up, negotiates memory again, causes a reboot, grub negotiates memory, the kernel negotiates memory. This can also occur with kexecs. So kexecs of arbitrary kernels are problematic right now for us. And then over here on the right, we have dependencies on 4 different cryptographic libraries. And right now, the most problematic one is embed TLS, and I'll talk about that one in a bit. We also have a virtual TPM. Everything is virtualized, so we also have this thing called the platform key store, which provides sort of the equivalent of flash storage, but it's all virtual. Everything gets stored back to the BMC. So we have some fairly severe memory restrictions. You might think, well, it's nice to have these virtual things. Yeah, that you should be able to do whatever you want to do with them, but we're actually fairly limited right now. In the future, we should have more memory to be able to store state back between reboots. So, you know, a little bit about secure boot, and we care about how the system boots because we have to implement secure boot. And our team has ended up being a fair amount of the center of competence for booting the system, for better or worse. And since it's always virtualized, we have to deal with things like live partition mobility. If you want to float these VMs around, you know, do you have the partition key store available? Is it configured? Do you have a virtual TPM available? You can't migrate if you don't have it. We'll prevent that. But we do have a different and generally simpler secure boot model versus UEFI. The authenticated variables, as I mentioned, are stored in PKS. There are no there's no SMM, there are no SMIs to deal with. There's no out-of-band management of the authenticated variables. We would like to do pre-provisioning at some point, but right now that's not there. There is no central secure boot signing authority. Either IBM currently provides default certificates, or the system administrator takes ownership by creating a PK themselves. And so that means there is no shim. We don't have need of a shim, or haven't found a need for a shim. So hopefully simpler is better generally with security. Of course, it depends on the implementation, but so far we're fairly happy with this model, and we don't have to go back to anybody external to us to sign anything for us.
Okay, so I'll give you an interactive question then.
Sure. Okay.
If you have no shim, how do you get keys into the kernel keyring? Because if you're acting like secure boot, they all go into the platform keyring, which is not part of the trusted secondary keyring infrastructure.
Well, I mean, we can load them when we want to load them. I mean, you know, for that matter.
But the usual problem we have with customers in most clouds is they come with stupid modules like sysdig or something that they need signing and then inserting into their kernel. And the way we tell them to do it is you put your keys in the mock variable list, that goes into the secondary trusted keyring, your module can just insert into the kernel.
Yeah.
What's your equivalent
we
story?
have variables where we can put them in. So we modeled our variables on UEFI, but the variables don't have the same semantics as UEFI. So we have, like, for say third party module verification.
Yeah.
We have a trusted CADB and a trusted third party module DB that's separate from our DBX specifically for that.
So basically you have a special variable that goes straight into
yes.
secondary keyring.
Yes, we do.
Have you told Mimi about this?
Mimi's very well aware of it.
Okay.
Mimi's helped us with this. So.
Is it part of PKS or it is something different?
It is part of PKS.
Oh, okay, thank you.
Yes. All of our stuff goes into PKS. And we right now have a very fixed PKS and a fixed set of variables. It's not arbitrarily extensible. Greg KH didn't like arbitrarily extensible PKS when we submitted the patch. Maybe we can change that in the future. So we created this static key management mode specifically to meet common criteria protection profile requirements. We didn't intend it for general purpose use. And we also had some problems with what we call RTAS, which is an interface to go manage control of the system. It mapped firmware through DebMem, and with lockdown, that was prevented. So the system wasn't terribly manageable. That's been corrected. There's now a message passing interface that deals with that. The physical presence is not with the administrator of the LPAR, it's with the HMC admin. But once the HMC admin gives control to the administrator has full control over the LPAR and takes ownership of it. And the existing static certificates become default certificates. And that can be cleared. Essentially populates the DBX KEC variables. So we do have a KEC, and that means that we, can have distros do key management. We can essentially delegate key management to distros. And I think I've said all I wanted to say on this. So on to some of the current considerations. So we've fairly recently added KVM support for L2 guests. IBM just has to have level 2 guests on top of the existing hypervisor. And this is fairly nascent work, but we don't have secure boot for it yet. We intend to create a secure boot so we can, provide the same experience, authenticate the images and what have you. But We won't have the same security guarantees. And this is a problem for Z as well. I've talked with Reinhard Bunken on the Z side. I mean, it's a real problem, right? IMA appraisal, I think, can get us fairly far, but is it good enough? And I think maybe James is not here, but maybe I got some hints from James Morris's presentation.
I'm just waiting for you to finish. So if you're running an L2 hypervisor, KVM, it has to have a firmware. Why doesn't it just use EDK2 firmware? Then you would just get secure boot.
Why don't we just use...
Well, yeah, it's either that or CBIOS.
I know.
KVM.
Well, yeah, that's actually, that's an interesting thought. Yeah, because there was work by Ben in the past to, bring EDK to power. So
well, yeah, the point is this is a doctor-doctor problem. KVM will provide you with secure boot as long as you use OVMF.
Yeah. You're right. That's a good thought. Thank you. I don't think I'm going to get my colleagues at IBM to buy into that, but yeah, that's an interesting suggestion, James. So yeah, I think the immutability things that James Morris was talking about might apply here. He was talking about containers, but to KVM in our case. So yeah, I wonder if we can get EDK2 on S390X as well. a big Indian EDK2. I don't know. Yeah. So post-quantum cryptography affects all aspects of secure and trusted boot throughout the stack. We're still waiting on the IETF standards, as is everyone, and they need to make their way into libraries. And of course, for trusted boot, we need TCG to upgrade the TPM standard. So anybody have any thoughts on what a realistic time frame maybe is for PQC support?
I have one comment for one of the bullets. I think that you can scratch it. We have updated the libgcrypt in Grab. So this is the latest one. And I think that it should solve
So you have MLDSA in there?
Yeah.
Okay.
Yeah. So the Grab have the latest libgcrypt right now.
Okay, cool. That helps. I think it really will be 2030 at the current rate. We wanted to accelerate that, but really we have to all wait on the standards to make their way through. So any other thoughts on post-quantum? If not, I'll move on. So our friend Embed TLS, we have a known timing channel attack that we submitted a patch to Embed TLS, and it's been waiting for a couple of years. I won't tell you what it is, but this is on the cryptography side of my team. And this was actually brought to our attention by an external researcher. And that, wasn't sufficient to get them to review it. They will consider it next year. They've been reorganizing, factoring out cryptography into a separate sub-project. I've started attending their meetings, and I think one of the things to help that might be to put some energy into it, much like we did for Grub, because it, is a very small community. Does anybody else use Embed TLS, and have you had any experience contributing to Embed TLS? We like it because it's small. OpenSSL is, libcrypto is really large in comparison, but it's become a problem. But they do at least have MLDSA on their roadmap right now.
So we have been having similar considerations when we implemented TLS support in the kernel for NVMe. There also was the question, right? Which library do we use if we are going to add? And Embed TLS also was one of the possibilities, but then we essentially said no, even though it might be small and might better suited. in the end, this is security relevant.
Mhm.
So you'd rather choose a library which is reasonably well audited and which at least has a chance to be qualified for, for common criteria and whatnot.
Mhm.
So if you now go for embed TLS, say, question is right, there's a fair chance you actually will have to do a full audit on embed TLS if you ever were to go to do
Yeah, we're planning on doing that actually.
CC1.
Yeah.
So we thought that it's far more useful to switch to one of the larger or better known ones, i.e. OpenSL or GNU TLS even though they might be larger. The hope is that we will getting less issues with that down the road. So it might be one consideration really would be to switch away from embed TLS.
We would like to do that. We wanted to do that. OpenSSL is executing in an adjunct partition in firmware, and it uses this message passing interface.
Yeah, so OpenSL, but GNU TLS is actually quite reasonable in that regard. So we have had relatively good experience in both embedding this in our project, but also contributing to it. So that worked reasonably well.
Okay.
So my question is a licensing one. How do you get embed TLS to work with Grub? Because one's Apache 2 and the other's GPL.
Oh, it doesn't work with Grub. It's in our partition firmware.
So you basically...
The license is compatible.
Okay.
Yeah.
Consider libgcrypt because we are using it in Grub and we stripped not needed parts from it. License, okay.
License, yeah. Yeah, we need it in our firmware.
Because as you can see, libgcrypt is currently, let's say, under development, let's say. So it is quite actively maintained, and I think it would be quite, from that point of view, quite good solution. But you have a license problem.
Yeah,
okay.
but it's the license problem. Yeah.
So yeah, embed TLS from trusted execution environment perspective, we use it in Opti as an alternative to libcrypto. So libtomcrypt basically. So yeah, it's useful there, providing all the certificate support and everything for the trusted applications. And really the TCB in case of trusted execution environment, we want it to be minimal. And this is the minimal library. We can't put OpenSSL there at all
right.
because of this huge code base.
Yes, that's a problem.
We can put this embed TLS in the firmware that people can audit as well. Although it's mostly driven by ARM, and they are moving it towards PSA crypto APIs as well. And yeah, there is reorganization happening as well. But from contributions point of view, we don't find anything that is holding us back.
Okay.
So yeah.
Yeah, I think we just need to put some energy into it, and maybe we can get. It's like every project, right?
Yeah. It's like every.
And I probably won't be able to get to all of the things I wanted to get to, but those were the higher priority ones up there. We have added a capability for multiple signatures within a CMS. And any thoughts on the composition of multiple signatures besides a default OR policy, which is what everybody has right now? Is there a case for an and as well?
That's not the problem. I mean, your default policy should just be follow what Shim and Grub or EDK2 does for multiple signers, which is an all policy.
Right.
But the problem is not that. The problem is the revocation policy. What do you do if one of the keys of your multiple signers is revoked?
Yeah.
Okay, you want to talk?
Because we started thinking about that and discussing with Microsoft. So we don't have a solution, let's say.
Okay.
It is a problem currently for UEFI because one of the certificates valid time ends. So we have to consider we should right now sign PE binaries together using two certificates or not. But as James said, this creates problem. What to do if you have to revocate at least one signature? So this is problematic, and currently we're discussing this.
Specific expiry in EDK2, you don't have a problem. We don't pay attention to the expiry date. But the problem is the way EDK2 is implemented, if you revoke one certificate of a multiply signed binary, binary is considered revoked. And that means that if somebody revokes the PCA 2011 key, as they're planning to, and you've dual signed with it, all your binaries stop working.
Thanks a lot. James explained much better than I. Thanks a lot, James. Okay, I think
All right, I'll
we
stop.
are out of time.
Thank you so much.
If you want, we can discuss in the hallway this.
Okay, cool. Thank you.
Będziemy musieli niestety wyłączyć wszystko i będziesz musiał jeszcze zablokować później slajdy.
Okay.
Bo James musi przyłączyć.
Is what you have to use to move, or do you have to click?
Arrows.
Yeah, all right, arrows.
Arrows or this, but arrows are more convenient,
Oh,
I guess.
That's wrong. That's the wrong deck.
Yeah.
That's not mine.
We don't know what to tell about that.
Yeah, that's not. I'm gonna guess today. No, it's yesterday.
It was he was yesterday, but it was a bit different thing. Okay. Maciej, may we start?
We don't have slides.
Oh,
He's getting the right.
oh, really? Just a second, because we have problems with slides.
Nie wiem, zniknęło, czy... Jest.
Co się dzieje?
Nie wiem, mam pobrane, ale nie pokazuje mi do tego. Jeszcze raz.
Yeah, that's why we wanted to get that. And I, yeah, that it creates problems.
Okay.
Sorry.
All right. Good morning. My name's Daniel Smith,
My name is Daniel Kuiper.
and we're going to be presenting on TrenchFoot's relaunch capability, doing a late launch with the Linux kernel. Oh, sorry. So Daniel helped me along, as well as Ross Phillipson on building these slides up. We're just going to hit the topic real quick and try to get to some discussion and see where it goes from there. All right. So just what we're going to cover today, I'm going to go over the introduction of what late launch is, where it's applicable. Daniel Keeper's going to touch on where we're going with the implementation side of things, and then we'll do a quick roadmap of what we have left to do, and then we'll start talking. All right, so for those that are not familiar with DRTM, it's a TCG mechanism that's implemented on several CPUs. For the longest time, it was only on Intel and AMD. ARM has now got a similar capability rolling out. And it basically allows you to reestablish your root of trust at any time after system launch. Generally, when you do do a dynamic launch, when it's done in conjunction with the system startup, that's usually referred to as your early launch. If you do it sometime after your kernel has started, that's what we generally refer to as a late launch. And again, this is a means to be able to repivot after a period of time to get back to a good state without having to do a full system reset to know what the state of your hardware is. The process can actually be done as many times as you want at any time during the life cycle of the system. it will actually get you back to a root of trust, and then using this capability is what we like to refer to as the secure relaunch solution. All right, so what can you do with it? In fact, there's actually many things you can do with it. I've given talks on what all are the possibilities you can do with it. One of the more common ones that are a lot of interest we've seen in over the last couple of years is mainly just just to reboot your kernel itself, to get your operating system back into a known state. This can be done for one of two main reasons. One is that you want to actually do an upgrade of your system. And then the other one is when you're wanting to switch between different states of the system. So we gave a talk a couple years ago in conjunction with Oracle about how it can be done to move between a management system to provision the hardware and everything, and then move back into a customer deployed solution without going through a full boot of a beefy server, which can take easily 10, 20, 30 minutes, even up to hours to reboot one of these devices. This allows you to basically get back into a new customer load without having to go through all of the retraining and everything. So that's generally what you can do with it. In order to make that possible, a lot of it will be available inside the Linux kernel, and then what's coming up, which Daniel will speak on to, is how we enable this through Grub.
Okay, thank you. As Daniel said, we are using Grub to execute late launch or early launch. We are decided to use also the Grub for late launch because currently the code is there, not exactly there. Currently we have patches, let's say, but we are waiting when the early launch implementation will be in the kernel. Then the patches also will be merged in the Grub. But let's assume that they are there. So the code is existing, and we want to reuse this code as much as possible, and we think that it is possible. After some thinking, we decided to create a new platform. What is a new platform? If you compile the Grub, you use configure command, and this configure takes a lot of arguments. And the most important ones are target, which defines an architecture or CPU type, let's say, and another important argument is a platform. The platform, let's say, more or less defines what is installed around the CPU, devices, firmware, etc., etc. And in this case, it means that we will leave the target as is. Simply it will be x86 or something like that, but we'll define the platform. Probably it will be quite small platform stripped from most of the things, and we'll call gexec. When we have this platform defined, and we compile the Grub, then we are able to generate the ELF binary. Probably it will be multi-boot compatible or something like that. And it will have a separate entry point to get arguments from the kexec and continue execution. And also we will reuse, further we will reuse currently existing code in the Grub. We do not expect major changes, if at all, I think, in the kexec. So this is important thing. So this will look more or less like this. This is simplified diagram. We thought about that, how to show this, but the process is quite difficult. But we decided to skip some not very important parts and show how it works in general. So at the beginning, there is a prior system launch, so it is initial execution of the system, firmware initialization, then system boot, and then we can go into the gexec. The gexec can be entered from kernel proper through kexec, as you can see at the bottom. Yes, I cannot see, but you can see. Through kexec, as I said, and it will jump into the gexec binary which will be simply the grab binary, ELF binary with a multi-boot header. Then this code set up the platforms for DRTM, then passes the control to DL stub, which does final platform initializations and executes DRTM event. The SLRT is a structure which contains needed information which should be passed from gexec and DL stub to the kernel. In this case, SL stub, and then set up kernel, and then kernel proper. As we said, we are going to reuse as much code as possible in the grub and in the kernel. So we do not expect major changes at this point to the currently existing code for the trench boot in this area. So how the deployment of secure boot is, as I said, will rely on the grub, and we expect that we'll be simply configuring the grub with these arguments, run make, and then generate the image. And the config file will look quite simply. slaunch, it means for the grub, initialize the platform for the RTM, and then you have well-known commands like Linux and initrd. And this way, all this paths will be started, and then you jump into the new environment in the RTM thing. And from this point, I think Daniel will continue.
So where are we at right now? We're fairly close to getting the initial Linux Secure Launch Series merged into the kernel. That puts most of the plumbing in place. Once that's in there, it's, as we said, it's just introducing this gexec platform, and all the pieces will be there to do the relaunch capability. The other thing we have coming is the AMD series. That is going to be not so large. There's a few changes there, but mostly it's just all the plumbing will be in place with the Intel patch set, and then AMD will come in. So then at that point, we would have DRTM launch for both AMD and Intel, as well as being able to do the relaunch on both platforms. So that time-wise, hopefully it'll be flowing soon. Hopefully we'll be getting the Linux series in the next, hopefully in the next merge window, if not the following one. We'll see how that goes. Grub will pretty much go fairly quickly once that's in. Yeah, so the Grub series will be done for right after that, and then AMD will be coming right behind it. So hopefully in the next, I don't know, 6 to 9 months.
Yep.
That's our hope. Okay. Any questions?
No one asked the better questions. If no one has any better questions, what about the grub config file format for the gexec image?
Mm-hmm.
That's obviously going to be a restricted set of commands.
As I understand, you are asking, is the grub will be a just minimal binary containing just minimal set of commands?
Yeah. I mean,
yes, it's possible. In general, we are not going to add. First of all, as I said, we are not going to do that much to the platform itself. So this will be quite small thing, but also we do not expect. We are not expecting to add much modules into this image. So it will be quite small.
Yeah, so that's kind of what I was getting at, because obviously you don't have boot services anymore.
No.
So what do the paths there actually reflect?
This one.
Yes.
This is a good question. We said, yeah, you are correct. Good guess. In general, yes, we said that kernel. We consider right now it is not set in stone. We consider two options. as I said in my presentation, we can take the image of the kernel from the arguments passed to the kexec. This is one option, but also it is possible to embed the kernel image into the grab image. This is a second option, but also we can load. No, the third option is not possible. I thought about earlier, but right now it is not possible. So we have two options. One is taking the kernel image from the kexec, or take the kernel image and init.rd from the grab image, which will be generated using grab make image.
Makes sense. Thank you.
Okay, thank you. Any other question?
Now that you've just got this upstream and working, how's it going to work with SD boot and UKIs, which are the new up and coming thing?
SD boot and UKIs? We currently, okay, we don't have UFI. This is a good question. We didn't thought about that. But SD boot, in general, I suppose we are asking, do we plan to support the RTM in SD boot or provide an implementation of the RTM's SD boot, right?
In principle, it should be simpler because it's not as complicated as grub. It's almost a pass-through bootloader.
In theory. Because we discussed, and let's say booting into the RTM system is quite convoluted because how the EFI initialization works in the kernel. I think the art can explain why.
I'm happy to explain. Yes. So basically, what happens with the secure launch is that you go to the stop as usual.
Yeah.
And then basically you throw everything away and you do your original legacy decompressor boot instead.
Yeah.
Which is kind of a wart on this design, but I don't think there's anything else we can do at this point. Which means that while conceptually this should be at a layer below the OS, where the firmware environment exposed to the OS should just look the same regardless. The hardware implementation really doesn't permit that. You come up, I mean, I'm paraphrasing what I've learned from the discussion here, so please take it with a grain of salt. But essentially, you have to drop out of the EFI environment because the CPU gets kicked into a completely different mode, which restarts in 32-bit mode.
Yeah.
And basically has to come up all the way back from zero. And that's very difficult to reconcile with how the kind of more abstract execution context that EFI aims to provide. Which makes it very difficult to make this more general across.
We are not saying it is impossible, but it requires, let's say, I would not say a lot of changes. Some changes in the SD boot, and I think that it requires discussions with SD community, SD boot community, how to do that.
Yes. So as I've mentioned it here again, just for the sake of discussion, but conceptually, what I'd like to see is for whatever firmware magic encapsulates all of this, is where you call exit boot services. You go into something that does a secure launch, whatever, and as you come out the other side, you're just running in 64-bit mode again, as you would otherwise be doing, and just boot into the OS.
Right now, it isn't possible.
Well, I mean, the problem is when you go through, you're making when this is done, when a DRTM launch is done, right? You're actually making a specific CPU instruction, and it actually causes the CPU to go into effectively a lightweight reset state, right? This is how you're reestablishing that you're in a good working environment. If you can go look in the SDM. I mean, it does some things like it checks power rails. There's a lot of stuff that's going on when it's going through this whole process. So, I mean, the going into the 32-bit state is more of a legacy of the fact of when this was designed, right? 64-bit wasn't even a thought at this point in terms of Intel CPUs. So yeah, I mean, pressure on the Intel to, maybe we can get rid of that. I mean, I don't know how difficult that would be, but the fact is that when you come out of that instruction, you're coming into what is effectively a setup environment for you. Another way you could handle that is, and again, this would go back to Intel, is put pressure on them, because really technically what winds happening in Intel is after the CPU comes out of that reset state, it goes into an Intel ACM, right? And so if they wanted to handle this inside the ACM and wrapped it up and gave us a cleaner interface coming out of the ACM, we could do that. Or if they did that, that would help ease our side of it. Outside of that, we're coming, the ACM puts us right back into that same 32-bit flat state for you to pick up and go from there. So
what is preventing you, and I think I know the answer, but just also for the sake of discussion, what's preventing you from taking the code, like there's quite a body of assembly code being added to the kernel just to support this use case. What's preventing you from putting that code in the firmware rather than in the OS? Why does it belong in the OS?
Oh, so the answer is yes, you can. And in fact, I've looked at that idea and seen how we might be able to do that. I mean, that would, we would have to write a DRTM service for EDK2 and work that process up and clean it up that way. So yes, I guess there is the third option, which I am actually looking at doing, or entertaining doing.
That third option would then give you the ability to support more bootloaders, because then you don't have to keep adding this code to all of them.
Well, yes and no. I mean, you still have to. So at the end of the day, you cannot call the get sec instruction while EBS is in place. The CPU will fault. Done. Right. So you have to call EBS before you call this DRTM service. So so whether you do this inside the kernel, you do it inside the firmware, you still have this problem, which what we've worked through, right, Art, is how do we deal with all the setup that's done by the setup kernel or by the EFI stub and transition it across that boundary, right? That's what we designed the SLRT, that took a bit of time. We went back and forth on that. That's what the SLRT got designed, is it gave us this area to kind of be able to, if you can't put it into the image that you loaded in, that you're going to eventually execute, the SLRT is another place that you can put the information that we can handle that transition. But the fact is that because of EBS has to be called, we have to deal with the transition of the data across the boundary.
But of course, this also doesn't solve the problem how to do later launch, because I think that your solution would require runtime services to do that. And is it?
It would be a runtime service.
Yes. Art, do you think that it would be okay to have such functionality as a runtime services, not boot services?
I'm sorry, which functionality?
By the way, you're 5 minutes over.
Oh, yeah, sorry. Okay, we are done.
Okay.
Thank you, James. James, could we restart everything? And okay, thanks a lot.
Real quick to the
services extensible, like you can write it something?
Well,
just so I can answer the person who asked. Yes, you can look at the EFI variables from the DRTM launch.
What's defined in what you have to work with?
SPI you can. Not something you should be using.
SPI?
ACPI.
ACPI, okay. Okay. ACPI, they added some runtime.
Yeah, but the problem is that you're taking firmware code, basically you're taking vendor code, running it at the same privilege level for OS kernel.
Right. ACPI step for this.
A PRM.
Okay. I remember situation with ACPI that's not working with the NF, like they have introduced some.
Tak, on musi to zresetować, bo mamy zły czat po
Yeah, that's
prostu w tym.
right?
On musi niestety to wszystko
Services are second step. There's the variable ones, there's resource system, nothing else is happening.
That's it.
Yeah. Because also, I mean, having been to runtime service in the first place, you have privilege, you have somewhere going at level in your OS. And actually, I guess some of that code will become part of your TCP.
Okay. So one, at least on. But from some of the IRS stuff. Anyway, all that stuff, when you go through a DOT launch on a platform, all the IRSD, obviously, so it's also referred to the framework gets run and my specific gets run in room 3, right, with a specific page table. What ISRB does is that when you do a DRTM launch, so I know that I can record that my handlers are in place, and I can restrict the sweep and sure that whatever their memory accesses are, you can push your code outside of that so it can't.
Yes, and pitch points all that.
Sorry, well, it's a lot there. So if you go with the white paper, it's over white paper, not security for a month of year. So you go through the essence of instruction. Oh yeah, it's what it used to be called.
Taking pictures probably kind of away from no, I'm saying. I think it's
So I guess the question becomes
Basically, make some virtual device with this space. Like I said, I think the demo specific What exactly does it look like?
No. So you can just use arrows here.
Okay. Right.
Or click, but arrows is more easy, I think.
Oh, okay, that's fine.
Guys, we won't start. Guys?
Hello.
Hello, we won't start. Go ahead.
Okay, so welcome everyone. Thanks for this opportunity. I will be continuing basically my discussion that we had in the confidential computing micro conference, and that is to say, attested TLS is a compulsory component of confidential computing, and that's what I take as a starting point. Yeah, so the agenda is that basically I will quickly recap what we discussed there, and I will come to some discussion points specifically that we couldn't cover in that specific micro conference. And beyond that, I have some backup slides in case some specific question comes up. So you are welcome to give any feedback at any point in time. So any question is also welcome. Okay. So this is a quick recap. The use case here for use is the confidential computing. There are other use cases. We have a specific document which is specifically focused on all the use cases. Other than confidential computing, we have others. So I just pick one up here, which is to say that we have a verifying relying party and an attester running on the cloud, where let's say you have developed a nice app, you run it on the cloud, and that's what is shown as the physical machine. You have a confidential computing platform on top of which there will be the coding agent which generates an evidence and sends it over back to you, and the evidence is generated for that virtual machine, the confidential virtual machine which we have. And along with that, we also need to have the infrastructure identity, for example, whether it's running in the metadata center or somewhere else. So you also need to have that identity to avoid the diversion attacks. And the attestation can be put into 3 different places in the handshake. That is the pre, intra, and post. Either you put it before the TLS handshake, in between, or after the TLS handshake protocol. And that's pre, intra, and post handshake. And each one of those have different solutions, like Intel's RATLS, Draft Fossati, one of the proposed standards for intra handshake. And the last one is Draft Fossati Seat Expert, for which I'm one of the authors. And we are standardizing in the seat working group, which has been formed. So the security goals we discussed also in the confidential computing micro conference. A quick recap that there was full agreement on that. All the goals, no new goals were brought up to us that are missing in this whole list that we discussed. And we had follow-up discussions afterwards with some of the folks who kindly spent some time on it. And the conclusion was that these goals are sufficient. They do not have anything to add on this. If you have anything, if you find anything missing, of course, you are very welcome to put that up. Remote attestation goals, TLS goals, and then finally a combination of both, which is the composition goals. So everything we hope is covered in all of these goals. And with all of these goals, basically, we have the results from formal analysis. That is to say, the second column here, IRA TLS, is about the pre-handshake proposal, that Intel's RATLS protocol, or later on called as interoperable RATLS protocol, for the when it was shifted over to the Confidential Computing Consortium attestation SIG. And then the last column is about intra-handshake proposal. That is the proposed draft that some of the authors had, draft for Sati TLS attestation. And that basically you see in both proposals a lot of crosses, which means that many properties are not satisfied. And thus we argue that that is not the suitable proposal for standardization. And we tried our best to see in intra-handshake how far we can go, like the second stream for the intra-handshake, doing all the changes within that TLS protocol. How far can we go? What can we achieve? And the best thing we can achieve is the solution number 5, for which you still see one cross here, which is to say that it does not provide you the correlation with one of the secrets. I will come back to it in one of the slides. The key point to take away from here is that even if you go with intra-handshake proposal, you cannot achieve all the properties. So not all the properties can be satisfied here. So that was the outcome from our formal analysis. And just to quickly recap what TLS 1.3 protocol does, you have server and a client, and basically they do this handshake protocol, which is a part of the TLS protocol. The other protocol part is the record protocol, which is not relevant for this specific discussion. So I have only the handshake protocol, client hello, and a bunch of messages from the server, which is the server hello, encrypted sanctions, certificate verify, finished. And then finally from the client side, the finished message. And afterwards, you have a one-way authenticated channel, which means that the server is authenticated. And optionally, you could have the client authenticated if if the server requests it. That's an additional message certificate request that the server will send, and then the client will also send additionally certificate and certificate verify messages. With that, it will have a bidirectional mutual authenticated TLS channel. So with this background, I want to come to a specific discussion point that was left over yesterday. I couldn't reach there in the confidential computing micro conference. So the thing is that we have this TLS protocol that I just showed you, like the messages which were shown on the last slide for TLS 1.3 protocol. I'm now showing it separate, each message separately. That is the client hello message, server hello message, encrypted extension, certificate verify, finished, and from the client side, again, a finished message. So each message separated. That's again only one-way authenticated channel. So I'm not showing the messages for two-way authentication, just to simplify the things. And on top of that, I am also showing here the, do you see the arrow? Yeah, okay. So I'm also showing here the key schedule. The three boxes which are here are the standard TLS 1.3 RFC 8446 key schedules. At what point in time keys are generated within that. And it's a very abstracted one for the purposes of this specific discussion, not to make it very overwhelmed. So the three keys I show at three different points is showing what state of the TLS handshake protocol goes into that specific key derivation. That's all what I'm trying to show here. It's way more complicated than that. Like it's a bunch of keys which are generated within that TLS key schedule. But I'm only showing that three keys which are really important from state perspective. The first one is ATSC, which is the application traffic secret of the client. And that is a function basically only of the client hello message. It takes no other contribution from the handshake itself. So it binds only to the client, what the client sent, and not to any contribution from the server. And that's why it's really insufficient. That's the early exporters are basically derived from this. And that's why the early exporters are insufficient, because they bind only to the client and not to the server. Server can still forward these things to the others, some other relate over to some other party, and then you can get that evidence and show it as your own evidence. So it doesn't solve the problem. The second is the one which is shown as the HTSC, handshake traffic secret of the client. That's another key which is generated within the TLS protocol key schedule. And what it does is basically it takes as contribution GXY, which is the shared secret, which is generated from contribution from a client as well as server. So it's better than the previous one, that it takes from both client and the server. And you see also that it has the log HS, which means that's the running log. So the one in the yellow that's shown here is the running hash, which means each message, client hello, server hello, appended together, and then it takes a hash over that, and so on. These hashes are computed like that. So the contribution which goes into this secret mainly is like the GXY and log HS, meaning that it has contribution from server hello and from client hello. Both contributions are there. So this is one of the possible candidates for doing that binding to server. And the final one is the ATSC, which is the application traffic secret of the client, which takes into contribution additional to GXY. It also takes into contribution the log finished of the server, which means transitively it includes everything which was done until log finished, because as I said, it's a running hash. This means like client hello appended with server hello, appended with encrypted extensions, appended with certificate, appended with certificate verify, appended with finished, and hash of all of this appending that we have done, which means that it's pretty much clear that it's very strong as compared to the secret that we have here, which only had the two contributions, client hello and server hello. That's why we argue that this secret, which is the application traffic secret, is much more stronger than the handshake traffic secret of the client, because of the reason that it includes, other than the client hello and server hello, many other messages and much more state as compared to the state which was included in that specific secret. So with this reasoning, we argue that basically it should be the application traffic secret which the evidence should contain or correlate to, that I will define later. So it should correlate to application specific application traffic secret rather than the handshake traffic secret. So this is one of the discussion points I want to discuss, like if there is any disagreement on this specific point, because this is critical for making a decision whether we go for intra handshake attestation or whether we go for post handshake attestation, because this secret is used in intra and this one is used in post handshake. So to me, it's very much clear. And as I argued, it should be clear to you as well that it is post handshake is doing pretty much strong binding than an intra handshake. But I just want to pause here for a sec to see if there is any support for whatsoever for intra handshake, so as to say that whether someone supports that or argues that this one is sufficient. Okay, nobody in the room. Okay, so then I proceed with the second argument. That was not the only argument I have for binding to application traffic secret of the client. That is to say, from a security perspective, not from the privacy perspective, handshake traffic secret and application traffic secret do completely different jobs. The job of handshake traffic secret is to encrypt all messages starting from 1C up to the finished message from the client. And only these handshake messages, not the application data. Application data which you send after doing that handshake is encrypted using this secret, which is the ATSC, application traffic secret of the client, which automatically means that basically ATSC should be the one that you should bind your evidence to. And that's the one which is most important, because that's what you care about. The client at the end of the whole handshake and all of this attestation dance, it needs to send over some secret over to the server. And that's why we argue that this secret is the one that it should relate to, rather than the one which is for the handshake traffic secret. And there is another formal argument for this, which means that basically the HTSC is irrelevant for any security analysis, just because of the reason that if I do a formal, and I actually did a formal analysis by doing no encryption of these handshake messages, on top of the handshake protocol, there is a record protocol which does all that encryption of these messages with using these secrets. So what I did is, in my formal analysis, I did no encryption. I assume there is no record layer. So without any encryption of these handshake messages, and I could still prove that the security remains the same as it would be for encrypting these messages. So that's why I argue that HTSC, the handshake traffic secret, is completely irrelevant for our security goals. It's for the purposes of privacy, that nobody knows that, let's say, you and I are communicating at this point in time using this TLS connection. So it's important for privacy, but irrelevant for security. And doing the security analysis here, or looking at the security goals, it's really important to understand that this is not the thing that we should correlate to or bind the evidence to. Rather, it's the one which is the ATSC, which it should be bound to. That is to say that is used for the application data, and that's the secret that we want to protect for in the evidence. I again want to pause here for a moment, because this is again a critical point that is important for the decision between intra and post handshake. And next month we have an interim in IETF seat working group where we want to really make a decision, and I want to take your input into account to see that we stay compatible with what all of you folks are doing in here, so that we take all the requirements in by doing. That is to say that if we go for post-handshake attestation standardization, is there any disagreement in the room on the arguments that I have presented here? Right. So I don't see anyone. Right. So I will then continue. So with this assumption that we all agree that there is consensus on the post-handshake attestation, that's what we will then do. So I'm just quickly summarizing it. pre and intra handshake as per formal proof of insecurity. There is a link also in the page, so you can have a look at the formal proof, which is all public, and analyze it further and build on top of that. So the key insights we got are like the 4 attacks which are shown, the 3 attacks that are shown here: diversion attack, relay attacks, and replication attacks. We can prevent using post handshake attestation, and by doing that, that allows us to get rid of all the problems that we have. And it's one of the most challenging protocols. That is to say, it's not only simply a protocol, it's a lot of architectural complexity which is involved downstairs, like the architectures like Intel SGX, TDX, ARM CCA, AMD SCV, and all that. So that adds a much more than making it a simple protocol analysis. And we the formal analysis for part of that analysis that I showed you here has been accepted at Asia CCS. That's one of the top ranked security conferences. So all the results, the paper will be out in a few days. So then I will link it over to this page as well. What we are doing now is that I'm continuing the formal analysis I showed you for pre and intra, and I'm now doing the formal analysis for the post handshake, which is our draft, this draft for Sati Seat Expert, using the same tool ProVerif that I have used for the other analysis. That will again similarly be publicly available for you to analyze or to see and get trust in that. There are 2 ongoing implementations, one in Rust TLS, that's Peg Jones is doing that, and one in Boring SSL. Powell is doing on that, working on that. So I think I already discussed this security goals, HDSC. And if you have any solution in mind that you think can be a possible candidate, please do bring it up either to me or to the seat working group in the IETF, or in some way, so that we can look into it further. So these are some of the resources which you can have a look at. And finally, I would like to thank all the people who have contributed to it. Me being here, the presenter only, so many people have put their efforts into all of the work that I'm presenting here. Especially in the IETF, people have contributed a lot by either being a co-author on the left side or by providing some feedback to us. So that's pretty much it, unless there is some backup slide required. I think that's very much from it. Say yes, please.
So when you talk about a post handshake attestation, does that mean that the TLS session will be established and the client could send data before the attestation is complete? And is the answer just don't do that, or do you have some way to make that harder to mess up, and to make sure the attestation actually occurs?
So the post handshake works like this, which is to say you have a standard handshake done between the 2 parties, client and server, and then the one-way authenticated channel exists, right? But what you do on top of that is, once that channel exists, you send, according to RFC 9261, there is an authenticator request message, which is essentially the same as client certificate request. And you get back an authenticator which contains these 3 messages: certificate, certificate verify, and finish message. And within the certificate, you contain the certificate message contains that evidence. So at the end of all of this, the application data should only be sent after of this.
Okay, so application data has to follow the authenticator request message, so the attestation
Exactly.
will have to.
And also the appraisal. I mean, on this side, you should also appraise it. And once the appraisal is done, only then you should send over the secret data.
I see. Thank you.
Yeah, welcome. Any other thoughts or questions? Okay, then thanks very much.
Sorry.
Well, you can just use those keys. And...
left, right.
Yeah,
excellent.
Does it work?
Cool. Yeah, thank you. So my name is Andre. I'm here from Google DeepMind in London, and I'm joined with my. Oh, yeah. Okay. Hi. So yeah, my name is Andre. I'm from Google DeepMind in London, and I'm joined here with our partners from Meta.
Yeah, sure. Yeah, my name is Kevin. I work at Meta. I am part of the private compute platform team. We're the ones who did all the WhatsApp private processing stuff.
Cool. Yeah. So today I'm going to talk a little bit about a custom minimal firmware that we built for mostly, the main target is confidential virtual machines, but I mean, you can use it with any virtual machine you want. So as a bit of a background, why we started building this in the first place is that State Zero was built as part of Project Oak. And you can go and check out our GitHub repo. It's all completely open source. And the idea with Oak is that we want to provide some externally verifiable claims about system behaviors. And this is different from what you can kind of imagine what like your average cloud provider would want, because the cloud provider is interested in providing evidence to their customer, and we in the Oak world, we're interested in providing evidence to like the end user, as in if we want to do some processing on the server side in a confidential virtual machine, how can you know that what we are doing with your data actually matches what we say? So this is kind of like the bigger goal. And yeah, so part of it is that obviously I think someone made the point in, I think maybe it was this session or one of the earlier ones, that the most secure code is the one that you don't have. And we've definitely tried to follow that in the Oak philosophy as well. And this goes all the way down to the firmware. So we really start like from the basics. So what we really want from a firmware in our confidential virtual machines is that, first of all, it needs to support like the QEMU and compatible virtual VMMs, because the QEMU is the most popular one out there. We want to run confidential virtual machines, so obviously we need to support SCVSNP and Intel TDX. And this is kind of like the biggest motivation why we started State Zero, is that we want to minimize the amount of code that we have in there. So as simple as possible. That was like the driving goal for why we started it. And yeah, and in the end, we're interested in booting Linux. Just the kind of like the I would say that this is one of the key design decisions has been, is like, do the minimal thing, do the least amount of work that you need to do to get Linux up and running, and then let Linux deal with it. That's kind of like was our primary goal with State Zero. So what do we have that actually kind of like exists out there? What could we do? So effectively, there pretty much are like three options. So one which is kind of like from the idea of like, we don't want to, well, the most secure code is that code that you don't even run. You could say it's like, what about running like completely firmwareless, like no firmware at all? I mean, we're talking about virtual machines here. We're not dealing with real hardware. So when you start the virtual machine up, you can kind of force the vCPU to be in some known state. You can just kind of preload the Linux kernel into memory, and you could like, off you go. This has lots of benefits, like, again, no code, no firmware whatsoever. And this was the direction we originally started going to, but we were advised not to proceed in that direction because of like issues around TDX, because in Intel TDX, the CPU start in a fixed state. We can't customize that. And yeah, this kind of like firmwareless approach requires the VMM to effectively set up everything in the initial state, which is not something that QEMU does. I think Cloud Hypervisor does exactly that. It's like, it just kind of like loads everything, boots Linux, off you go. And from the existing firmware choices, like, there's only two other options. We got like OVMF, which is like the big gorilla in the room. Everyone uses it. It supports like everything, including the kitchen sink. and this is probably the main thing that why we didn't want to use OVMF, is like, we don't need most of those features. We don't need like block device support. We don't need network device support. So you could argue, it's like, we would need to go to OVMF and start like stripping out like a good like I don't know, 60-70% of the code. And even then it's like, yeah, OVMF is a it's a big project written in C, and we thought we can do something simpler written in Rust. The third option really is the C BIOS, and this is the thing that QEMU still uses by default, I believe. Provides like this, provides just kind of like the basic BIOS services, legacy BIOS services. Doesn't support SCVSNP or TDX, but I would argue it is like the code base is simpler. So we were kind of like we had like three options really. It's like either we start stripping down OVMF, do we start enlightening C BIOS, or we roll our own, and we chose the third option.
Okay, so there aren't just three options. There's a ton of Rust-based firmware things out there. What about TD Shim from confidential containers? That sounds almost exactly like what you're doing with Oak.
I'm now trying to recall because I think I've seen TD Shim. I now can't recall what exactly were the issues around that.
But the basic issue is they stripped it all down like you're doing to support the Kata.
Yes, the
VM
Kata
running
containers. Yeah, that
confidential
project. Yes.
containers. But basically, if
But
everyone...
didn't they still rely on like the OVMF being in there?
Well, TD Shim is sort of a Rust rewrite of the bits of OVMF they wanted. So it aims for OVMF emulation, which makes it helpful and useful when you're trying to attach it to bootloaders.
Okay.
But it doesn't, it's supposed to be fully Rust. I mean, I don't do confidential containers. I haven't looked at it for a long time. I just get the confidential containers people burbling about it. I'm just asking you why, since you're reinventing what they're also reinventing, why not collaborate?
Yeah, that's a really good question. I think it partly might have been that we weren't aware of each other, as always. But yeah, that's probably something to look at. It's like how much overlap there is and how much we could join forces.
Okay. Thank you.
Just following up on this, I think like Google Oak exists for quite a long time when there was no container at all. Like container, I believe, is a new thing than compared to Google Oak. That was that's quite an old project, right?
Yeah, I mean, we started the State Zero effort, I think, around like 3 years ago, something like that, 3-4 years ago.
Okay. And confidential containers, I think, came much later than that.
Well, there you go. Then it could be then that could be the answer. Is like we didn't reinvent the wheel; they reinvented the wheel. Cool. Okay, so yes, we like I stated, we reinvented our wheel. It's kind of like a bit of a bootlog from our State Zero firmware. And yes, like I said, it's written in Rust. Obviously, we didn't need to sprinkle in a little bit of assembly to go in there. We support like SCVSNP, and pretty much the only kind of like hardware interface we support is that we just use the QEMU firmware config device to load the kernel straight into memory. We load the ACPI tables, and that's pretty much it. It's like I said, we intentionally do not support like block devices, network devices, no nothing. It's like that wasn't our purpose. And yeah, the State Zero firmware right now does some like basic PCI bus and configuration as well. That was actually I was hoping that we wouldn't even need to do that, but turns out you have. So Linux does have some expectations about how the machine should be set up. And yeah, it's like for SCVS and above, we do the AP parking, all of that stuff, and critical for the confidential computing use cases that we gathered like the attestation evidence of, and like we measure the kernel, the ACPI tables, the initial RAM disk, all of that. We measure that and use that as the attestation evidence, and we build a dice chain off of that. And yeah, on the SCVSNP, we actually do clear the VMCK 0. What was that? VMPCK0, yes. So that means that you can't get like a new hardware rooted attestation report, but you need to go like you have to have all the dice layers and like the evidence showing that this was like the firmware that was loaded, this was the kernel that was loaded. You can't falsify that up because we've just kind of like removed the key, so you can't like get a completely blank slate attestation report anymore. And how we pass that to the Linux kernel and the applications right now is that we just reserve a page in RAM, mark it as like reserved in the EA20 table, and then just kind of like pass in flags on the command lines. Like if you need the dice evidence, go read from there. And yeah, and then we hand things over to the Linux kernel, and the goal should be that after that, nothing in stage 0 matters anymore. Linux could just reuse the memory if it wanted to. We're not providing any BIOS services. We're not providing any EFI services. No, nothing. Right. So some of the fun things that we've run into. So first of all, obviously, it's kind of like it's a moving target from both sides, as in people tend to do, well, QEMU makes changes, Linux makes changes, and we are on the outside. We're not in the mainline tree for QEMU or anyone else. So we kind of like have to watch from the sidelines and figure out what exactly is required to support various features and to just keep up with the rest of the world moving, because it's not like there's like a written down spec for many of these things. It is kind of like the implementation is the spec, and we need to reverse engineer stuff from like looking at like OVMF behavior to figure out how things work. And what's probably the bigger thing, and this is kind of like the question I would like to pose to the community as well, is that the expectation that you use EFI for booting seems to have percolated through everything, especially in this kind of like confidential computing situation. We have run into bugs in the Linux kernel where it's kind of like there's like an if check going. Is like, yes, we just assume that if you're not using EFI, we're going to just probe this memory address to figure out whether it's like the VGA card is there, and we didn't like mark that memory as accepted, and things came crashing down. So there are like there's definitely points where the kind of expectation of EFI is there, and lots of like newer kind of confidential computing features also seem to kind of like assume that you're using EFI. So this is kind of like, I would say, my question to the community is like, are we fighting a losing fight here? Should we just kind of like embrace EFI and go, it's like, we need to start implementing EFI services? And conversely, is there like a minimal set of EFI features that's just the bare minimum, don't care about like official compliance, but is there like the bare minimum that we could do and just kind of like get things up and running?
I'm pretty sure you can get away with very little. Basically, you don't care about the runtime services, you probably can just ignore those. What would probably make your life easier would be to get the memory map and the config tables and those things, which tends to be what you're, because actually what you described isn't the reliance on EFI. It's kind of a reliance of, well, if you have EFI, we have an architected way, and if we don't, we wing it.
Well, yeah, that's part of it. So
yeah, like I think I'll talk about this later about like kind of an accepted memory, but we've noticed like even though like theoretically like if we have just like all of the information from EA20, like there's like a couple of like points in the kernel where it's like, oh, you're running EFI, so you can go down this path, and that will allow you to do unaccepted memory. Whereas like we would expect that like if it's supporting non-EFI bootloaders, it should we should be able to run unaccepted memory, but it's just in the EFI path. So I'll talk a little bit about that later.
I think we might have possible we have ended up with an unintended semantic of if you're running in EFI mode, if you're not running in EFI mode, well, then you're probably a BIOS.
Yes, this is the this is definitely the case. And like I said, this is one of those points where I would like to pose to community is like, is this even a branch that we want to support? Or are we just completely going in the wrong direction in that?
So in the motivation that you had that providing externally verifiable or falsifiable claims.
Mm-hmm.
I'm wondering, like, so you have basically a relying party which all of these claims will be transported to? Like, how are you doing that? Is it a kind of a post handshake following up on my presentation? So which protocol? Like, if you claim verifiable or falsifiable, somehow the claims
Yeah.
have to reach that. And at what point in time, like, how are you generating that?
So on one hand, I would like to say this is beyond the scope of this presentation, but I would recommend look at the Oak repository. We have the Oak noise session where we can establish. Well, we're not using the solution we are providing is not using TLS right now. That's still up in discussion, and this is actually where. Well, I believe you have talked to some people on
Yeah, so
IT.
you basically use attested noise rather than attested TLS.
Yes, yeah.
But what I'm trying to ask is that post handshake, you do attestation after the handshake has completed? So every transport protocol has handshake, right? So
Yes,
maybe some other words, but you do like
I believe it's after, but I'm not 100% sure because I haven't done much work on that side. Yeah, well, yes. The attestation evidence is in the dice chain. We bind that to the session. Okay. Cool. So that really was like the highlight. So where some examples of the use cases where we actually do use our state zero firmware in Google. There's like the Chrome Cloud Authenticator, confidential federated analytics, and we recently announced the private AI compute as well. And parts of private AI compute rely on the Oak infrastructure. Cool. You've got a couple of minutes.
Yeah, it's fine. Yeah, you guys might be wondering, why is Meta here? Because it's a Google project. We ended up working with, the Oak folks for a bunch of like other, transparency related reasons. But we found out that they had the stage zero bootloader, and for our purposes, we wanted to leverage the bootloader. One, because it's like easier to develop with, but also we can make some interesting modifications that will kind of just benefit both companies. One thing we were really concerned about when we were doing private processing was we wanted to eliminate the attack vector that is AML, which is a custom bytecode interpreter. There's a AMD like security bulletin notice that describes like a way to attack CVMs where you can achieve like a root shell from QEMU. So we wanted, since private processing runs on our data centers, we wanted to really prevent even the possibility of Meta as an adversary in this case. We also saw that stage zero and just parts of Oak are also reproducible like bitwise. So this will help with strong code provenance. And so we have a couple of internal patches, but we're hoping to upstream them so that everyone can use it. And we, both Google and Meta can use the same bootloader. To our best extent, this is the first major consumer outside of Google using stage zero. And naturally, there's a discrepancy between the stacks that we use. We use QEMU, stage zero, vanilla kernel. We have the NVIDIA GPU stack. I think Google uses, their own internal hypervisor, stage zero, kernel, and then I guess the Google TPUs and stuff. So we have a lot of patches that we're trying to do so that we can help make it usable outside of just Google's infrastructure. So there's stuff like kernel hashes. This will help us use the QEMU kernel hash attestation schemes. We have CVE fixes, a bunch of we're possibly considering doing stuff like table generation, as well as making dice attestation optional so that you don't have to use it. I have a minute left, so let me just go really quick. We'll talk about this afterwards, but one of the issues that we saw, with unaccepted memory was that, this seemed to be very, EFI baked in. And, in this particular function, there's a lot of EFI related calls. We initially tried doing some hacking with the kernel, tried to do some dynamic allocation. It didn't work. It wasn't initialized at that point. And then we tried a minimal set of EFI implementations, create your basic table struct, your basic structs, and then that ended up failing. So after this, maybe we can talk about, how can we avoid replicating UEFI, or if that's a lost cause. Theoretically, EA20 should work, but yeah.
Cool.
One question.
Yeah, but I mean, this is pretty much literally the last slide. So, but the kind of the tagline is that we still believe that there's need for this minimal firmware that's smaller than OVMF EDKT. It's something simpler, especially for the confidential computing use cases where as little code as possible is beneficial. So, this is our proposal, our proposed solution for this problem. And yeah, there's like a bunch of other plans, like we are looking at SVSM support, ARM CCA support, even talking about cloud hypervisor and getting Stay Zero up and running there. And yeah, our colleagues from Meta are also looking into like doing some contributions. Cool.
So we talked about this dice chain here. So
Yes.
what's the root of trust here for the dice chain?
It is the CPU. So we do ask like for the hardware attestation from the CPU. So this is like, for example, for AMD SVSNP, which I'm most familiar with. Yes, the kind of like the that includes the initial CPU state, initial memory state of the confidential virtual machine that's signed by the key that's baked into the into the CPU, and that in turn is signed by the AMD root key.
I remember this dice chain. Okay.
Well, I guess you can catch us later. Cool. Thank you.
So we now will have David who is remote. David, can you try taking ownership of the presentation?
I will try now.
You should click on this blue plus and can you see such option under actions?
Under the actions. The
Yeah, on
page
the
is
left
being
side.
on the left side.
In the left lower corner, you have this blue plus, and then you select.
I see it.
Take presenter or something like that.
Yeah, I just did.
You did. So now you should upload. Then now under actions, you should see like your file or upload it if it's not there. Can you see this 1230 file also on your side as well?
I see it. There we go.
Okay, cool. So that should work. If you can already switch slides on your side, then that should be enough. Does it work for you?
Yep.
Okay, we can see that here, so it's fine.
Okay.
Do we wait, Daniel, 2 more minutes? Okay, so let's start if you are ready.
Sure. So sorry I couldn't be there in person. It's a long flight. I'm sure some of you are aware. My name's David Mulder. I work at SUSE Linux. I work on the Himmelblau project, and I'm also on the Samba team. I've been doing identity for decades now. Kerberos, Active Directory, and now working in the cloud identity space. So I'll go ahead and jump in. So I'm talking about the difficulties and challenges that we're facing in cloud identity on Linux. So you can see here the classic Linux auth stack requires, of course, a password. You can authenticate either by like Etsy Shadow or perhaps LDAP or Kerberos. With modern identity, the authentication decision is delegated to a remote identity provider. It's driven by policy and very often completed somewhere else entirely. MFA is usually described as something you know, something you have, and something you are. In this example you see here, the core factor is something I have, my phone. And possession of that device is what allows the flow to proceed. But possession alone isn't enough. The device also proves that it's me holding the device, typically using a biometric like a fingerprint or Face ID. But that biometric, of course, never leaves the device. The IDP isn't authenticating my fingerprint. It's trusting that the device is secure hardware to assert that the legitimate user is present. Modern identity is less about what you type and more about what context can be proven. And none of that is something that PAM was ever designed to express. So PAM and NSS can already handle most of what we need. The problem isn't that PAM can't do modern auth. It's that the user interaction model is incredibly limited. PAM can display messages and ask for simple input. What it can't do is structured interaction. So there's no concept of multiple choice, no way to say, for example, you have 4 MFA methods configured and prompt the user which one they want to use. I could ask you to type a 2 at the GDM prompt for the second option, but of course that kind of looks silly. And some of this does matter in the real world. Perhaps the user doesn't have their FIDO key today, so we can't use the default method. Or perhaps the user needs to change their IDP password. They may be traveling, or perhaps this is their first login and their email exists in multiple IDPs and we need to pick one of those. PAM currently has no clean way to express these choices to the user. The second issue is that PAM conversations can't really branch or go backwards. If I start one MFA flow and realize I can't complete it, there's no way to say, actually, let me switch to a different factor. The only option today is to cancel and start over. That's not because PAM is broken, it's because it was never really designed for multi-step stateful authentication flows. Modern identity absolutely is. But honestly, the biggest problem isn't PAM at all. Modern identity providers assume you have access to a browser at authentication time. And this assumption is baked into most MFA flows. But my SSH session doesn't have a browser. My GDM login prompt doesn't have a browser, although the systemd folks are actually working on that. My SMB mount doesn't pop open Firefox to authenticate. This assumption was wrong from the beginning. We've been papering over it with hacks, device code flows, and polling, but these are workarounds, not really a concrete solution. What we really actually need is not just better PAM dialogues. We need standardized browser-independent MFA APIs for OAuth 2. So given these constraints, let's talk about how this actually works today. So a Himmelblau is a good example, the project that I've been working on, not because it's special, but because it shows that we're forced to do in the absence of standards. To support Entra ID, we had to reverse engineer authentication flows with Git and push browser emulation and implement a daemon that translates IDP-specific behavior into something PAM can tolerate. It works, but it's inherently fragile. Every one of these pieces is tightly coupled to one identity provider's undocumented behavior. If you change the flow, change the policy, or change the UI expectation, then you're back to doing packet captures. And this isn't specifically a Himmelblau problem. Any Linux project integrating with modern identity today is forced into the same pattern, either bespoke protocol handling or device code workarounds. And that doesn't scale across IDPs. What we actually need is not another clever hack. We need standards compliant MFA APIs that are designed to work without a browser. These APIs should let a client say, start authentication. Here are the available MFA methods. Here's the flow type this method uses. And here's how to complete or switch that flow, all in a machine readable way. We've done this before. The device authorization grant in OIDC exists because people realized browsers aren't always available. MFA deserves the same sort of treatment, but done properly, not as an ugly workaround. The UI is a separate problem. Whether a flow is rendered in a browser, in GDM, a terminal, or a desktop app is an implementation detail. The real missing piece is a portable browser-independent MFA protocol underneath. The Himmelblau project now proves that this can be done. The fact that it has to exist as bespoke glue code is evidence that we're missing a real solution, though. So let me show you a little bit what that looks like today. This diagram shows what it actually takes to make modern cloud MFA work on Linux today. On the left, we've got the client. On the right, Azure Enter ID, and this is just a simple MFA path. It's a Microsoft Authenticator passwordless. This is not all of the flows. This is just a simple one. The story starts off normal. We hit an OAuth 2 authorize endpoint. This part is documented in OIDC, and so far so good. The response is where it immediately goes off the rails. We don't get a nice JSON API. We get an HTML page with a big JavaScript config blob buried inside of it. Himmelblau has to parse that blob to discover authentication endpoints, flow tokens, context. None of this is a stable contract. Once we've scraped that config, we start calling a bunch of JSON endpoints like the get credential type and get one-time code and so on. As far as I know, none of these are public documented APIs. There's no spec you can read for how this is supposed to work. What we did was watch the Windows client, captured packets, and cloned what it does. This loop here in the middle is the MFA polling. We send a device code status over and over until some internal authorization state flips to 2. We don't know what that means exactly. There's no standard, there's no RFC. We just know that when the magic number changes, the phone probably authorized us. Then we get a 302 redirect with a fake redirect URI and an authorization code jammed into it. That redirect somehow means forward the authorization onto the local app. Himmelblau has to catch it, peel out the code, and pretend this all made sense. Only at the very end do we land back on something the OAuth 2 spec actually describes, which is the token call. So in this whole diagram, the solid bookends, authorize and token, are standardized. Everything in between is reverse engineered, undocumented glue code. This is how Himmelblau survives today. And to be clear, this isn't an indictment of Microsoft in particular. Any project trying to integrate Linux logins with a modern IDP would need to do something like this. You reverse engineer the web flows, you pull some secret endpoint, you parse whatever the front end team is emitting, and then you pray it doesn't change. As a side note, Himmelblau falls back to a device authorization grant when this path breaks. We had to build in some kind of safety net. So yes, it works. Users can log in, MFA happens, we get tokens, but it's all built on sand. There's no standard MFA API here, and there isn't one for any of the IDPs. Google doesn't have a standard that it follows either. It does something completely different. So there's no guarantee that these semantics will be the same tomorrow. This is exactly why I'm here. I want to argue for the need for a real MFA protocol so that Linux logins don't have to depend on diagrams like this mess. All right. I want to wrap up by talking briefly about the device authorization grant, because it usually comes up as the obvious answer to this problem, if you're familiar with it. A DAG exists for a good reason. And by the way, a device authorization grant is for example, when you authenticate on your smart TV. You scan a code on your screen and type in a number. You scan a QR code, type in a number, and then it authenticates you. And that's the only protocol defined way to authenticate today on a device that doesn't have a browser. The OAuth 2 spec explicitly calls out things like smart TVs, media consoles, digital picture frames, and printers, devices where a browser either doesn't exist or doesn't make sense. In Himmelblau, we do rely on this as a fallback. If the more complex flows break, DAG gives us something that still works. But that framing is important. It works as a fallback, not as a foundation. In the DAG model, Linux basically steps out of the interaction loop. It shows that QR code, and then we authenticate on our phone. For some users, that's merely annoying. For others, it's actively frustrating. A typical flow looks like this. A user types their email on Linux. Linux displays a QR code and that cryptic short code. The user scans the QR code on their phone, manually types in the short code, then re-enters their email address on their phone, then enters their password if applicable, then completes MFA, often on the same phone they're already using, possibly covering up the prompts that showed them the code they're entering, and all while Linux sits there polling. That's a lot of context switching for something people already find irritating to begin with. It also creates some real problems. Linux has to verify that the identity that's successfully authenticated on the browser is the same one the user originally supplied at the Linux prompt. In environments like Entra ID, that's not trivial. Users can have multiple valid accounts, for example, for personal, work, test tenants, contractor identities. And if they authenticate to the wrong email tile, the whole flow has to be rejected and started over again. And then there's some more serious issues. Some users simply refuse, with justification, to use a personal device for work authentication. And this isn't just hypothetical. I've encountered this in the real world. In some countries, users have legal backing to refuse using a personal phone for work sign-in. In those cases, DAG just doesn't work. The company has to issue a hardware authenticator, a FIDO key, a smart card, something like that. And personal devices can't be part of the loop at all. And DAG authentication fundamentally fails in that scenario. So the issue with DAG isn't that it's incapable. I turned the slide too soon. Sorry. It's that it solves most authentication scenarios in a way that's irritating, exclusionary, or policy hostile, and it still doesn't solve all of the issues, which puts us right back where we started. What we actually need is an alternative that doesn't assume a browser is always available, doesn't assume a second device is always available, it doesn't push the entire interaction off host, and can still express modern MFA flows in a structured way. And that's the gap that I'm trying to fill here. And I honestly don't know what the solution is going to look like. I assume it would be probably an OAuth or OIDC extension, maybe some new IETF work. I don't have all the answers. What I do feel pretty confident about is that this problem is real, and today we're solving it by reverse engineering web flows and hoping they don't change. So I'm going to go ahead and stop there, and I hope we can have some discussion about this. I can take questions on the chat if you'd like, or in the room as well.
Thank you. My question is like a comment or maybe even contribution to the problem is, in normal case, like if you just like zoom out for like just secure authentication, in normal case, it's kind of like it's doable without standards one way or another. The problem that I've saw once in a while that our servers are offline for one reason or the other, and then you can only use like emergency access to log into a server which is hooked via a serial terminal. So all you have to implement a secure authentication flow is a serial port, literally. So do you have any ideas how to extend your proposal to work on reasonably well on a serial port, or maybe just doing something wrong? I don't know.
Over a serial port, I'm not sure what you're getting at, but you said something about offline. So like if the host has no access to the internet, is what you mean? Well, we
So
faced
like
a similar problem.
the host is down, like you can access to a serial port, you want to debug it, but you also want to access it securely, right? So you don't want to just like a default, like a backup password authentication, because that's kind of like breaks the whole model of, like it will be like the weakest chain.
Yeah, and that's something I've been thinking about actually. So one of the things I've been considering right now in my project, one of the ways we work around this is the user is authenticated to using this device authorization grant, this hacky workaround with the QR code, and then they register a local credential, and that local credential gives them access to the host without having to use that MFA flow every single time. Now that works, and but in a lot of occasions, in a lot of situations, that's not a good idea. For example, I explicitly tell my users to disable that behavior when on systems like there's universities that use it for students accessing a shared server, and that's not a reliable solution because you don't want essentially you're falling back to just a password authentication at that point. One of the things I was considering is that we could have we could bind an authenticator app, for example, to the local, and then you would have MFA that would be bound to the local device instead of bound to the network, and it would still unlock that user's remote credentials. So, I mean, does that make sense? What I'm getting at? Because then, for example, if you're debugging the host over a serial port, you could enter your local password and then MFA using your local device, your local authenticator code. That would be an option.
So quick reaction to this question. The software to do that already exists today. Has been written by Google, and it's called GLOM, Generic Low Overhead Message. And you can use it to do like a custom authentication protocol over serial console for BMCs that are locked or emergency accesses. And it's cheap enough for the serial console transport rather than like a fast transport where you can do OIDC stuff, right?
And that's it.
So I felt like the discussion was more about client devices for this talk rather than server devices where you usually don't access them over serial console. And I have a question for those client devices, which is, will Himmelblau try to accommodate more than Azure Entra ID and be a generic PAM plugin for IDP that would honor the standard that you're describing or that you would co-develop with other people?
So it's a good question. I started it as targeting specifically Entra ID, and I had planned to add like Google Workspace support, for example. But the problem I'm encountering is what I'm pointing out here is that MFA does not have a standardized protocol, a network protocol, which makes it very difficult to reverse engineer every potential endpoint and to communicate in a standard way. So every IDP has to be handled on a case by case basis, which is simply impossible. And I've come up with something that works for Entra ID, where we can actually do MFA flows at the PAM prompt, but that was a huge undertaking. And so what I'm proposing is that if we had a standard like an OIDC extension that defined how MFA should behave, then we could implement a universal library that works with every OIDC provider. And that would make it so that we just need one standard way to communicate over MFA. And that's definitely possible. If you look at the way that Himmelblau has implemented MFA interaction with Entra ID, it can be done. Also, interesting that you would ask, because I actually just recently added basic OIDC for any OIDC provider. So now Himmelblau works with any OAuth 2 OIDC compliant provider. That's in unstable. It hasn't been released yet, but it can do that now. And that's my goal, is to be able to provide basically we want first class citizen support for MFA on Linux. And right now, all of that I can provide for the OIDC extension in Himmelblau is a device authorization grant with a QR code, and it's hideous. It's just a terrible user experience, and people are complaining about it. But I don't have a protocol defined in order to improve that situation.
I just wanted to mention quickly that the GNOME OS people got an STF grant to do some GNOME OS stuff, but part of what they got the money for is to basically do an alternative to PAM, right? Like with multi-filter, with MFA and everything. So the idea basically is that on GNOME OS and GDM and things like that, you can log in either in like the PAM still works, but you can entirely bypass it to get everything done. So it's systemd close, and I think some components will even land in systemd. Part of it is actually that even the GDM PAM running stuff should actually just move into systemd entirely, so that GDM has no understanding anymore of PAM at all. All I'm suggesting, I guess, is that there's an issue open at on the systemd GitHub, which discusses all this. I think it's already quite close to what you're asking for, but in case you haven't looked at it, please have a look and participate.
Yeah, actually, I'm already involved in those discussions, but thank you for bringing that up.
Okay.
Yeah, that solves one specific use case. So it means that we'll have these browser flows and the I mentioned it briefly during the talk. You must have missed it, but I just glossed over it. But yes, it solves the use case at the GDM prompt, and that's just one small place where this is being used. And the reality is, most of the users that I encounter are using it over SSH, and it doesn't solve that problem. And that's why I was saying we need a new protocol.
But I mean, this is gonna be a hard sell, right? Like, because the SSH people are not particularly fond of Linux and anything new there, particularly.
Well, it
comes
doesn't
from
matter.
systemd, actually.
So that doesn't matter, because if we can define a extension to OIDC that OIDC providers will adhere to for MFA, then we can still operate over standard PAM, and we can provide a MFA flow using the old PAM prompts. We don't need this new systemd GDM stuff or something similar in SSH.
Right. I mean, there are two things, right? Like, there's first of all I mean, your talk was originally called getting rid of PAM, but I mean, if you want to get, like, what you're now suggesting basically is that SSH does OIDC directly with the remote peer and things.
No, I'm suggesting SSH would just use PAM. I'm saying that the network protocol needs an extension in order to be able to do this properly. And yes, my talk changed a little bit, partially because from when I wrote the abstract to when to today, that project started that you just mentioned. And so
Okay.
I was pointing out some of so that problem's being solved. And
Okay. So it's really just about, you want a standardized way how the network side works. Okay, I can.
Yes.
That makes sense.
Yeah, so PAM, the PAM issue is being solved, but only for GDM, and that's so it's still a problem. It's still a problem over SSH or any other connection that is not.
Well, but my understanding is that the GNOME people actually want to provide two-way compatibility anyway. But I don't know. Like, I haven't actually read the newest proposals yet. But talking to them personally, the idea was to have both-way compatibility, meaning that you can still use PAM modules if you really like in an authentication flow, and that you can also expose the authentication flow that we normally would do as a PAM interaction too, right? Like, so in that regard, if this is provided, then you have the SSH compatibility.
Well, we still have PAM. Yes.
Okay, just one minute left. So one more
Okay.
question.
So let me just emphasize really quick. The issue is that PAM over SSH cannot handle MFA for most providers. Go ahead and with your question.
Yeah, so we focused a lot on OIDC and all that stuff. Does Emailblow plan to support offline FIDO2 authentication with security keys, smart card, this sort of stuff?
Yes.
Because today it's okay. Is it already available, or is this like on the roadmap, for example?
That's on the roadmap. Some of it will land in version 3 here in a few months.
Okay, thanks.
Other questions? Nope. I think that you are done. Thank you for your presentation.
Thanks.
Should we start now? Do we start early? No.
Start in 5 minutes.
Okay. Switch slides, you can just use arrow keys or click. Whatever you like.
Yeah.
Okay, so let's get started. Hello, everyone. So my name is Dmitry. I work at Android Calfish team and Android bootloader team. Today, Ram is my colleague and Leaf from the Qualcomm, and we're going to present the Android boot, particularly GBL and DRTM and UKIs, which is potentially the future of the Android boot. Let me start with a quick overview about the Android boot flow. So currently on the site, you can see the typical partition set, which is used by the Android devices nowadays. So mostly during the boot time, we are interested about the boot partitions, and they're used to deliver the final boot artifacts such as kernel, RAM disks, and device trees. Let me give you a quick overview about what the Android boot flow looks like right now. So first of all, we detect the block devices available to find the partitions required to boot the device. Then we check the Android boot mode and active slot we are booting it. So then we load and verify this Android custom partitions format to, for example, to extract some boot artifacts and put them together, handle the rollback protection, and once verification is done, handle the DM verity errors and initialize the secure vault. Once this is done, we need to decompress the kernel, select the device trees and overlays to be applied, and build the final boot config and kernel command line. Also, one of the recently added steps is initialize a protected virtual machine. So basically initialize a hypervisor with protected virtual machine firmware. Prepare board, so flush caches, disable MMU, and something device specific, and do the kernel jump into the GKI, which is ultimately the Linux kernel. Also, another step, which is also very tight with the Android boot, is a fastboot. So fastboot is a protocol to communicate with the device bootloader to get some metadata, flash the partitions, erase, do the factory reset, reboot into the different modes, and something vendor specific as well. It can be used via USB network or vSOC for VMs. So, and how this Android boot flow, majority of the steps are pretty much common, but with some modifications, with some vendor-specific details. So that's why we decided to introduce the GBL, which is Android booting UEFI application provided by Google. So for partners and the ecosystem, is our bet is like integrating the GBL should be better and easier than re-implementing the entire Android boot flow. And for us, the main value is that we can make some changes into the Android boot flow without forcing everyone to implement it into their bootloaders. So right now, to make some changes, we need to work with each partners closely to force them or like ensure they just implemented all the features. Otherwise, we may have like a backwards compatibility issues. So, but if you have like a generic place where we have all that logic, releasing this should be easier than convincing everyone to re-implement it. So a couple of details about the GBL. So first of all, it's a UEFI application written in Rust. It's a we don't have a standard library, obviously, since we are running on the UEFI environment, and we rely on the UEFI allocations. We try to avoid them to make the memory usage of the GBL is more predictable and rely on the vendor side for this, but sometimes we still have to do it. So it's built by Bazel, supporting the major architectures right now on the market, available as a part of the ASP and getting developed as a part of the ASP, so fully open sourced, and all the discussions are also available to read for everyone. It's compiled against the some trusted libraries which are already on the AOSP, such as ATF, libavb, boring SSL, libfdt, libufdt, and other stuff. So we still have to rely on some C stuff for that. So also it's going to be shipped as a EFISP AB partition. So we are looking forward to also update the GBL on the market independently from the rest of the firmware, which is much more challenging usually. And it's already used to boot the Calfish, and we also booting the major vendors' dev boards with the GBL, and currently working hardly to close the gap and make sure it's production ready for the next releases. Why we decided to go with the UEFI? So first of all, it's already adopted on the production by the major vendors. So also it's supported by the firmwares. So first of all, obviously DK2, also U-Boot has a UEFI support that we currently rely on for the Calfish, and we also introduced the basic UEFI support for the little kernel, which used also pretty heavily, and we already booting the GBL on the LK-based devices. Also UEFI protocols, I'm going to cover it on the next slide, but it's really useful way to abstract out the vendor-specific logic for us, because Android boot, we haven't standardized and do anything like this for the last 15 years. So, and just providing the one application that can cover everything, it's not really realistic. So that's why we need to provide a lot of hooks for vendors to do some stuff that GBL cannot know about. Also, UEFI provides a lot of interfaces to communicate with the hardware, like block devices, network, etc. And it's pretty stable and advocated by ARM System Ready for embedded devices. So it seems like a good timing to do so for us as well. Here is a quick overview of which standard UEFI protocols GBL currently relying for doing some basic stuff, such as reading disk, communicating with network for def flavor of the GBL, like getting the RNG, allowing the vendors to re-implement to provide the vendor-specific hash implementation, and some memory allocations. But we also have to introduce a couple of protocols to support, as I mentioned before, to help vendors to still have their specific logic, but using the GBL. So we had to introduce first of all, the boot control protocol. This one is responsible for handling the A/B slotting and boot modes, and allows the vendors to do the custom kernel handoff. Also, boot memory protocol. So it's basically to provide us some predefined memory area where, for example, we're supposed to put the kernel into, or protected virtual machine firmware, because it's usually required by vendors to have these pieces in some predefined offset on the device layout. So OS configuration protocol to select device trees and overlays, and update the boot config with some firmware specific details. AVB protocol to handle some vendor specific stuff on the Android verified boot. AVF stuff to AVF protocol to for us to get the vendor specific dice chain and derive it with the Android standard details, so we can boot the protected virtual machines. And some debug protocol to handle errors, fastboot protocol to provide the vendor-specific details into the fastboot implementation, some custom fastboot variables, or like flashing some virtual partitions that, again, GBL cannot know about. And we also adopting DT fix-up protocol to make sure firmware can modify the final device tree and command line with the details, because right now that's what's heavily happening on the field. So before I let Ram and Leaf tell you about like GRTM and UKI, so here is a slide with a couple of links you can check out after. So it's basically the links to GBL development, our little kernel UEFI implementation, and also EDK2 work in progress patches to land the protocols that required by GBL.
Hey, I'm Rama on the Android team. Two notes about what Dimitri said. Cuttlefish is a Android virtual device, and AVS is Android virtualization framework, just a way to boot VMs on protected VMs on the device. I'll be talking a little bit about our investigations for dynamic root of trust, and specifically for this talk, I guess I'll define DRTM, at least how we're looking at it. It's a way to protect. Well, it's a way to protect against early firmware compromises, so bootkits and whatnot. And the method for doing this is to drop into a how would I say, known good state, which would enabled by the trusted element, and allowed the boot firmware to complete and do a measured boot, and allowed the user space to handle an attestation. Why are we considering DRTM right now? At the moment, given that Android is starting to look into virtualization or protected virtualization in EL2, we need to, how do you say it, handle, let's rephrase. Given AVF, we need to handle running in EL2, and that means we have to launch the hypervisor. And so that allows for a lot of vulnerabilities in this protected state. So we would like to mitigate those and mitigate those vulnerabilities in the existing boot firmware projects. How do I phrase this? So the question now is, how would we adopt the DRTM spec? The existing DRTM spec that ARM has released is ACPI forward, and all the Android devices use device tree. So how would I phrase that? There's a bit of a compromise there for us. DRTM specifically, when we drop into the known boot state, there's this flow called the DLME, which is a single entity that does the measurement step. Given all the various implementations of Android in the ecosystem, having one DLME isn't really feasible for us. And so we need to ideally split this into a number of different options. Something that handles all the device-specific verification, and then something that handles the product-specific verification. GBL also, how would I say it? GBL does its verifications through Android verified boot, and that's not really in the DRTM spec right now. Could we move those to the DRTM environment? And yeah, I mentioned the architecture agnostic part. Cool. So I'll let Leaf do this.
So Ron wanted the target to read this slide. How about we switch Android to boot with ACPI? Yeah. There's a couple of problems with that. First of all, as we've been discussing a bit in the sort of laptop sessions and so on, there's currently a bit of a gap in ACPI with regards to the granularity of power management required for decent battery life. And also some historians claim that switching Android to ACPI might invalidate the Peace of Westphalia and restart the 30-year war. The power management aspect is going to get resolved for the laptop space eventually. The good thing about ACPI is that it is actively in use today by Windows on ARM systems with DRTM. So it's kind of, then we don't need to invent as much ourselves.
Can you go into a bit detail on what part of it is ACPI specific for DRTM? Like what functionality of ACPI do you need? Is it like a special table? Do you need like a special callback? What part? I don't understand what the entanglement is between ACPI and DRTM.
The intent of using ACPI at all, or what's missing from ACPI? I didn't quite catch it.
What's missing from device tree in order to support, like what functionality in ACPI are we using for DRTM that is not available?
What's really missing is a spec for how to do DRTM with device tree.
What part of the current spec? I haven't used DRTM on ARM there.
I think, if I remember correctly, correct me if I'm wrong, The DRTM specification from TCG requires 1 or 2 tables to make it work, if I'm correct, right?
Sorry?
If I'm correct, you need ICPI specification because you want to be aligned with TCG DRTM specification, which requires 2 tables.
Okay. So I think there's the TCG spec, and then
Yeah.
ARM has released their own specification.
Oh, okay.
And that's what I was referencing.
Okay, so
that explains a lot.
And then Microsoft has released an additional specification on top of that. And that together is what we would need to replicate in order to do the same for.
Okay, so this is
because
bigger mess than I expected.
Because ultimately, both ACPI and device tree are an attack vector to the operating system unless you can control that all the information in them is safe. And that's what we need to spec up.
So it means that you have be aligned with TCG specification and ARM specification to be correct, right?
So again, I'm like, maybe this is too deep for right now, but like I'm really curious what type of data there is, and whether this is really just a matter of basically extending, like writing our own device tree edition that effectively tunnels exactly the same tables with the exact same format just straight through to the device tree part. Like, is there any active thing? Is there like a DSDT callback you need to provide? Like active functionality that you need to interpret, or is that really just tables?
It's the spec.
I don't care
We're
about
lacking
the
the
spec. You can validate any spec at any given point in time that you like. Especially if you Google, you can just do whatever, right?
Yeah, but we still don't have it.
So,
yeah.
So
I don't want to get too derailed on this because this was kind of a flippant slide because, hey, why don't we do ACPI and Android? But
so if your problem is really just exposing a few tables, do a prototype, send it to ARM, and tell them to specify it, done.
So it's not so much getting the ecosystem to shift to ACPI in the mobile segment is quite infeasible right now. And so we're looking at, I think your question right now is, why don't we just use ACPI?
No, my question is why, that sounds like you don't have an issue. It sounds like the problem you have is somebody else didn't do the work for you yet.
Yes.
To basically just write up these 3 sentences in a specification that says, if you using device tree, apply the same spec, but take the same data format and just shove it into a property in device tree, right?
Yeah, so if this came up in our internal discussions as well, but I've pointed out that HPI tables are sometimes used where EFI tables should be used, just because the people who write these specs work on operating systems that have both, and they don't really appreciate the difference. But I think if I can paraphrase what Alexander is saying, is that this is not a good reason. I mean, maybe you have a reason to switch to HPI. This is not a good reason to switch to HPI.
The actual paraphrasing is just get it done. Like there's if all it takes is taking a few tables into device tree, just do it. Like that, nothing should keep you from it.
So that is that is what we are planning to do in our reference implementation, which is for next year, but I'll go through how we were trying to boot first and talk through that. This is just this is just how Android boots today, with a lot of SoCs provide a reference hypervisor attached to their device. So start at EL3, which is just ARM's, start at EL3, jump from the XBL, drop to the T. At this point, they'll load a hypervisor. Leif will talk a bit about that. And then jump into UEFI and EL1, GBL will run. At this point, we have to drop back out and let UEFI do the kernel jump because it has to update a number of trees to include the PBM specifications. And then the hypervisor itself will jump into Android. We also have a hypervisor we ship with Android called PKVM. So we'll jump in. This is the boot flow for that. It's relatively simpler. The thing you'll note here is this is built for a system that might boot with system ready. So in this case, the hypervisor can't be bundled up with the silicon, and we have to leave that. That's usually up to the OEM to choose what they're building with. Let's see. So this is the competing slide for that. ACPI can't exist or coexist with device tree. And so the question now becomes, how do we handle measurements of the device tree in the final stage? And the options are all kind of terrible. Let's see.
So yeah, the measurement problem is the real one, I think, with device tree. How you measure device tree with all the fix-ups and everything.
Yeah.
ACPI is part of the firmware, which is provided by the firmware. So you can trust it and it's measured as part of boot chain. But how do you measure device tree? There isn't a solution that is out there. That's the real problem.
In this case, we have a list of relatively finer grained options. I think they have to be paired with the one we will likely. Okay, so not measuring the device tree is not a great option. So diffing the device tree in runtime in this DL context and checking a block list of nodes is it would become a maintenance nightmare over time, because we would have to constantly keep updating that as we added new devices, and that ABI surface just changes annually. So the last one is to kind of reduce all the patched values to a small set, work with every single SoC and get them to drop that down and do a measurement of the patches. And so that's a negotiation between us and all of our partners. And then we'd have to do the same thing for the boot config, which is just an addendum to the RAM disk. Let's see. So I'll talk through the DLME problem for us. I don't remember what it stands for, but it is the bit that runs in the trusted state triggered by the secure, by the, secure element that will do all the measurements before letting user space do the attestation. We're going to ignore AMD and Intel because, at least for Android, we don't have to deal with that at the moment. Let's see, this entity will also have to handle hardware acceleration for all of the measurements. Usually we can just use the ARM instructions, but a number of our partners would rather use custom silicon for that. So we have to handle some customization in this state. So the two options we're thinking of is splitting up the DLME into a bunch of different device-specific pieces and Android-specific pieces, or having everyone fork and do their own implementation per SoC. And so that's not what we're trying to do. So I'll talk through the multi-stage option a bit. Android has a requirement to maintain a device for 7-ish years at the moment. And so LTS is a rather big deal for us. And then even if, let's say, a Qualcomm SoC platform is shipped, it will have multiple different options or multiple different SKUs. And so the device measurements will also have to be changed per device. So if we split the DLME, then we have the ability to update some pieces on the Android platform side while leaving the device side the same. But that creates a whole bunch of other problems. So this is what the multi-stage DLME would look like, and it is a bit of a mess. Okay, so everything starts from the relevant bit is after GBL. Okay, so there's a few new blocks in this. The hypervisor loader is a new entity that would have to be created that Leaf will talk through a bit. That passes over to GBL after loading the hypervisor. GBL runs, initializes everything, hands off to UFI, which triggers DRTM. And then we have our multi-stage DLME, which then passes back to the hypervisor, which then launches Android and all the VMs. Okay, so I think this is the real slide. How would we, let's see. So if we take on device tree, the calling convention for the DLME, the DLME has to do a number of initializations in the final stage before it jumps to the kernel. If we're splitting these, then the calling convention between these DLMEs has to guarantee that the last one does all the initialization and everything else before that carries all the Android specific stuff and device specific stuff outside of the final stage initialization. And then there's a bunch of Android specifics that we have to measure during this DLME state. Dimitri touched on a bunch of those, but that's the short list of them. RNG seeds, we have a public key and rollback indices. Android has a bunch of boot modes and boot reasons. The device or the RAM disk that we select and the device trees that we select. MPE settings, and finally the PVM handover, the dice handover. Okay, and let's see. The last one is what do we measure? At the moment, it's the kernel, RAM disk, device tree, and what do you call it, the PVM firmware. And let's see, there are probably some other custom OEM measurements that have to be taken. So I don't know, if you have a radio on the device that might be loaded by the bootloader, that also has to be checked at this point. And then lastly, attestation. Android provides something called RKP, where the measurement is taken by the bootloader, passed over to user space, and then user space test that with an on-device thing hanging out in the, or on-device TA hanging out in trust zone, which then phones up to a server somewhere. That's not very widely used at the moment, but if we are to take on attestation with secure boot here, or what do you call it, DRTM, then we will have to guarantee its propagation. So yeah, and let's see.
This is no longer about DRTM. I'm now going over to UKIs. So on Qualcomm side, again, there's been frustration in the laptop land because historically Qualcomm shipped hypervisor embedded in the firmware. So by the time you get to the operating system, it's already gone. We've been reworking that to get our Type 1 hypervisor Ganya loading as any normal operating system, system ready compliant, yay, bells and whistles. Type 1 hypervisors are sort of the unloved stepchild in the Linux world. They're tolerated, but no one really makes life easy for them. So I reached out to our friends at Zen and suggested that maybe we should try and standardize a bit about how you load a Type 1 hypervisor so we can actually integrate it with proper tooling and stuff and not have to do so many custom things. There are actually other Type 1 hypervisors as well in real use. So if anyone here is interested in Type 1 hypervisors and want to join in, give me a shout. So when thinking about how to deal with this, kind of stumbled over Red Hat's Nimble thing, which is sort of an adaptation of system deboot workflow using the system stub and building UKIs. And the cool thing about the UKIs is that they're basically just a big peek off image. So if you want to add more images, just add more sections. So hey, why don't we add a hypervisor type in there and some other things. And then when I did that, and I'm going to be horrible now because this is really all the diagrams on one slide and all the text on the other, but the normal current systemd boot workflow just looks like that. You have a systemd stub stuck to the front, you have a Linux section, you have an initrd section, optional you have a DTB section or command line, or even the normal workflow uses quite a few different sections. And we can use the same. If we use Ganya also in systems that don't run Android, and this would be a fine workflow for us with still using the systemd stub mechanism with the hypervisor, with VM images and VM parameters, etc. But then when I was doing this and I was talking to Google anyway around GBL, I went, hey, didn't you mention you considered UKIs at some point? And effectively, if you can just replace systemd stub with GBL, you have a UKI that's now Android compliant.
You know that P section are limited by 8 characters, right? P section are limited to 8 characters. So
No, this is not a serious specification.
Okay.
That's a diagram for
okay.
demonstrating.
Sorry.
Excellent catch, though.
Yeah, discussion over, yeah, well, questions with the minute we have. I was looking to discuss device tree for DRTM, and then UEFI and Android, and the multi-stage DLME, and also GBL as an EFI stub. But if there's anything else.
Question in the chat.
Oh.
Why do you need to measure the energy C?
We do not. Thank you. That was an error.
Okay, this
So GBL is an EFI stub, as it means superseding the one that Linux uses, I guess.
Yeah, that was a thought we had.
So one thing, so I noticed the thing that where the boot flow where you're turning off the caches and turning off the MMU caches, doing all the cache maintenance, etc. I will point out that if you boot via the EFI stub, you will lose all of that as well. You can just go from the EFI stub straight into the kernel.
Yeah.
We never
And just
turn off the MMU or the caches. Well, we swap the MMU from one state to the other, but we do never need any cache maintenance or any costly parts of that. So generally, all the kind of kernel handover pieces, I would try really hard to eliminate those if you can, and just boot in EFI mode. And you don't need the runtime services. You can just turn those off or not provide them to begin with if you don't need those. But just doing the handover in a standard way, I think, is an important design goal for this.
Which means that in your Ganya flow, right, you probably want to have something like Art's tiny UEFI stub that then can load your kernel directly in PE mode, so you don't have to jump through cache disable and enable, which I suppose on your platforms actually means disable caches, accelerating the boot.
I think Dimitri would have the context on that, unless, do you? No. Okay, cool. Well, then never mind. Okay, well, thanks for that. Well, we'll think about that and come back. Yeah, appreciate it.
last question. Thank you.
Thank you for joining us, and see you next year. Bye.
Took my trolling slide way too with Microsoft.
Okay, everyone, let's get started. Welcome everyone to the Gaming on Linux micro conference. For the past couple of years, a lot of more vendors have been using Linux as a platform to deliver gaming products. And this led to very interesting projects to the kernel to have all this new gaming workload. We have a lot of new cool stuff and a lot of things that are still being worked. So yeah, we planned to have this session here to see what's going on and how we can help each other. Yeah, you want to say something?
Yeah, no, just I think gaming is one of the really big untapped. I mean, it's being tapped. Obviously, there's a ton of people working on it, but it's like a huge area where I know everybody is like excited for the growth that we're seeing. So, thanks everyone for coming. I think the topics are pretty interesting, and yeah, looking forward to gaming or talking about it.
Yeah, and we want to say also thanks for our sponsors to make this possible, and for plumbers we have a code of conduct that is being enforced here. And I think we can have the first session with Stefan. Are you around?
Can you hear me?
Yes, we can.
All right.
So, yeah, we'll make your presenter, Stefan, unless you did it already.
I did not know. I think you have to change the presentation to mine.
Oh, yeah, but you need to ask that person now. Resource management.
Yes, that's it.
Okay.
Perfect. All right, ready? Good afternoon, everyone. My name is Stefan Baspali. I work on Meta Horizon OS as part of the Core OS team. And today I'll be talking about resource management on embedded Linux gaming devices. Just a quick agenda of what we'll go over today. We'll talk about why resource management is so important and our goals with doing resource management. We'll talk about what mechanism Linux gives us out of the box to do resource management. We'll talk about how Android implements resource management and ultimately why at Meta we decided to go our own way and implement our own solution. That'll lead into a discussion about expanding upon that with the implementation of Orchestrator, which is the service that we've implemented. We'll talk about our current successes with the service, and then we'll talk about our plans for the future. So first off, why is resource management so important? Well, embedded devices are limited in their capabilities. Hardware is generally limited to fit a form factor. Embedded devices generally have passive cooling or limited active cooling. This is especially true with wearable devices where you're actually making skin contact and your thermal considerations are even more elevated. And many embedded devices are battery powered, right? So any kind of poor resource management in inefficient scheduling, memory IO churn, can increase power consumption and lead to shorter battery life, which is obviously a degradation in user experience. Embedded devices are generally multi-purpose, right? embedded devices like phones, tablets, wearable devices generally have multiple things that the user is actually doing on them. Like one moment you could be playing a game, the next moment you're checking your email. Having one poorly programmed actor can cause system-wide latency and jank. This can lead to things like UI stuttering, audio underruns, a missed deadline for real-time tasks and unrelated components. Devices need to be able to handle multiple workflows of varying importance. Lower priority work can't starve out higher priority tasks. And finally is cost optimization. Shipping hardware is expensive. Software properly utilizing resource management can do more with hardware. That means selecting a lower spec chip, decreasing your BOM costs, and lowering your price entry points for users, which simply means more hardware shipped and more user base for your actual product that you're selling. So we'll talk about what our goals are with resource management. Well, first and foremost, right, is accurate collection of resource usage, right? We need a way to actually collect resource usage and monitor how it's being used. Not only that, we have to attribute it to its usage to a process so that we can actually take enforcement actions against that process. And we also need to be low overhead, right? We can't cause a significant amount of resource usage while attempting to measure the resource. We need a way to control resource usage per process. It can vary at different levels, right? It could be things like throttling, where we limit the rate of a resource usage per process, or it can be things like a hard limit, right? Where we can't go over a certain level of a resource. And this is really aimed at solving the noisy neighbor problem, where we take out targeted enforcement on misbehaving processes. We need to be the sole decision maker when we do resource decisions. We can't have it scattered across multiple processes. We need to have a complete view of the hardware and everything that's going on so that we can have an accurate reflection of the enforcement actions that we're taking out. We need telemetry, right? The ability to log resource usage and aggregate data to detect regressions. Benchmarking in CI is a great tool to have to detect regressions early on. However, production data is the highest quality because it shows how your actual device is performing in the field. And we need to be able to log our actual enforcement actions against processes so that we can inform process owners that their app or game is poorly performing in the field. And finally, we need experimentation, right? Resource decisions are almost always trade-off decisions, right? You're increasing performance in one area and potentially limiting it in the other, right? If you guarantee a certain process a limited, a baseline level of memory, you're taking away that memory from the rest of the system. So you need to be able to have an experimentation framework where you can go out, write a hypothesis, deploy it out in the field and see whether your user metrics are increasing, like in your hypothesis, or you're actually seeing a regression because there's an unknown cause that you didn't initially factor into your calculations. So what does Linux provide us out of the box? Well, there's two really powerful tools to do resource management and monitoring in Linux, and those are cgroup-c2 and BPF, right? cgroup-c2 landed in mainline Linux roughly a decade ago, so it's been there for a while. It introduced the concept of a unified hierarchy where all controllers share the same hierarchy. It provides a nice agnostic way for us to monitor and manage resources. Linux gives us the knobs, but it's completely up to user space how to organize and categorize processes within the hierarchy. Systemd is a really popular user space processes that manages the cgroup hierarchy on distros like Ubuntu and Fedora. But however, on Android, it's a init and system server that do the management. BPF is an extremely powerful tool. It's usually used for observability, CPU profiler, schedule latency, syscalls. This fits perfectly with resource management because we can monitor which processes are using which resources and for how long they're using them. Linux provides us with a whole bunch of standard hook points, but if we need to implement our own and proprietary drivers like GPU drivers, we can do that as well. At the end of the day, BPF is just an ISA. It's up to the programmer to ensure correctness of their program and also to ensure performance. BPF out of the box is very performant, but if you do things like spin locks and just write poorly programmed code in BPF, you'll actually increase your overhead, which is obviously not something that you want to do when you're trying to measure resources. For the next couple of slides, I'll talk about how Android does resource management. We can't talk about embedded gaming, Linux gaming, without mentioning Android. It runs on 3.5 billion devices. I know it's not kind of the hardcore gaming section, but a lot of casual gamers game on Android. And this is really supposed to give you context on how Android handles resource management and ultimately why we decided to go our own way. So this is right now, this is the cgroup v2 diagram of how Android lays out its hierarchy. Right now, Android has a split hierarchy between cgroup v1 and cgroup v2. On cgroup v1, they have CPU set, and I/O controller. On cgroup v2, they've migrated over to freezer and memory on cgroup v2. Cgroup v1 is very dynamic. Processes will leave and join the cgroup hierarchies. That's the complete opposite of cgroup v2, where once a process joins a hierarchy, it will stay there until it's def. And instead, the knobs within that actual hierarchy are fine-tuned. And so you can see here in the hierarchy, kswapd and init are placed at the base level. As I mentioned before, cgroup v2 is very static. So Android by default creates UUID and then PID as part of its hierarchy. Obviously, those can't change, so they'll stay there in that process hierarchy forever. UUID 1000 is a little bit of an Androidism. It's just a system process, so any kind of native system services are spawned in UUID 1000, and then they go into this hierarchy. For apps, you can control memory and freezer, but for native system processes, you can only control memory. Oops, sorry. So how does Android actually control the knobs in these actual cgroup hierarchies? Well, at the heart of Android cgroup control is actually called a library called libprocessgroup, which is a cgroup abstraction layer. It defines cgroups in cgroups.json, which is just a high level of what cgroups are enabled and what version they are. And it defines actions and profiles in what is called task profiles.json. I'm going to go quickly over some terminology. I don't want to get too bogged down in this, but it's kind of a little bit of context here to understand how Android actually does this. So there's attributes, which are almost always a sysf node or a cgroup node that actually will be written to. An action is just a action that is performed on an attribute. It's usually just writing the specific value to an attribute. Profiles are just a collection of actions, and aggregate profiles are just a collection of profiles. And libprocessgroup will expose an API that allows you to apply profiles and aggregate profiles to a process. And we'll go over a quick example right now. So here's a very minimized version of a task profiles.json. You can see here we define a memcg high and memcg max. Both are part of the memory controller. Memcg high only exists in cgroups v2. Memcg max exists both in cgroups v1 in the limit in bytes node, and the file v2 is memory.max, which is the cgroup v2 counterpart. We define one profile, which is just the background profile. So when the process enters the background mode, this will be applied to it. And so you can see here, there's two set attributes. So we're setting memcg high to 128 bytes. So if it goes above that, we'll start to put it under heavy reclaim pressure. If it exceeds the max of 256 megabytes, we'll actually kill it. And then we have this join cgroup action right here, which is very much tied to cgroup v1, where we're actually changing the hierarchy of this process in the dev CPU controller, where we're actually moving it into the background cgroup. This is just a quick, I'm overlaying how the process group actually interacts with the C groups here. So like its name implies, it's a library. So these will actually include it in its DT needed section of the ELF. So it'll be loaded by the linker. And then you can actually call into the API. Once that happens, right, once the processes or the shared library is loaded, it'll read the task profiles.json, construct the schema in memory. And then when you call into the process group and say, hey, apply this task profile to this process, right, it'll figure out what actions do I need to run on that process, and then issue the read and write syscalls to the various C group nodes in that hierarchy to actually accomplish the C group abstraction. All right, well, thanks for sticking with me. That was a lot of context. And now we're actually going to get into why we decided to go our own way at Meta. So C groups, the libprocess group has some benefits, right? It abstracts away C groups and provides a unified API. This is particularly useful to Android because it supports so many different devices across so many different vendors on so many different kernel versions. They need a unified API to actually apply these kind of high-level concepts and go in and figure out the details later. It centralizes configuration, right? So there's one source of truth, and allows for vendor overriding. There's the concept of vendor partitioning in Android I'm not going to go into, but basically allows vendors to include a task profile JSON, which then overrides the one that Android provides by default. But what are some of its limitations, right? It still uses cgroups v1 controllers, especially the CPU CTL controller. As shown in the example, join cgroup action really has no counterpart in cgroups v2. Resource management built in as a shared library, you really can't deconflict, right? There's no way for you to actually have multiple processes managing the same underlying resource, because they both have the process group in their memory space. So they both have write syscalls built into their binary where they can go out and modify the C group hierarchy. And the two, if they're not communicating with each other, you end up with the last one that writ to that C group file wins. And that applies whatever profile they applied. And lastly is experimentation, right? Task profiles.jsons are static and they can't change dynamically. So there's no way to do like an A/B test where, let's say you wanted to modify how much memory you want to put a process under throttle and background. You really can't do that without a lot of code and a lot of kind of hacky workarounds. So there really isn't a good way of doing experimentations with libprocess group. All right, so let's talk about reorganizing the hierarchy. So we're going to take what Android did and we're going to expand upon it, right? So first off, we're going to migrate all of our controllers to C Group v2. That basically makes it so that we're all in the unified hierarchy. We all have kind of the same view of what's going on in the system. We're going to put K threads into its own C group. So you can see right here under the system, there's K threads. So we can actually monitor and potentially control K threads that are running on the system, like kswapd. We're going to disambiguate between system and content. So any kind of native system processes will go into systems. That includes K threads. Any kind of content will go into content. This will allow us to not only monitor like content versus system PSI, but also allow us to make decisions on the content and system level if we wanted to, let's say, put one under throttling or guarantee memory to one, or weight CPU shares differently between the two. This hierarchy will allow us to do that.
Hey, Stefan, can I quickly just jump in to mention something there? So for a lot of our customers who are doing like VR stuff, we have a lot of third-party partners who have SLAs for what they're guaranteed to get on the device. So for example, they get a certain amount of CPU, they get a certain amount of memory. So we really had to split it this way. For something like desktop gaming, it's obviously a little bit different because you can have whatever CPU that you're running on. But in general, it's something I think that's interesting to think about for Linux because, for Unity, Unreal, whatever you're working on, like that's what developers are developing against, and having some ability to like make it clear for people that are developing games on Linux, like how much resources are they going to get, or how can they at least reason about like how the system is partitioned. I think it makes it easier for people to use and develop against. So it's applicable to us because we do have SLAs, but I expect that for like gaming on desktop and other scenarios, it'd be useful too. Just wanted to give some background on that.
All right, so we'll talk about actually implementing the process that will actually control these C group knobs. So we're implementing at Meta, we're implementing a Rust-based policy framework called Orchestrator. We chose Rust because it gives us memory safety without the need for the Android runtime environment. It'll solely manage the C group hierarchy and its value. So it's the only process that's allowed the write to these nodes. And it has a couple core components. It obviously has a C group v2 interface, which is both non-blocking and blocking. Some of the files in C group care whether you open them with blocking or non-blocking mode, so we'll allow for both of those. It has a policy manager and executor. Policy manager can actually run multiple policies simultaneously, and it has logic in the actual executable to deconflict policies so that only one policy can control a resource at a given time. It'll have BPF programs for metric collection. So we'll have BPF programs that are running in the kernel populating ring buffers, and then we'll aggregate and potentially inform policies of kind of aggregate calculations so that they can make their decisions based on that. And then we'll have an RPC interface for applications to provide additional context, right? These are policy specific, but things like if the device is in battery mode, battery saving mode, if it's dawned, not dawned, that kind of deal, all that kind of additional context that we may need to make additional resource decisions. So what are the goals of this, right? The policy framework is really built around making reusable components. So it allows developers building blocks that allows them the quick implementation of policy and reduce code reuse. It's the unification of all C group management into one process. Again, distros like Ubuntu and Fedora already have this. So we're trying to migrate that way where we just have one process that's allowed to actually access the C group hierarchy. And it allows the unification of both resource monitoring and resource management. So you can write telemetry policies that have no actual output as far as actually making resource decisions, but just use kind of the rich building blocks that we have there to do things like data aggregation to send to our backend so that we can actually monitor regressions in real time, so that we don't have to have like a separate process with all this other telemetry that we're going to be calculating anyway and during the resource management phase. I did it for the process group, so I'm going to do it for Orchestrator as well. This is just an overlay. So it's the same thing here where we are doing rewrite and ePOL control to manage like actual PSI to subscribe for any kind of sum or full updates in an ePOL loop. We'll have BPF programs running and doing resource measurements that will send to Orchestrator, again, external service over an RPC interface that provides us additional context. And then we'll have a bunch of policies running where Orchestrator will provide them state, and then policies will run and they'll provide us a list of actions. To talk a little bit about the policy framework, it's based on the reactor reaction model, or the lingua franca model, a little bit of a subset of that. And so it allows us to build real-time systems with very little actual like logic, and it's really kind of rigid, which is a good thing because it allows for policies to be built fairly quickly. So I'll go over some very brief terminology. A policy is just a stateful component whose logic is triggered by various amounts of input triggers. A policy factory is an immutable factory responsible for deciding whether a policy gets created by a new process. So that can be things like the process is executable, its group ID, and other things like if the device is in an experiment or a control group. So it allows for kind of dynamic of loading of policies based on outside factors. A trigger is what decides if a policy should run or not. Examples of triggered are like a periodic timer ticking, PSI exceeding some threshold, an RPC interface coming in and providing us a message. So we have a trigger on that. And then you have actions, right, which are just cause something to happen on the system. It could be writing to a C group node, killing another process due to low memory conditioning, triggering another policy, that kind of deal. And so you can see Orchestrator is not just a program, it's a framework to run policies. And this has like really big benefits. It allows us to actually establish clear responsibilities, right? We don't want to merge. As time goes on and as code matures, right, there's a tendency to kind of merge these two things together. But by having a framework-based system, it allows us to kind of separate responsibilities and ensure that over time we don't have this degradation where we have kind of code merging with each other, and eventually you end up with a bunch of spaghetti code. So you actually have a clearer designation between policies and the actual framework that it's running. Another great thing about that is real-time guarantees. Right now we have deadlines on policies. So if a policy doesn't complete within a certain window, we can actually trip a watchdog timer, and that allows the policy to be deactivated. Resource decisions by that policy are then rolled back and telemetry logged. It allows for deconfliction of policies and allows for experimentation, right? We can hot load policies to be experimented with. So all these are pretty big benefits. Here's a quick overview of the systems. I'm running a little bit low on time. I want to make sure I leave some room for some questions. But basically, the BPF programs are running in the kernel. They write to ring buffers, right? We have code in the user space that then aggregates and triggers if there is a trigger condition. Things like PSI also goes into the trigger queue and external events. A trigger, single-threaded trigger executor runs, right? So all these are placed in a sequential order. That then runs policies. Policies then output to an action queue. And then we have another executor that's actually running the actions. And those can be things like updating to C groups, triggering other policies to run, or writing out to external services. Here's a quick overview of, I know I've been talking a lot about kind of high level stuff, but I want to actually show you what an actual policy looks like in like the declarative world, right? So here's an example policy. We have an internal state, which is a simple counter. We have three triggers, right? PSI high at some sort of high threshold, PSI low, which is at a lower threshold, and a periodic timer. And so you can see here on our actual like execute, which is the dispatch loop of our policy. If PSI high event happens, then we kill some sort of low priority process, right? If PSI low event happens, then we'll increment count by 1. And then if the timer elapses, right, then we reset our counter. And if it's a greater than 10, right, we perform some sort of memory audit and upload it to our backend telemetry servers, right? So we're basically saying like, hey, we didn't really experience like game breaking PSI here, but we experienced a lot of low events, and there's potentially a regression that's happening. So we'll upload that to our telemetry server. Else we don't do anything, right? It's a no op here. So what do we have currently deployed at Meta, right? So we have 2 telemetry policies running in, well, they're actually being rolled out to production very soon. They're running in dog fooding populations right now. And so what we're doing there is we're just using BPF now to actually do telemetry, which I don't think we did a little bit of, but we're doing a lot more of now. And so it's collecting metrics that you usually can't get from Linux by default. So things like graphics PSS, camera PSS, that kind of deal. And we have a heat type telemetry, which is just parsing SMAPS files. One of our big forays right now is actually rolling out the dog fooding, which is the budget service and policy, where we actually have budgets that we ingest, right? We have SLAs, as David was talking about, and we actually take out target enforcement against processes that are running on an actual device, like in dog fooding populations. So if they violate their budget, we have various different enforcement actions. Some of them, they violate their budget a little bit, we'll log telemetry. If they violate a lot, then we'll start actually actively throttling the process's memory usage. And if they go above like a certain threshold, we can actually SIG abort the process, and then it'll log something on our backend to go inform the process owner, like, hey, you're abusing memory. There, you have some sort of memory regression. You have to go out there and fix that. So what does the future look like? One of the policies I'm most excited about is transparent memory offloading. Meta actually did a huge, pretty big talk about that, so I included a source here. But basically, we'll monitor the PSI of a process, and if it goes below a certain threshold, we'll start placing it under reclaim volume until it actually goes above the threshold, and we'll back off, and we'll start to reel that memory back in. And our goal here is to try to actually get the resident memory footprint actually down to the process's work set size. There's a really good article. If you have time, definitely read it. Also, CPU and GPU policies, we really rolled out memory fast because it's the most contentious resource for us. But I just reviewed a bunch of code this week for CPU and GPU policies. So those are really quickly being added as well. And then we've open sourced this project, right? So we have released the source code of Orchestrator. I have a link to the GitHub. So if you're interested in, you can definitely take a look. And we're at Meta committed to keeping it as much as possible in the open source environment. I can't promise all policies in the future will be open source, but we're trying to maintain the framework in the open source world because it is applicable to basically all Linux processes. And yeah, that's it. Sorry, I know I'm kind of low on time.
This is TJ. Can you talk a bit about deconfliction, like what techniques you use to deconflict policies that want to like write to the same C group file or something?
So right now we have basically very, very like not brittle, I want to say, but basically basic logic where two policies can't be enabled at the same time that manage the same underlying resource, right? So if you're writing the memory.high and another policy's memory writing the memory.high, obviously that's a case where two policies can stomp on each other. In the future, we're looking to actually inhibit one policy based on its priority. So for things like working set size, we were actually trying to do a policy where it could, every like, let's say 15 minutes, it would tick and it would actually inhibit any other policy that's controlling memory.high. And so it would allow like a temporary lock on that resource. And then any other policies that were running, trying to attempt to get that resource, they would then say, oh, I failed to acquire the lock on that resource, and then kind of wait for a certain amount of time until they actually try to manage that resource again, and then reset their internal state. But that's something that we have planned for the future that's not currently implemented.
Okay, yeah, thanks, got it.
The other thing to consider as well is that we wanted the semantics of the framework to lend itself to avoiding that. So, for example, like you could have a set of triggers for various low memory conditions, and then if you're able to resolve that low memory condition, you don't need to necessarily do like other actions that might conflict with it. Like, oh, we don't have to do LMKs because we're able to throttle and like get the free memory back. And so by aggregating into one service and having like a clear semantic, pipeline of like triggers, policies, actions, you're able to kind of like have a hermetic, like way to resolve these types of situations in one place.
No problem. Hi, I'm Søren. Can we go to the previous slide? I wanted to. So transparent memory offloading. From the graph, looks like when pressure goes low, you start reclaiming. That counterintuitive. Is my reading incorrect, or this is actually what's happening?
No, this is actually what's happening. So the memory dot, so we're monitoring PSI of a process. And when you write to it, we're really controlling the knob of memory dot high. And there's two, in the kernel, there's two ways. You can open it non-blocking, which you can just write to the memory dot high, and any kind of like paging that happens because of that memory dot high write will actually be attributed to that process. Or you can open it in the blocking mode, which if you open it in the blocking mode, any kind of paging that happens will actually be attributed to you, the process that did the write. So what you're doing is you're monitoring a process's PSI, and if you start right, so there's actually like a control loop. It's asymmetrical. In fact, it's called Senpai. There's a whole article written about it. So I probably won't do it as much justice in depth as I can go. But basically, what you're doing is you're monitoring the PSI, and as long as it stays low, you're going to put it under reclaim volume to try to shrink the actual working set size down to its resonant memory. Then if it starts to experience pressure, right, now you know, oh no, I'm causing degradation to that process. I need to reel back that memory back out, because if I don't, I'll start seeing that process start to falter with memory.
I see. So you're creating feedback loop. Basically, you're putting under pressure and see how far you can press it.
Yeah, it's actually like a control system that they built. Like it's almost like a PI control system where the input is the PSI and the output is the amount of memory that process is allowed to have.
Okay, got it. And this PSI you are monitoring per process, so you're basically using C groups PSI triggers or levels.
Yes.
Okay.
We don't right now it's a tick-based policy, so we don't use ePOL. So we do it every like a second. We calculate the difference, right, and then run our control loop. And then we can potentially increase or decrease the tick rate. There is a potential to us using ePOL where you're actually informed of, hey, your PSI exceeded this threshold that you've written to in our monitoring. But that's something that we have slated to do in the future. It's kind of right now on the back burner because we have a tick-based policy implemented.
Okay, thank you.
Could you explain more about the CPU budget policy and how they are related to the current C group V2 policy about the CPU, such as the CPU.weight and CPU.max?
Yeah, so Android actually does a pretty good job of doing CPU, right? Because CPU, I guess it's CPU.shares in C group V1, CPU.weight in C group V2. Right, and those only really come into effect when the core is under contention, right? CFS will actually, like if there's no one else in the run queue, you can run on the whole process, right? No problem. And it's only when you come under contention that it actually starts to calculate your V runtime and say, oh no, you can't run now because there's other processes that are have more shares than you. So what we're doing right now is we're just monitoring CPU cycles in BPF, and we have like you can only use this many CPU cycles per unit time in our budget, right? So it doesn't matter if no one else is running on the core. You should never exceed this amount of CPU cycles per unit time. The only enforcement action we have right now against those processes is we log telemetry and we do SIG-abors. Eventually, we want to implement some sort of CPU throttling. Again, like I said, this project's been around for like 4 months, so we're still very nascent. But eventually, we want to do something where potentially we could maybe not use CPU shares, but I believe C group has like a CPU quota where we could potentially limit the amount of time slices a process gets in a certain amount of time to allow them to back off that CPU to allow them, because it's not only like contention that we're worried about, we're also worried about battery life, right? So if the device is unplugged, and even if the core isn't under contention, we still don't want a process taking up the whole CPU potentially and saying like, no, we like you know, if the device is, if the screen is off, we don't want Beat Saber taking up all 4 cores, right? So there's a lot more kind of thought that we need to put into how we want to and we're still kind of experimental with budgets. Obviously, we have SLAs, like David said, but for the C group action, it'll probably be something in the realm of quotas and not shares, if that makes sense.
Okay, thank you.
How hard was it to disable all of Android's existing C groups usage?
So we haven't migrated completely. We've migrated everything. Correct me if I'm wrong, David. It's just CPU. We're waiting on CPU because that's basically baked into Activity Manager is basically reliant on CPU CTL controller.
Yeah, so I mean, this is going to be done in like many stages, because we're going to have a stage where we like have task profiles do an IPC out to orchestrator to like update the C group v2 hierarchy. So if you go into the background C group, we set your CPU.wait to something that reflects that. And then eventually we're going to have to change the app model as well, and Activity Manager and Adjuster to reflect like, you know, the model that we need. So it'll be very long and involved, but getting it working for memory and just doing like budgets by measuring stuff in BPF has been pretty easy. Yeah. We're out of time. Yep. Thank you, Stefan.
So our next speaker is Hamesh.
You're good to go, Ramesh, whenever you're ready.
Okay.
I think you might be muted.
Controls. Can you hear me?
Yeah, now we can hear you. You're coming in and out a little bit, but we can hear you now.
Okay. I'm still trying to figure out. Okay. Yeah, I see the controls.
Yeah, you're
Cool.
good.
Okay. So good afternoon or good evening, whatever the time is. The what I'm going to talk about today is how to use some tools like Perfetto to better understand how gaming is done on Linux, and also how the games are utilizing various resources either in the operating system or in the hardware. So that's what we're going to talk about. Now, before I go to these things, by show of hands, I would like to know who is a level 10 in Perfetto in the audience here. And level 10 is the expert, and level 1 is a novice. Any level 10s in the audience? I don't see any hands. How about any level 5s in the audience? Oh, okay. So I do see a few. Cool. So what we are going to do, the reason I'm asking is because we are going to be using quite a bit of Perfetto here, and I'll be talking about various aspects of Perfetto. And what we are going to do is to learn a little bit about different kinds of things that we can know about how games, when they're running on a device, be it a phone or be it a VR device, how they're using the resources. So some of the things that I'm going to show here are how the overall time is being utilized, how the frame, what is the concept of frame, and what is the notion of a frame time, and what happens in a frame is what we want to know. And then whenever a interrupt handler or a soft IRQ gets executed, what impact does it have on various threads that are running inside the system? And then also we want to know about who is waking up who, because there is a pretty complicated sequence of events that happen when a game is running on a system, and there are dependencies among different threads. And the main dependency is the main thread is going to do some rendering, and then it is going to hand off that stuff to the GPU, and the GPU is going to do its part, and then it is going to show some stuff on the screen. But that is not the only thing, and some of these things are highly pipelined in the sense that while the frame is being worked on by the CPU, the next frame is being rendered by the GPU, or some part of the next frame is being rendered by the GPU, so that we can meet the deadlines that are needed to be met. And so understanding all of that is pretty critical to know what is going on inside the system. Then we also want to know what is the overhead from the operating system point of view to orchestrate all the different kinds of threads that are running inside the system. And typically that is the time that we are spending in the OS scheduler. Now, normally in a high performance computing system or in a server, the amount of time that you spend in the OS scheduler is pretty small. But in a game, that amount of time is pretty high. And how do we determine that and how do we compute that is quite a bit of a challenge. And Perfetto has a lot of features which will enable us to do that. And then also I'm going to talk a little bit about the memory leaks and how we can understand and trace the usage of memory inside a game while collecting a trace with Perfetto. And the way I'm going to show that is by showing a simple example which has a memory leak, and then show how we can use Perfetto to detect that leak. Now, all the traces that I used here are collected on a Pixel 8, which is running Angry Birds, that is shown here. Now, I haven't used the VR device, but any Android device or any Linux device will be able to use the exact same techniques and exact same config files that I'm showing here. Now, before we go into the details, I just want to show a few differences between games and apps. So a game is typically highly repetitive. So there is a concept of a frame, and the frame can be either 10 milliseconds, or it can be 9.1 milliseconds, or 13.2 milliseconds, or 16.6 milliseconds, which corresponds to 30 hertz, 72 hertz, or 90 frames per second, or 120 frames per second. Now, typically, the amount of work that happens inside a frame is fairly constant across frames, but sometimes we may not be able to do the work within the given time period, and in that case, we get missed frames or stale frames, and that is something that is undesirable. Now, because we have a fairly limited amount of time or a fixed amount of time in which to complete the work, it is usually a real-time system. Now, it is not hard real-time, it is kind of soft real-time in the sense that even if we miss a deadline, then we have techniques there where we can take an old frame and then try to reuse that so that the user will not feel the difference. Now, the game is highly latency sensitive, and also the memory usage for a game is highly spiky, unlike a normal app, which is fairly uniform. Now, one of the things about games is that the kernel has a pretty big impact on how a game is running. For instance, the kernel scheduler has a very big impact. The interrupts that are happening have a pretty good impact on how the game is able to run and how it is able to meet its deadlines, because interrupts typically are going to preempt the main render thread, and that is probably going to put delays into when it is going to complete its work. Now, affinity to cores and then the migrations that can happen from one core to another core of the threads is also going to have a pretty big impact. Now, the scheduler time quantums typically in a game are measured in milliseconds or in hundreds of microseconds, because most of the threads are running for very short durations of time. But in a normal app, you typically see hundreds of milliseconds or even seconds where the thread is running. So these things make games quite challenging in terms of perf analysis and understanding exactly what is going on. Now, we have a number of tools that are available. So Perfetto is a tracing-based tool, and Simple Perf is a sampling-based tool, and BPF Trace is an instrumentation-based tool. Now, I won't go into the details of the differences of those, but we are only going to talk about Perfetto here today. Now, typically we use all the tools. No tool is by itself sufficient to know or understand what is going on inside the system. So we use a combination of these different tools. But Perfetto is a pretty good tool, and most of these tools will be able to use each other inside those tools, inside the UI that is supplied by these tools. Now, first, we are going to talk about performance. And in order to understand what is going on, we use a very, very minimal Perfetto config. And the Perfetto config that I'm showing here has two main important aspects. One is it is using 3 ftrace events, which are getting the scheduler events. So the sched switch, whenever a thread is switched from one thread to another, or whenever a core is switching from one thread to another thread, there is an event that is generated with a timestamp on it called a sched switch event. And then we also monitor the sched waking event and the sched wake up event. So together, these 3 threads, these 3 events are going to tell us a lot of information about what is happening inside the game. Now, we also monitor the interrupt handlers, the entry and exit events, and also the soft IRQ entry and exit events. So together, these different events are going to tell us everything that we need to know about what is going on inside the hardware or inside the operating system. Now, if you add more events, I mean, literally there are a few thousand events that you can add here, but if you add more events, the overhead is going to be pretty high. And with these events, you can get about 60 to 70% of information that you would want, and then the overhead will be reasonably low. It is typically around 2 to 3%. Now, once you have that config and then collect the information, this is the view that you would get by looking at the trace when you load up the trace into the Perfetto UI. Now, at the top, you see a bunch of swim lanes, and each of those swim lanes correspond to every core. And then you see a very, very dense view of the thread executions on each of those cores. Now, you can zoom in and zoom out into these thread executions so that you can get a lot more detail as to when and what time a thread is executing on a particular core. Now, at the bottom, you see a summary of all the information that you have selected on the timeline view that is shown on the top. So what I'm showing here is a 10-second time interval that I have selected on the timelines associated with all the cores. And what this is showing at the bottom here is the total amount of time that the threads are active on the cores. And the circled value here is the total amount of time that the threads have executed on the core. And that is about 41.48 seconds out of total of 90 seconds that are available, which approximately gives us about 46% utilization. Now, there are 9 cores inside the system in Pixel 8, and I selected a total wall time of 10 seconds. So we have a compute time of total 9 times 10, which is equal to 90 seconds, and out of which only 41.48 seconds is actually being used by various threads executing on the cores. So that kind of gives us a pretty good idea about whether this game that is running is using the compute very heavily or not. Now, anything that is below 50% is kind of okay. Now, anything above 80%, we are in a pretty bad shape because we are going to miss the deadlines and we are going to not be able to meet the frame times. So that is about the overall performance that we can get just with this one view here. Now, this is the frame time. And typically what we can do is to zoom in. And by using the key W, ASWD, you can zoom in and zoom out. And then once you zoom in, you can go into the main process, which is, in this case, Com Rovio Baba, which is the Angry Birds main process. And inside that, there is a main thread, the Unity main thread. And when you look at that Unity main thread, which is shown at the top here, you will see that it is executing at a pretty regular time interval. And that regular time interval happens to be 16.6 milliseconds in this case, which translates into 60 FPS. So by looking at the Unity main thread in the main process, we can determine what is the frame rate that the game is executing at. Now, some games execute at 72, some games run at 90, and some games run at 120. The higher the frame rate, the more work you're going to be doing, and so more battery life and then more power is being consumed. Now, next about the IRQs and soft IRQs. So typically in Perfetto, when we look at the trace, we can assume that the thread is executing whenever it is scheduled onto a core, which is indicated by a dark green line. So in the previous slide here, this dark green essentially means that the thread is executing on that particular core. Now, the issue is that when an IRQ happens or a soft IRQ happens, even though the Perfetto UI thinks that the thread that is running on the core is executing, it has been preempted out, and the IRQ handler is the one that is actually executing. And this is a big problem because the view that you get typically is that the entire core is being occupied by the thread that is executing on it, which happens to be, in this case, 41.48 seconds across all the cores and across all the threads. But those things have been preempted out by the IRQ handlers. And those IRQ handlers are also collected here. And these IRQs are shown here. And those are executing for 4.05 seconds in these handlers. So essentially about 10% of the time in this device, while running Angry Birds, we are spending time executing the IRQ handlers. And that needs to be subtracted from the time of the occupancy for the cores to get the actual utilization of the process Angry Birds on the CPU cores. So this is again a issue with the Perfetto UI. It is nothing to do with the kernel or the way in which the traces are being generated, but the UI does not take this into account. The next one is about the IRQs and the thread timings. So if you look at this specific thread, in this case, this thread is running, but while the thread is running, a interrupt happened, and the interrupt handler actually preempted the thread out, and then it executed, which is shown in the circle here. So if we want to know exactly how much time this thread has executed, it is not the 2.02 milliseconds that is shown here, but it is 2.02 milliseconds minus the amount of time that we have spent in the IRQ handlers that are executing while that thread is running on that core. So this is again a issue with the way in which Perfetto is displaying the information to the user. Now here is another thing that we can get out of Perfetto, which is we can look at the thread wake-ups and determine which thread is waking up who. Now the way in which these threads work in a gaming system is that one thread is going to do some part of the work, and then it is going to hand it off to another thread in a different process so that it can start executing that part of the process. Now, what happens is that when a thread is going to hand off a work to another thread, it is going to use some mechanism that the kernel provides, either through a signal or through a mutex, or through some other mechanism that the API is going to provide it with, and then it is going to signal a thread to go start executing that. Now, the way in which you can determine which thread is waking up which is by clicking on a particular thread, and then you will see a line and a little diamond on that, and the diamond is going to tell you that this thread has woken up that other thread. Now, the way in which this is happening is through that mechanism of ftrace that we have collected, and that is the one which is telling us who has woken up who. Now, again, there is a little gotcha in here in the sense that typically the IRQs are going to wake up some threads, and because the IRQ is going to be executing by preempting the actual thread, we might end up in a situation where the Perfetto UI is going to think that a particular thread is woken up by another thread, but in reality, it might be woken up by the interrupt handler, which was executing during that time period. So again, you can look at the ftrace events that are shown at the bottom here, and this is the message which is going to tell us whether the CPU 3 here is being woken up, or the thread which is executing on CPU 3 is waking up another thread or not. Now, the other question that we might want to answer here is how much time are we spending in the OS scheduler? Now, if you again look at the total time and the view of the timeline, what you might think is that all the empty time here is the time where the thread is not executing, and a dark colored part is where the thread is actually executing on the core. But that's not entirely true, in the sense that there is this CPU idle state event that will happen with the state equal to 0, and that is the point at which the core is actually going to sleep. And between the thread switch and the CPU idle is the time where the thread is where the core is still active and it is executing the OS in the OS scheduler. And in this case, what you can see here is that there are 3 instances where the OS scheduler is executing, and this is the time that we need to compute. The UI is not going to give us that information. So what we need to do is to look at the traces and then compute this information in terms of how much time we are spending in the OS scheduler. Now, typically in a gaming system, what we see is the OS scheduler is taking up about 10 to 15% of the total time in the entire execution. Now, that seems a little high. And the reason for that is because if you look at this time quantum of each of these threads, they're extremely small. So on average, we see about 100 to 500 microseconds per thread that is getting executed. And therefore, the overhead of the OS scheduler to orchestrate these threads, to put them to sleep and then to wake them up whenever they're ready to execute is pretty high. And that is where the OS scheduler comes into play. Now, here is another place where we want to know how much time the cores are actually idle. So what we typically do is we look at the ftrace events and then look at the CPU idle event, and then see between the two states, state equal to 0 and state equal to -1, is where the CPU is actually going to sleep. Now, if it is not in that state, then it is actually running either the OS scheduler or some other thread. And again, we want to keep the cores in sleep as much as possible, because when the cores are sleeping, the power is low and the battery is utilization is low, and so we get a better battery utilization in the device. That is about the Perfetto and the kinds of information we can know about how the OS is using, or how the OS is being used by the game to do its work. Now, if you want some more information, then the Perfetto trace file format is extremely well documented. You can use a trace processor, which is a command line tool, and some SQL queries to get deeper into the UI, and it can provide a lot of information about different metrics that I talked about here in the earlier slides. Now, if the SQL queries are
Ramesh,
yeah,
just to let you know, I think we're at the 5-minute mark or almost there. So okay. Just we may have to cut off at some point, but I just want to let you know, because we may have some questions at the end as well.
Yeah, thank you. So the trace processor is a command line tool which will take the SQL queries, and we can get a lot of deep information about what the trace is telling us that the UI cannot provide. Now, the Python also has a binding for the trace processor, and we can write advanced metric calculations that the UI cannot provide in Python if SQL is too hard. So overall, Perfetto is an extremely powerful tool. It provides deep insights into how the OS and the hardware is being used. Now, the memory is a very critical resource inside the system, and leaks are a big problem. And we can do leaks just like how we can do the performance analysis using Perfetto. And essentially, in summary, the way in which we can do leaks is we take Perfetto snapshots at various frequencies. And at every frequency, we are going to record what is the amount of memory that is alive and what is the amount of memory that has been released. And here is a screenshot of how it will look like. So what I've done is I wrote a simple example where there is a memory leak. And in that example, what we do is to run the Perfetto trace, and then record the snapshots. And what it is showing is at every snapshot, the amount of memory that has been allocated is monotonically increasing. And when that happens, we know that there is obviously a leak, because in a game, we are running at frame boundaries, which are very small time intervals. And if a memory has been allocated and it has never been released in a frame, and continuously it is doing the same thing over and over again in every frame, then obviously we have a leak. Now, this is not very intuitive from the Perfetto UI. So we have to do some SQL queries, and I've shown some SQL queries in the slides here, and that will tell us how these leaks can be detected. So I will not go into the details here, but overall, we can get symbolized call stacks, and then we can precisely point out where exactly a leak is happening by looking at the lifetime of each of the allocations inside these games. So that is what I wanted to share with. So again, in summary, Perfetto is an extremely powerful tool. It's not just limited to performance. You can do quite a bit of memory analysis and then understand how your game is using the memory and the CPU resources inside the system. So thank you. Questions?
Thank you for the nice talk and sharing your experience about using the Perfetto. And I found that the Perfetto is pretty useful, but at the same time that the Perfetto collect a lot of the data. So sometimes the collected data is overwhelming and hard to find out the useful information. So that in my experience, in my use cases, I found that just collecting for like a few seconds is okay, but the collecting like a Perfetto trace like a minute is kind of impossible. Do you have something similar experience with you?
Yeah, so it depends upon what events you're collecting. So the trace file that I showed, or the config file that I showed, is the absolute minimal config file, which gives you most of the information that you would need. And with that configuration, you can collect almost 2 to 3 seconds, 2 to 3 minutes of information. And that would be more than enough to debug any issues that you need. Now, there are more events that you can collect. You can collect syscalls, you can collect all kinds of information. But once you go there, then the trace will become overwhelmingly big, and it will be very hard to decipher.
Thank you.
The other thing is that with memory, we run it for almost 10 to 20 minutes to find the leaks. And memory is pretty easy to collect. And so it is not too big. But for the performance, it is much harder.
Ramesh, for the tool you were showing us where you detect leaks, is that like in any public repo that folks could take a look at?
Yeah, it is all. I mean, all this capabilities are public, and Perfetto snapshots is quite well documented. And again, I put a link in there, which gives all the information about on the Perfetto website as to how to use it and all that.
Okay, I would guess for like the stuff where you're doing SQL queries to figure out where the leaks are for call stacks, that's just interacting with Perfetto, so maybe nothing to open source. Okay, got it. Fair enough.
Is it possible to run Perfetto like the UI in my own server rather than using the one on the web?
Yes, you can do that. And in fact,
Yes,
at Meta, we do have our own version of Perfetto UI.
Okay, thanks.
Just to clarify, most of the stuff that you're running on Perfetto, even if you're using the public common perfetto.dev website, it's actually running locally. So the traces aren't actually being uploaded; they're all being analyzed locally. There is some telemetry, I think, just to see that people are using it, that sort of thing, but it's fairly trivial.
Yeah, that's one big fear that people have. Is my trace getting uploaded to some central server somewhere? No, it is not.
Just I put a little comment in the chat that if you're wanting to use Perfetto for kind of regular Linux distributions, sometimes the documentation is a little Android focused. So I have a little gist about how to get it going for like upstream Linux kernel development.
Cool. Yep. Thank you, Ramesh.
Hello, everyone. So some years ago, I made a new API for Futex. So why not doing a new API for robust lists as well? Right now, for the SteamOS, the gaming API is Windows on x86. So most of the games on the Steam store are compiled for Windows x86. But the SteamOS right now is a Linux distro for both x86 and ARM64. And from there, a lot of interesting challenges are appearing. So we have in the past, we had just the Proton layer to translate from Windows to Linux, but now we also have the fax simulator to translate from x86 to ARM. And because of all this translation, we need to poke the file systems, the Futex, memory management, a lot of stuff. And yeah, we can discuss about all this implication of the new ABI later, if you wanna. And yeah, just to clarify, FAXMU is just-in-time compiler for translating x86, both 64 or 32-bit applications to run on top of ARM64. And of course, whenever it finds x86 syscall instruction, it needs to translate to an ARM64 syscall. And this is not so easy when the syscall is x86 32-bit types, and the project page, they have a list of every syscall that they need to have some work on top. And one of these is the robust list. And just to give an overview, so the set robust list syscall is used to have robust mutexes on user space. So because if the lock owner, the thread that is owning the lock on user space dies, this can starve the waiters, and this is not good. So to avoid that, every time a thread take the lock, they will add the pointer to a linked list that we call the robust list. And then you can call this syscall set robust list to tell the kernel what is the head address of this list. And then whenever a thread dies or get killed, in the kernel side, in the exit path, the kernel wakes all the threads waiting for that Futex. And the kernel also marks that Futex work with Futex owner died. So this user space thread knows that the lock that they are taking now is like they are taking because the original owner of the thread died, so they can do some cleanup or something like that if it's needed. And also the robust list structure, they have a special pending field for whenever the user space is transitioning from taking the lock and putting the lock address in the linked list, they have this special pending field for operation that is still happening. And why do we need a new API? So let's cover the problems of why we cannot use the current API for what we need. So the first thing is that ARM64, they don't have the compat entry point. So that means that a 64-bit application on ARM64, they cannot call the 32-bit syscalls. This is something that x86 can do. This is a special thing. But we want to also run those 32-bit apps on top of ARM64. So if you give the robust list, a 32-bit robust list to a 64-bit kernel, it cannot parse correctly, of course, because of the bad pointer arithmetic. And one question that I got was like, so why don't you use your emulator as a 32-bit app? So the problem is that the new ARM64 cores are removing the 32-bit ISA, and the 32-bit ISA for ARM to have the vectorized operations is not good for emulation, the stuff that happens on x86. So yeah, it's not a good target. So they always run and build the emulator as a 64-bit application. So yeah, we need an interface where we can tell what is the bitness of the list that we want to process. And another problem with the current interface is that we can have one robust list per task. And so the emulator, they want to use robust mutexes itself, but if the app also uses robust mutexes, the fact emulator needs to choose which application will be robust. So we need an interface where we can set more than one robust list per task. There's also a bug report from LPC because to avoid being trapped in an infinite loop, the kernel parses up to 2048 elements in a robust list, but this was never agreed with user space. So this is not part of the fulltext header, and it's not exposed by the kernel in any way. So the user space was never like formally told that. So they have a bug report. So maybe we can just make this part of the API, or maybe we can remove the limit and have some countermeasures to circular lists. I'm not sure. And then we have something that is much more interesting, that we have a race condition on the current set robust list syscall. And yeah, this is kind of tricky to explain, but let me try. So this is coming from another bug report from LPC. So the procedure for unlocking a robust mutex follows like this. So the first thing that you do is that you put that mutex address in the pending slot of the threading robust list mutex list. And then you remove the mutex from the threaded robust list of your lock. So you remove from there. And then you perform the unlock. That is probably doing an atomic write on the fulltext word and wake whatever waiters you have to do. And then you finally clear the pending slot because your operation is now done. However, this is where the race condition is happening. So between step 3 and 4, let's say that another thread takes the mutex, and this thread is like the last user of the mutex. So after taking the mutex, it freed and unlock a new memory or file in the same memory region where that mutex was. And then the other thread that was doing this operation and wrote this address to the pending field, this thread dies before finishing the cleanup. And as I said before, the kernel writes fulltext or not die in the memory when the kernel is exit. So now the kernel just wrote a random number in a random memory or a random file. So that's called a corruption. Thank you. And yeah, this is very hard to replicate. It's very hard to reproduce, but it happened some time, right? It's a bug. It's a very strange bug, but yeah, since we are having a new syscall, we should take care of this as well and need to fix. So I'm not sure how we can fix that. So from what I read, like in the bug report and the Linux kernel mailing list, maybe we need some way to serialize the exit path and every map and unmap that the thread does. Or maybe we can do some API change somehow around the pending field to avoid that. And this is the bug report if you want to read more. And after yesterday's session about SCADX, the SCADX guys, they have all sort of fun schedulers. So what if we could create our own static scheduler that puts things in the order that we want to reliable, always reproduce this issue? So we could have a text case that that have like user space side, and then a custom scheduler just for always creating this race condition. I don't know if that works, but yeah, this is an idea. And yeah, after all this talk, this is how the new API would look like. So you have all these arguments. You have a common argument. So you ask to the kernel, I want a new user index. This is important because both glibc and the application can set robust lists, and to be sure that you are not reusing the same thing that glibc is using, we did this interface. So you ask for the kernel for a new index. The kernel return a new index for you and set the head. If you want to overwrite already existing head, you can use set list. And you can see you have here 32 and 64, of course, so because you want to tell the kernel what is the bitness of the list. And you have like list command list limit to know the number of robust lists per tasks. And we have the equivalent for get as well, get robust lists. And yeah, this is much more straightforward. So you ask for a given PID and index, the kernel will return the head for that. And yeah, this is what I have for you. Any questions?
Yeah, can you go back to the race you're trying to produce there? So if I remember correctly, there's another part to this that if the task you have is OOMed, you then have to wait a certain period. There's a delay put in the Reaper for the robust futex because we were reclaiming that memory. So we had to wait and put the on a timer of some type queue for the exit path to actually wake up your tasks to restore it. So if you want it to reproduce the race, you could actually take out that timer, set it to 0, and we have another way to actually call the code, right?
Sorry, can you?
Process M release is called basically.
Yeah, so process M release will execute the Reaper, Reaper, I think it's called that it calls, and then you will have your race condition, and then you can just create a new futex to reproduce your race.
Good. So this is one way that we can make like the step number 4 happen after the other thread takes and release the lock, something like that.
Yeah.
Cool.
Yeah.
While that reproduces the failure, it still doesn't give any of us a solution to the problem, which is that you need. So the issue was clarified. Both Rich Felker from Muscle and I reviewed this issue as well, which is the primitive is self-synchronizing. So that last lock, basically, as soon as you're done, that step 4, which was part of the protocol, clear the pending, you can't touch anything, right? So the last operation that we get to do from user space has to be a atomic store release. And that needs to be enough for the kernel to then walk away and be able to clear what you have. I just don't know, like I haven't sat down to think about what does a solution look like, but I think we definitely should. If we're writing if you're doing a set robust list, get robust list 2, we should definitely look at what we can do here, because it is the perfect opportunity to transition to something better. But also we're going to have to consider, how do you transition to the new interface from existing C libraries using it, and also process shared, how do you transition as well?
It gets worse. So there was another issue with this in that the timer for killing, you can have a frozen process from C groups, And so then you have like a timer waiting for the exit path that never occurs. So, so the killer is sitting around waiting to kill a frozen task. So that's another thing that kind of came up. So we bypassed that, right? We stopped. Yeah, so it was adding an unnecessary delay to the unfreezing because what it does is it queues up the Reaper to run at a later time, at an arbitrary later time, because we don't really know when the other tasks are going to come back. So yeah, we should definitely fix all of this if we're putting in a new API.
Hey.
So what's the kernel side problem? Does that mean you're just frozen waiting and something never dies, so you never get the reclaim on the robust mutex? It never gets turned consistent by the kernel?
All right, so there's two kind of issues, right? There's one where we have this, well, doesn't work great, right? I mean, to the point where we have PSI and D, and so we select a victim, and then we put the victim on a wait queue for an arbitrarily chosen period to see if the exit path has happened so that we can iterate through the list of the lock holders to tell them that we're going away. So, so it's terrible, right? Like we're waiting around in hopes that something gets fixed later on. And we've done all this work to figure out what to kill, but we're not going to do it. And then the other problem was that well, sure, but think about what's happening, right? We're under memory pressure, we're thrashing, trying to figure out what to do, and then we put a timer on that hopefully the tasks on the list come around or the exit path happens. Like we're under so much pressure, like the system's already in a bad state, and we're hoping that even though we've selected something to kill, it's going to exit. Like, what are the chances of that happening? Probably not awesome, right?
But I'm just trying to separate concerns here. So yes, there is this concern, but from a user space perspective, I have a normal shutdown path. I have a normal operation that I'm doing. So from user space's perspective, I have a normal shutdown path, a normal process operation that I'm trying to do. And robust mutexes are helping me, they're defined by POSIX, to reclaim and make a mutex consistent so I don't get blocked by this, right? And that's also part of our shutdown process. But user space doesn't care until the thing is dead, right? Like the kernel has decided to kill the process is dead, right? And there's a registered mutex here. So from a separation of concerns though, this race condition, yes, we need to fix that. And yes, we need to fix 32-bit versus 64-bit. You need to know the ABI of the structure that you're sharing with the kernel. And in this case, for emulation, you're looking to be capable of registering things that have a different ABI, right?
Right.
So let's hope it's not more than 32 and 64 in the future. But
we have flags.
Yeah.
This one has flags.
Yes, it has flags. Yes. When we talked about the fact that like there are sized things, there are flagged things, and there are versioned things, and yeah, okay, we'll look at that. But so what? I still don't understand why should I care about the other problem? Like, how does it tie into this change in the implementation that Andre is looking at?
Well, so the change that this particular adding a new interface, you mean?
Yeah.
Yeah. So I don't think it really ties into it. It's just the fact that we've added an arbitrary delay in the path for this interface, and that is wrong, right? Like there was no way around it. So now we have this arbitrary time wall clock thing that we're saying, well, or I don't know if it's wall clock, but
yeah. So why do you delay? Just kill it, and then you process the robust list, and you're done, and you walk away, and then user space gets its locks back, and it continues down its merry way, executing whatever it has to do.
So you're saying instead of
you delay?
What? I didn't delay.
Oh,
They-
well
they-
then get rid of the delay.
They put a delay in because they want to go through the exit path so that they can iterate through the list so that user space sees the dead thing, right? So they're waiting. Killer waits in hopes that the exit path executes before it needs to actually reclaim the memory that contains this lock.
I think that delay was added so that the process that looks at that list does not basically stumble on use after. Basically, doesn't have use after free situation.
Yeah.
I don't like. I still don't understand why, because a correctly formed program shouldn't see UAF if it's consistently following the make consistent protocol for robust mutexes. Now, you may have added it just because there are badly behaved programs, and that's fine. Like again, if you have identified something, it is another protocol issue between user space and the kernel to attempt to get a robust mutex consistent. Or maybe you saw this and you tried to work around it in some way.
I didn't.
No, I'm saying someone, the royal we, whatever you want to call it, like maybe this was what surfaced in another light, right? And then
So this is on a private, anonymous private. I think it's in. Is that right?
it could be anywhere.
No. Yeah.
Well-
Okay. So the from my remembering of the problem, will free the memory that the lock contains, or that contains the lock. Okay.
So what happens is goes around and decides who to kill, and then they kill it, and then they put it down. They stick a sick kill, which you cannot block, so it's gone. And then at some point it will be picked up once the last task struck is gone. And then once this is gone, they will go around until the last MM is gone. And once the MM is gone, they will release part of the memory piece by piece. But before we get there, the robust mutex will be processed. I don't know if it's the first task user or level before that, but I don't understand part of the problem. This thing was on my list. I didn't bother so far. However, I promise that I will take a look.
So what the fix was, because we could get to a point where the user space process was trying to reference the memory that the killer had reclaimed. So to avoid that, they put
You can't have done that unless user space dropped the reference on that mapping, though. Like unless user space calls them unmap, you've just taken memory out of another process's address space. Like I don't see how that could happen. Like I mean, user space would have to have called m unmap, but yeah. Either way, we're gonna get to look at this. So how much time do we have left for Liam and for us to like keep shouting at each other? So
2 minutes, right?
do you have more slides?
No.
Or were you hoping for this kind of conversation to happen? Yeah.
Can you?
This protocol is wrong. We have to fix it. It's a PNC issue. The last thing you should do self-synchronizing is an atomic store with release, and that should be it. But we have to rewrite how that gets done. There needs to be a little piece of memory that never goes away that the kernel knows about that we do an atomic store release on, and that'll be the last thing. That's how you get your pending things off. The fact that step 4 exists is a PNC oopsie.
What I'm saying is, like, at a higher level, if you're using these interfaces and one of the applications.
Sorry, do you mind talking to the mic?
Yeah.
You don't know what your behavior is going to be at that point, right?
No, you absolutely do know, because you designed your application to use robust mutexes.
But it's crashing. So if your application is crashing, it's inherently doing something that you didn't plan for.
No, so because you can have two processes with a process shared robust mutex, and you can know that one of your things went away. Yes, yeah.
Yeah, I see. So what I'm saying is, like, are we just minimizing damage?
Oh, sorry, I forgot.
Is this
minimizing the damage of like a distributed application gone wrong versus like, yeah, so you're not guaranteed to have like correct behavior for your entire application in this situation, right?
Like there are things that you really, really want to do, and so then that's what you use this for. You're not wrong. Like if killer killed your thing, it is basically an asynchronous interrupt at some point in your instruction stream, and like as you're not doing anything, but you have some guarantees, and you have promised other people those guarantees, and you're trying to make good on those promises.
Okay, so the thing is
Did you find out why?
yeah, we found out why.
At least put it on the
Okay.
record.
Okay, so the killer kills the process that has the lock list. So then it goes to the exit path and it has nothing to do, and your tasks are screwed. In a politer way of saying that, maybe.
You got the last word. Congratulations. I think that's it. Thank you, Andre.
Coffee break?
Yeah.
So now it's time for a break, but if you want to still talk about robust lists, we are around.
Yeah.
Found the most like contentious topic possible. Documented this race somewhere. That's the first time I heard about it. How? I thought it was the Swiss call for the 3264 thingy. Was this also on the list?
Oh, in my
Yes.
No, because Carlos told me yesterday.
This is completely new.
No, this happened like 10 years ago, but I was not aware of that. And then
this race is known.
Yeah.
Why is no one?
I don't know why no one. I mean,
Because we didn't have a gaming on Linux micro conference, so it never came up.
I mean, he comes up with one thing after the other, right? Like this Robert's list. This was posted 2 times on the list. I was aware of this part. This race thing. You learned about it yesterday.
Yeah, Carlos told me about. I don't know if someone reported.
It's the first time I hear about it. Because food export is perfect. Right?
Really, I agree.
Could you drop me an email and describe the race if possible?
Yes, if you don't mind, I can send you the link for the book.
Is it from 10 years ago?
Yeah, like. Oh boy. I think we can use you have you download here or somewhere else? Okay. You download. Oh.
Yeah, it's there.
That's the right fix, right? Or actually, the right fix is probably iterative lists.
Come on, this is not my department. So this will have been reported downstream to the forms.
File corruption race condition. 2012.
Which Völker? This is Muscle.
Yeah, this guy is
Yeah, he is not fun to work with.
working Florian.
Muscle's not fun to use.
GDC.
You know him?
No, I said Muscle's also not fun to use on its own.
And Carlos is here in the room.
But this is 2015. Torvald is not fun to work with either.
And yeah, here's the. I will send you this link. But here is a precise description of what happened.
This was never reported downstream. So no, come again?
Never reported in the mailing list. You said?
Yes. So I'm not aware. Thomas is not aware. Peter is not aware. Literally everyone here should be
Right.
Ulrich.
Right. Yes.
I don't know Ulrich. No.
Right.
Come.
Sorry.
Ulrich Beckman.
Oh, he's still doing kernel work?
No, but he did GDC work. And for all the side notes, for all the PI thing, he was one of the protocol developers. Like how should PI work from user kernel side and what would we have this response and so on. Anyway. I had vacation plans.
I mean, it's been sitting around for 12, 13 years. I think you can take a little vacation and fix it later.
I was like, I didn't want to look over the Swiss code. It's just a Swiss code, right?
Sorry?
Just a Swiss code. It's nothing else. You have just the Swiss code. Nothing else. Yeah. Everything else we got everything else is good. Do you have any other patches? Oh, okay, so let me delay things until we have settled out. When we have
Like MFD, you don't have kind of like yours, right?
Then second, we have a different element, or we can fix it entirely. Have this
Carrying over
But it seems like maybe if this change the behavior,
yeah, we're not very far along. I think you're farther along than we are.
I have no idea how we fix it. Because I don't even see the problem.
Yeah, but at some point,
right?
we're going to start pushing this file.
if you want,
You'll see conflict.
maybe have an idea.
I have to have this process. And then I can think. Carlos can look at it.
I am interested. I am interested. I think it's a good idea.
I don't know if we need to change semantics. Or if it is okay, does it do user thing?
You got more or less.
That's the thing, right?
So you know that it's changing.
Other ways to do it in that, like, you could actually go and look and see that it's dead.
Bubbles.
Robust mutex are just.
We have 1,000 developers. You have like
I know you have it.
Correct. Yes, yes. And so then the sad part is that. Yeah.
Who wrote the documentation?
It's in the UAPI headers.
Yeah.
There's no benefit.
Oh.
Yeah, it's your project. I don't know. It's just where all the bugs go.
Do you know Elixir? You can find it in Elixir.
Oh, Elixir.
Elixir.
Elixir.wooden.com.
I bet there are like a handful of robust mutex users in the world that care about this.
That's I think it's in UAPI. Search.
Yeah, you're absolutely right about the distributed nature. Everybody touching it in their own ways.
Here, these open thing. Okay.
Yeah.
You have here is the pointer to this.
When the thing is killed.
Here is the open situation thing.
That's the pointer to userland.
So the user is more focusing on the list. They can focus here.
No. The upper thing is
Yes.
What that action is, it's up to you.
Yeah, I mean, it's missing a big concept. Yes, I recommend. We don't have. Yeah, we don't have for process.
Okay, go on.
There's another discussion that it can be more than a page. The journal has that.
Well, it doesn't matter. It doesn't matter. Something like, so we are somehow so that that particular mapping, particular. Because the exit path is still going to happen. So as long as we don't free it, remove it from our map. Exit path will do the right. So, and then we get it out of the critical path.
Absolutely do. That robust is called by. Whenever the process calls set robust list, that indicated.
Yeah, but where will we find out? We could see it, right? It checks. We're not putting it. Yeah, there's no really matter. Yeah, we can solve this. Then get rid of the delay. Yes, that is, it is. Yes, so, like, arbitrary delay, like yellow, for parallelism currencies. It's like when I see delays, it's a PNC issue. Yeah. You're like, I wish I'd known you were involved in this. So funny enough, we're doing functional safety testing. All the go and you execute all like your test cases, everything, blah blah blah. But you're injecting randomized noise into all things. Fails. Time I've gone to look at a test suite, it's like 5. I'm like, what? What were you waiting for that you could not determine the thing was done? And it's often always that like no, there is an API, but the developer didn't know it. They didn't know it. They just put a sleeve. So all of these cases are like education cases. Coach someone. Did you know? Actually, call the wait. Call the wake guy that will eventually notify you. Oh, I didn't know there was. Yeah, it's better than a sleep because the sleep is arbitrary. It is often. I have RCU rates that so what I will do is we'll use this as a case of this is called wrappers, properly documentation orientation. Multiple C library. Ionic has 3, muscle has 3. Yeah, because when I saw that delay, the delay came in right? Yeah, and it was in the context of someone had a frozen path getting put on this wave. The wave will expire, and then it's like it's still frozen, right? So they just skipped the frozen path. And it's like I think that's right, but they were skipping, adding it to the killer skip. Yeah. So I don't. Oh no, it will execute immediately. So then it will wake it up. Yeah, that's what will happen, right? At the jiffies, so it will expire immediately. Yeah. But that's fine. Your application of the kernel. I think he got worn down. And they're like, well, we can't fix it any other way. Yeah. Literally arbitrary for some random. I think when you read the comment, it's like, if they make it too big, then it's no good. And it's like, oh, so we picked this random number. Cycle. No, rolling the ground. That's what I'm saying, yeah. It's jiffies plus Reaper delay. Yeah. Totally
As long as the task that's tasked with doing all this. But yeah, that owned task, there's no guarantee you're going to get it from it, right? You have to do this.
And there's repeated max hard code it to 10. Max it would cause the waiter to block indefinitely run this issue. The integral work is delayed 2 seconds. Now it rarely runs seconds. So the delay is 2
Literally sending a signal to the partner, waiting 2 seconds, and then delete without.
So the Google Reaper is the part that frees the memory. Right, so what they did is they added a 2-second delay between signal, sending the signal to running. And if it's going to this, if it hasn't exited, so that's.
So it tries to kill it 10 times? No, but it's not that you want to know. I have even the process is not dead. Right. And it'll never run again.
Right, and in the exit path is where they're releasing this bomb, right?
In a LPC exit path?
No, in exit MF. Exit MF.
But that's not first.
Yes.
That needs to happen.
I think the right thing to do is, is to leave the list in place. The law list.
Well, you've got a registration.
Right, that's right. You can't, but you can't free it. So the Reaper doesn't read everything, right? It reads. No, it does not. It reads anonymous and private DMA, but other because they may need to be flushed. So no. So if we mark it and say don't, and we let the exit handler do the thing, then we're okay. Well, it will, because, eventually, because the Reaper will mark that task as having no memory, and then kill other things. Eventually.
It's around.
20 seconds.
Or 20 minutes, who knows, right? Whatever. But the problem goes away from my sphere, so I'm okay with it.
Yeah, you get rid of all that.
So you just need to make it so when that.
Yeah.
Yeah, when you register the robust view text in the first place.
So robust, it's on.
That's what you want.
So how big is the DMA?
He said it could be a page or more.
I'm just wondering if some giant piece of anonymous memory that.
No, it's fine. It'll be marked as Zoom skip then, so we're back.
It will never be killed.
But it also was like when I saw that I was like, wait. So now if I'm like, the robust view text, or just one, and then my task can do whatever it wants, and it will never be killed. Perfect. Yeah, but it will never exit. Or no, it'll hang.
I mean, it'll eventually.
It'll hang.
that page will hang around all the other.
Right, so what you would want to do is create plus view text. And be killed.
Yeah, if you take
Right, and then it will be waiting. Everyone, all these tasks will be waiting.
Oh, so if you're holding the robust, oh, if you hold the robust.
If you hold a robust view text.
When you exit. You're fine.
Right, but if you are the one with the list, that's the problem. Yes.
We're gonna fix that.
Yeah.
Seems like a really.
track the list, it's easy enough.
Yeah.
But it's not. Robust view text. But there's already a list of VMA that aren't deleted.
It's by the flags, yeah, I think,
Add a flag.
yeah.
And I'm sure there's plenty of flags. Probably just instruct that.
That's what I was about to
Not a
say.
problem.
How many VMA flags? Yeah.
A little bit again.
Yeah, we'll just.
Yeah, sure. Oh, we can use this other flag.
I know. Yeah, overloading it, I think that might be.
Never.
I think what we'll do is we'll put a task.
Yeah, but the max size is small and per task.
And it's
And it only happens at the
so
reach.
it's not gonna be in view text.
So it's, yeah, it's just things that happen. So where are these?
And you allocate when you allocate the robust.
Right.
Yeah.
Yeah.
Yeah, we're like arbitrarily long.
What is arbitrarily long? How many robust view text?
Yeah, but it's only up to 20.
You need a doubly linked. Bad one.
Maybe a B-star tree or something. I don't know.
Yeah, we'll allocate. List.
Oh, and yeah, you can
Like a straightforward fix.
authorship.
Why did inclusion?
I guess that will show up.
This is not.
Just got beat
That must have been an
Someone
old
got beat
commit you just
down.
saw on AOSP.
So he was doing some Rust.
It will, I
He
think, because
just
then we
noticed
don't need to
that the code
retry.
he had written was
Because we retry time
just like,
allocation.
I don't remember this getting
It's
worked.
literally
He
for
just
this.
noticed.
That's
Yeah,
what I'm
okay.
saying, and when we sell,
So,
like.
yeah, so, okay, so this code, so right now I think it will go out in 26. Next.
Yeah, no worries. Yep, good we should be there.
There was one yeah, okay. Sometimes we just I don't right now, but so actually. Not so much government because yes, I was in the break, which not really my area. I'm just kind of like, this is one of the wonderful things about. I'm just like, go ahead and enjoy. You know, stuff I don't know. I thought you wanted super interesting talk. No. I was figuring this track was the others were pretty niche. Yeah. Yeah. Chris and Lens were in the hotel bar. I went Yes. Yeah. Absolutely. I want to listen. Yeah, so we were looking at. I'm excited for the last I noticed that. How much stuff you can actually tear out of it. It's a little bit of a ship of messages. How much do you tear out? So it's okay. I just kind of asked exactly as well. So you can kind of guess all of that. Will it actually use that, or will it just give you so it like makes sense?
Okay, we can get started. There you go. Thanks, John.
Okay, should we start? Okay, or let's get started. I'm Changmin from Igalia, and I'm going to talk about I wanted to share about my experience of the developing the gaming optimized scheduler, which is the aim rather than that what I already achieved. And before starting, let me introduce a little bit of me. So I'm actually work for the Igalia and the luckily since I joined the Igalia, I have been keep working on the developing the RAVD scheduler, which is one of the SCADX scheduler aiming to become the good scheduler for the gaming. Let me briefly explain about the RAVD scheduler. That stands for the latency critically aware virtual deadline scheduler, which is pretty mouthful. That is basically the motivated by the gaming workload. So basically the aim is that we wanted to run the game workload better on the Steam Deck and run the SteamOS games runs more smoother. That's basically what we wanted to do. So a little bit more technical side, I wanted to minimize the stuttering during the gameplay. So that's the thing. And the primary target is the SteamOS and Steam Deck is basically wanted to run the Windows games on the Linux, so that the software stack that we are dealing with, that the Linux and Wine, Proton, and the Windows games are running on top of the Wine and Proton layer. And as you may already know, the Steam Frame, which is the running the Windows games on the ARM SoC. So it actually added one more layer of the facsimile that the Andre just explained in his previous talk. So that's basically the thing, primary target of the application. And basically, since the RAVD is the SCADX-based scheduler, most of the scheduling policy is written in the BPF code, and there is a shallow user space code which is written in Rust. So that basically means that my experience about the gaming and the scheduling is kind of limited to the Windows games, and my experience about the scheduling is about based on the SCADX based one. So I hope that my experience is worth to be shared and trigger some discussion. So basically, this talk is not about the teaching what I did. So this is more about the throwing the questions to the community and the trigger ignite the discussion that what are the missing things and what should we work together to find out the answer and share some discussion. So basically, after short, a little bit more sharing of the lessons learned while developing RAVD, I mostly focus on the analysis tool. The biggest my pain point during the developing the scheduler, improving the scheduler. So those are including the analysis tool and proper benchmarking, and of course the better support for the Windows games. So actually, when I actually start working on the RAVD, so I thought about what are the important things that the scheduler need to improve. So that of course the one is the performance, the other one is the energy consumption, because So regarding the performance, I found that the game is pretty unique domain because it has a unique, widely accepted universal performance metric, which is frame per second, right? And then it turns out that the FPS is kind of two types of FPS. That is the average FPS and low 1% or the minimum FPS. So that the average FPS is kind of roughly translated into the throughput of the application. And the low 1% FPS is basically the 99 percentile, the latency. So that the average FPS, that's the every gamer wanted to achieve high average FPS, but the gamer will become angry if their low 1% FPS becomes lower and they actually start suffering from the stuttering. So that in some sense that the overall experience, in my view, the average FPS is the high enough. The low 1% FPS matters more in terms of the gaming experience. That's one of the finding. And the other one is that the energy consumption, right? So because that the main gaming devices are battery backed ones, so that for example, the Steam Deck is the battery backed handheld console, and VR glasses are basically also battery backed, so that the energy consumption is also important metric. And also most of those high hardware devices adopt the hybrid processor, having the big cores and medium cores and little cores. So that's also pretty important. And one of the thing is that not all tasks are created equal. So that some are okay to run on a slow but energy efficient core. So if you take, actually I measured some runtime distribution of the task. And some tasks are a little bit running long. Usually the games are very short running tests. They are running like more than 1 millisecond. There are few tasks which actually runs more than 2-3 milliseconds, but mostly are very short. But there are some more tasks which are extremely short, less than 100 microseconds, so that those ones might have a little bit more flexibility in terms of the task placement and the scheduling decision. So that's the one of the thing that I observed. And actually, scheduler can do I believe the scheduler can affect a lot of things in the performance and energy consumption aspect. One of them is because the scheduler, in my view, is essentially make three decisions. One is that the deadline, which task should run first, which basically means that if the latency critical tasks are delayed in the scheduling, then we're gonna see the cascading delay or the UI jank or the stuttering from the user experience point of view. And the other one is how long should task run, so for example, the running the x86 Windows games on ARM, right? Then when the application actually hitting the new basic block then of the code, then the FACSIMIL come into the play and have to translate x86 code to the ARM code, which basically makes that the particular task a little bit more CPU intensive, so that how to properly assign the time slice, right? That's pretty important question. And also at the same time, so we always wanted to give a long time slice for the throughput, because that is very useful to leverage the warmed cache, right? But if the time slice is too long, that actually makes the CPU monopolized by a certain CPU test. So actually that is not at all good for the tail latency and low 1% FPS, right? So that's another one. So the another thing that the scheduler can do in terms of performance and energy consumption is the CPU selection. So that basically scheduler have to constantly make a decision where to place this particular task on a small core, little core, and big cores, right? Where the scheduler have to make a decision, and the quality of decision matters, so that if the scheduler make too much effort, too bad effort quickly, the overhead of the scheduler is going to be low, but we actually have to pay the price of the bad decision. But the scheduler makes too much effort to make a best decision in terms of the throughput, latency, and energy consumption. That ideally good, but actually we end up spending too much CPU time on from the scheduler side. So that's also bad. So one thing that I found is that the understanding workload is very critical. That's I can surely tell. So suppose that if at the very beginning, the question that I asked is that would it be possible to come up with some gaming optimized scheduler? Is that even possible? So actually at the beginning I was not very confident, because that I have no idea about how the game works, right? So that after some profiling and the benchmarking and the workload characterization, I found that will be possible. And the reason that would be possible is that if there is some characteristics that game workload showed, and if scheduler can make a better decision by leveraging those properties, then that we can say that that's a gaming optimized scheduler, right? So that's the thing. And so that the first thing that I actually developed is analysis tool, which is named the Vapormark, because at that time we actually work for the Steam generate the vapor. So and we wanted to make it as a benchmark. So actually I just named it Vapormark. So we actually that shows the various the collection tools and analysis tool, but the most useful one was the collecting the scheduling activities. That time I didn't have enough knowledge on the BPF side, so I just collect all the possible information using the PUF SCAD record, including the call stack, and it generates a lot of the data. So, but anyway, that is not a real-time analysis tool. After collecting the huge amount of data, post-processing it for an hour or two, and show some reports. So I found that that's pretty useful. And this is one of the examples of what Vapormark reports. So actually, I wanted to understand what is the typical runtime duration of each task, and what is the correlation between the runtime and those things. So would it be reasonable, statistically reasonable, to predict the next task's runtime value based on the previous one? And what is the typical interval when a task is scheduled in one time and the next time that is scheduled? So the idle time interval actually goes to all those things. And as this pie chart shows, that I also collect the call stacks when the task is preempted out, when the task is scheduling again, and wanted to understand why task scheduling happens. So actually I found that that's super useful, and that becomes the foundation of the LAVD's policy design. So one of the I wanted to share a little bit of the key finding which was basically used for the LAVD design, but at the very high level, the key finding is in some sense obvious, right? So if you just press the button on your gamepad, right? So that eventually game character will move and the audio will be generated and the display will be updated. So that in order to do this one, right, that easily 20-30 tasks should interact each other, right? So that some of tasks belongs to the same process, but some are not, right? Because it just starting from the device driver and go through the kernel and the game thread pool in the game engine and the game logic, right? And then GPU driver and audio drivers, audio stack schedule, right? So that the many easily 20-30 tasks should correlate each other, and the kind of logically create a task chain. So which is the group of the tasks which are heavily correlate and interact each other. So I found that that's one of the very important thing of the property of the gaming. And I believe that some other domains also have the similar property, but I wanted to say this is one of the major property. And this graph, actually, I believe that I collected this graph in the Cyberpunk 2077 while running the benchmark. I just collect top 50 percentile of the Waco and Wakey relationship. So if you can see this, only handful of tasks are very heavily interact each other. So, and the center in this figure is the wine task, which is wine server. So, which basically means that wine server is delayed, right? So that it actually creates a lot of problem. So that's one of the thing that I found that time, and that actually makes me focus on Waco wakey frequency. And considering the task chain is one of the pretty important factor, right? And Waco frequency becomes that whether a task is the producer or the consumer, or just being both by putting itself in the middle of the task chain. So that's one of my finding, and that becomes translated into the LAVD's scheduling policy. But I found that later, once I finished the prototype of the LAVD, I found that the Vapormark is not useful anymore, unfortunately, because when you are designing the policy, understanding the high-level picture is super important, right? So how they interact and what are the typical ideal runtime value when actually running the task. But once that's done, so we need a different tool. So that actually I tried Professor, And Puppet is actually the better, especially I found that that's very useful, especially if you take a look at the problem and scheduling activity in the very microscopic analysis and to find out the pathological scheduling behaviors, right? So that's useful, but I also found that the Puppet is not perfect. Maybe that's because I'm not the Puppet level 10. So I maybe just Puppet level 3. So that I found that that's also pretty difficult. The one of the reasons that I found that the Puppet, both of the Puppet low level tool and high level tool like a VaporMark and Puppet are not perfect is that the problematic behavior happens rarely. Suppose that the game runs very smooth, right? And I observed the latency spike, FPS drop every 5 minutes, right? Then how should I capture this, right? So I wanted to understand what exactly happens around that latency spike happens around that time. But I found that is not very easy to capture the Puppet trace that time. So of course that what I did is just a brute force, hoping that collecting the Puppet trace every 10 seconds and just find out that this trace is related to this one. So there should be a little bit of better way. So yeah, that's the one thing I believe which we are missing, so that some correlation between the high level view and the very microscopic view that's something missing.
So I believe that Perfetto does actually allow you to look at memory consumption and a few other things. I think it's not perfect at all because it's sampling based, if I recall correctly. Like it'll look at VM stat for global, and it can look at per process stuff too, but it is sampling based. And so I think if I recall correctly, and John or others, you can probably correct me here, but you can adjust the granularity and make it more frequent, which is more overhead. And so we tend to do that, and it's pretty good for finding like outliers if you have a large enough sample space. But I think there are events for doing other resources too.
John, no. Okay, yeah. So actually, I wanted to hear that and how the others are using those analysis tools to optimize the games in general and optimizing the schedulers in general. Yeah.
So one thing is we usually, for gaming, we usually focus on FPS, of course, and tail latency is the most important metric. But there's also the fact about input responsiveness, like some, those professional gamers that plays esports or competitive games, they care about, when they press a button or something needs to reflect on the game engine. Is this LAVD, how does approaches this? And I probably know the answer, but I mean, it's still something that we need to, or more than approaching the problem, we need to monitor this event. Like we need something to measure this, right? Yeah.
So basically, LAVD does not have the hard-coded logic to process the input immediately, but rather than hoping that that one is also captured by the waiter wake up frequency, producer consumer frequency, because that is the event producer, right? So my short answer is that should be ideally handled by the producer consumer concept, but yeah.
And I don't know, like is there a way to see this in Perfetto? Maybe.
Yeah, any experience? So
you can see like chains of who woke whom up. So you would probably see an IRQ, and then you can see which thread is woken up from that, which task is woken up from that, and you can trace the chain of work. It's not always easy to visualize because I think by default it only shows you a single wakey waker. I'll stand over here.
No, the thing is, like, I see everything from an IRQ kernel perspective, but I lose the visibility inside the game engine. And I'm not saying that we need to trace uprobes or something like that, but the thing is, like, I don't know the answer to that because requires inspecting theoretically the game engine, or who knows.
Yeah, you see the task, but that's as far as it goes. Yeah. One thing I'll mention as well, Chungwoo, I don't know if you're going to talk about this, anything else like this later, but for us, well, there are some games that have, I think, fairly CPU intensive tasks too, right? Like I think Civilization 6 is an example of that, where it does like heavy. So we have a lot of those use cases as well, and so we're looking at the possibility of measuring end-to-end work chains. So treating a deadline as like when a task first wakes up from a timer or something like that, and then all the way till the end of a chain where like every task is done being woken, right? And then detecting the end-to-end deadline as a function of that, and like stale and like the frame rate and stuff like that. Have you looked at that for LAVD or?
So LAVD actually didn't consider that because I thought that that would be the one direction and possibility that scheduler can leverage, because in some sense that the games are kind of semi-periodic task, right? So they're starting from here, starting from one frame to the another frame, right? So that the group of the tasks should interact within this time window, but due to the complexity, I didn't consider that part. So, but definitely that's the area that I wanted to explore further.
Okay. Yeah, because I think that there's some other interesting stuff too there, right? Like if you figure out that you miss a frame, you may actually want to prevent the task chain from running until the beginning of the next frame, because if it's going to miss its deadline, then like that it'll be a stale frame again. So if you look at things from the end-to-end perspective of like a whole chain, you can also sort of like get it back on track, if that makes sense, by like delaying it as well, because it is very periodic.
Right. So relate to that, it might be possible to somehow make the CPU scheduler interact with their GPU thing, like a GPU DRM scheduler, right? So whether the CPU scheduler have idea about whether this game actually missed the deadline or not, or the frame per second is too high or too low, then that may be a good hint to make a better scheduling decision in the game domain, at least.
Yeah.
Yeah. Yeah. So I think that we need better tools.
I don't want to monopolize the. No, the other thing is like this is waker-wakey relationship is all about timing, right? Who decide who goes first, but there's also space implications, meaning that if a waker wakes up another task, we have two options. We keep the waker and wakey running on the same CPU where they're running, or we move the wakey on the same CPU as the waker. This is another tricky.
Yeah, that's the pretty tricky thing, right? So in some sense, that actually drives to the second point. In some sense, that what I explained now is just about the scheduling timeline management point of view, right? But there are many other aspects, like such as the cache locality, right? And the memory distance kind of things are also necessary, so that having some tool to provide a little bit more holistic view of the resource consumption of each task, that might be possible using the Perfetto with a nice magical configurations. But those things also needs to be necessary. So one of the interesting point from my scheduler's guy's point of view is that if task is not scheduled, resource is not consumed, right? So I believe that is the important hint, that how the scheduler can be further optimized in terms of the resource utilization, not only for the CPU time utilization. Let's move on to the second topic. Second important topic is that benchmarking is super hard. The reason is that because in order to compare that my improved scheduling policy B is better than the old shitty scheduling policy A, better than A, then there is reliably reproducible benchmark that is absolutely necessary, right? But the game, at least in the game, and many problem domains has some standard benchmark set of the benchmarks, such as spec CPU for the CPU bound job, spec JBB for the Java virtual machine, TPC&H for the database workload, MLPOF, right, for the ML thing. But thankfully, some games has an in-game benchmark, like for example, Cyberpunk, Far Cry, Forza Horizon. Those are racing games and the different kinds of the games. But that's good. And also at the same time, some games allow to replay the recorded game sequences, which is pretty nice. But then if you take a look at this, problem seems to be solved, but actually that's not. The reason is that two things. One is that it is unclear how representative they are because that many users, not me, many users of the 8A really complains, oh, it looks like your scheduler doesn't work perfectly with the Unreal game engine. So it might be better to have a little bit more representative set of the games. So that's another one. The another practically difficult problem is that the games are updated very frequently because, for example, in case of the Steam, right? So that we are kind of control, in some sense, the Steam OS stack, but when I actually try to run the game, it actually starts updating and downloading the 2 gigabyte of the update, right? And then update it. So the comparing the result before the update and after update does not make any sense, right? So that's another practically very difficult part. And I also found that not all, some games, in-game benchmarks also rely on the external resources, especially interact with the game server during the benchmark. So if actually run the exactly same game, same scheduling algorithm, but the results are different between the last night and today's morning, right? So that's because of their game server's performance. It is really difficult to measure the game performance reliably. And the other thing is that even if you are able to reliably run the games, right? So that suppose that you are lose the 5%, 10% frame per second drop compared to your previous scheduling policy, then that's quite difficult, right? How to interpret from the 5%, 10% performance drop to the actual scheduling policy that you changed, right? So the correlating these things is very difficult. So I always wish to have some more micro benchmark, at least for the game domain. So actually there are several scheduling benchmark, but I found that they are mostly focused on stressing the scheduler itself. So stress ng and Puffbench and Hackbench, those are the nice benchmark, but they are mostly focused on makes the scheduler gives a lot of pressure to the scheduler and wanted to measure the scheduling overhead itself. But that is good, but the improving numbers of those benchmarks does not oftentimes does not translate into their actual application performance improvement. So there are some micro benchmark that mimics the behavior of some certain workload. For example, SCH bench. At least they claim SCH bench claims that they reproduce the scheduler characteristics of a production web workload. So actually, I found that that's pretty useful to optimize the web workload. But I think that we need something similar micro benchmark, similar with the SCH bench, so that basically, for example, we have some understanding of how the tasks interact each other, so that they mimic those interactions and writing it as some micro benchmark, so we can actually quickly reproduce the problem.
Were you envisioning this being like synthetic games that use like Unity or Unreal that are representative, or like having like AAA titles or other like actual games be kind of part of the benchmark?
So I do not have a good answer because what are the representative games will be determined by the market shares of the game engines and game titles itself. But probably one thing that we can think about is that we need a kind of benchmark suite. Right. So instead of so I think that we need two things. One is the micro benchmark, which is the simple benchmark that just runs the 1 minute or the 5 minutes. So every scheduler developer just can run for their development site. That's the one type of thing that we need. And another type of thing is that benchmark suite. So probably a collection of the games, which has the in-game benchmark. We believe that those are the representative games in terms of the game engine's market share or the title itself. So that kind of thing seems to be necessary, yeah. Because for example, in case of the cloud workload, Well, one of the examples is the Cloud Suite. That is the benchmark suite. But the under the hood, Cloud Suite is just a collection of the cloud applications like Redis and Memcached and MySQL, something like that. So I think we need something similar. And one thing that which I wanted to emphasize is that the some game benchmark just report average frame per second, which is useful but not ideal. So we should take those things in mind. Am I using too much time? So I think this is the last slide. So the another thing which is important in the gaming is that since the test.
And about what you said about just saying the average FPS, can't you use Mango HUD to get more information about the FPS?
Yeah, so absolutely Mango HUD can be used, and when it is properly configured. Yeah. So because the one thing that we found is that the Mango HUD you can set up the kind of batch when to write the log output. So that if the batch cycle is too large, then actually cause the kind of another stuttering, another latency spike. So that should be carefully configured. I found But if we have some sort of the benchmark suite and set up a recommended Mango HUD configuration, for example, and set up the reliable game titles having the in-kernel benchmark and does not interact with the other out of the computer resources, I think that we have some standard set of the games that will be very helpful to compare the performance. Not only the scheduler performance, the overall performance itself. Yeah, so since I'm actually mostly care about the Windows games, and as I mentioned that the Windows games are heavily communication intensive, and previously they are communicate through the field tag. So basically, the reason is that the Windows games use the Windows synchronization primitives, and that Windows synchronization primitive is emulated in the wine layer, and wine layer using the field tag to emulate the Windows anti-synchronization. So that was obvious. And since many tests are very short running and communication intensive, so the preventing the rock holder preemption or the priority inversion is really important in the avoid the stuttering. So yeah, so how Array handles partially this problem is that we just trace the field tag, whether that is the hooked or not, the cold or not, and emulate, use that information to decide whether a certain task is hold a rock or not, field tag or not. So and use that information as some time slice extension or not. So, but that is not precise because that the field tag user space field tag implementation, user space rock implementation may have a fast pass, so it may not directly go into the kernel space. So that in that case, that is not precise. I think that what the they proposed is for the better field tag design that will help. And also, eventually, I think that the proxy execution seems to be the right direction in this one, right? And the other one is that eventually the wine server is moving towards the anti-sync, which is another kernel module there, which actually designed to support the better support of the anti-synchronization primitive, so that eventually I believe that anti-sync and field tag should be supported by their proxy execution. Yeah, I think that's the long-term solution. Yeah.
Yeah, about that. When I was developing the Field Texture API, I reached through a lot of different communities, and one person said, as you just said, on the fast path, the kernel never knows who is the owner, and there was one person that says that on the FreeBSD kernel, you always tell the kernel who is the owner, because then the kernel can do the scheduler can do better decision to avoid priority inversion. And as you know, but a syscall is very expensive, but mainly because the vulnerability workaround, but in ARM is expensive as well. This is called in ARM 64.
I don't know exactly, but as far as you know, the cost of Cisco is getting cheaper as the hardware evolves. But the cost of the Cisco in the on ARM platform might be much expensive than on the x86 platform. That's just my guess.
Okay.
This is my last slide.
So there is another lock type on Windows called Slim Writer clocks, writer locks. These are basically the same as pthread mutexes. So they have a fast pass that doesn't hit kernel. Most Windows games I know they should use this pass. So if LabD supports Futex, there should be no problem. You can support anti-sync, but I think these are more of a legacy usage. So just a comment.
Is it possible to infer when the task is using this non-kernel locking by inspecting, I don't know, uprobes, let's say?
So luckily with Wine, you can just patch whatever you want, including Slim Writer locks. So as long as the game doesn't go as far as implement its own lock, which I think browsers do, but not games, you have some flexibility here.
Hi. So does LAVD use the same scheduler for all games on, suppose, say, Steam Deck?
Currently the LAVD is just one scheduler. Of
Yep.
course, it provides some tuning knobs as a command line parameter, but basically we just use the one scheduler.
So can it be changed to like something like profile guided scheduling where we have a game run that has been profiled by using, say, Perfetto, and then we can use those metrics to tweak the scheduler. And this doesn't have to be for all games. This should only be representative of the engines, because smaller studios use commercial or open engines, and bigger studios have their own engines, and that will just create a smaller space for us to profile.
I think that idea makes a lot of sense, but that I never explored that direction yet. Yeah, but I think that sounds pretty the feasible and the reasonable direction, because that anyway the most of the task interactions will be heavily affected by the game engine design itself, right?
Yeah, because
So
we
having
can
some core of the scheduler profile per game engine sounds like an interesting idea.
So like if we set a target FPS and we have a profile for every engine out there, then we can tweak the scheduler for those games created using those engines, and this will help with resource usage and battery optimization more, because if once we reach the target FPS, we don't need to do a best effort thing then. This second question I had was for reproducing game runs. If we are in an offline scenario, we are not doing any network calls, what else do you have to look at instead of just inputs and the outputs of random and pseudo-random generators?
I think that is the most important thing. Yeah, so that so the once there is no interaction with the outside the computer, then everything becomes hopefully becomes very deterministic, then I think that will be much easier to collect the reproducible ones. The one thing that might affect is that the thermal throttling and thermal condition, because if the games are running too fast, right, that actually generate a lot of heat and actually makes things slows down everything. So that is the one factor. But yeah, that is hard to control by the software anyway.
Just the last question. Somebody asked a question on the chat. Okay. I do want to mention that I think a lot of what Chung Woo is saying, or like the workload characteristics for Windows, is similar to just like native Linux as well. It is very pipelined.
Yeah,
Like,
I believe so.
yeah. So I think it's pretty convenient that it's actually solving a lot of the same problems for Android and for other platforms. Thank you, Chungwoo. Oh, another one. Okay.
Joel Fernandez had a trick a while back that he was playing with about the pipelining is the part that's kind of making me think about this, but it was basically having kind of this inherited WF sync through the scheduler. And so I don't know if that's something that you're familiar with or if you talked with Joel maybe.
I don't think I have a good knowledge about WF Sync scheduler.
So no. So WF sync is a flag that you can pass to the scheduler to hint that after the wake up, you're going to block soon. So like, yeah, for like wait queues, you can say like, I'm waking this person up and then I'm gonna stay here. So the scheduler can like keep the task in the same core, knowing that it's about to become available and you get better cache locality. I wanted to bring that up too, because that's very useful for us too. We've implemented that locally, and otherwise, you try to keep CPU util up and you migrate onto another core, and then the same one becomes idle like right after that. So.
Yeah. Oh, that's a separate.
Yeah, the flag in the kernel doesn't do that anymore. It did that 10 years ago or 20 years ago or something. The comment says it does it, but it doesn't do it. There's another flag which is, I don't know, same CPU or something like that.
Yeah, that's right. It was renamed. That's true. But I think the sentiment is pretty much the same. Yeah. It's changed. Okay. So. Oh, okay. The semantics have changed. Okay, got it.
Then what was the name of the flag?
Well, it's WF sync.
WF Sync. Okay.
Changed upstream, and I'm in Android we've basically reverted that, so we still have. So it's still used in that case, but.
The point is that having the Futex Wake API maybe support that as like a signal would be potentially useful. All right, cool. Thank you, Chungwoo. We went quite over time, but we have a lot of we had some buffer at the end, so hopefully should be okay. Okay. Yeah. Thank you.
So, hi everyone. It seems I am the only thing between you and the dinner, right? So I'll try to be a bit concise here, not too boring. And we're going to be talking about the collection of data in the Steam Deck, right? And a fun fact is that this is the second iteration of this presentation. The first one it was in the observability MC. I applied to both of them, and it seems the topic is correlated with both of them. So, okay, let's do it kind of twice, right? So I'm Guilherme, and I am not taking much time presenting me, but I live in Brazil. I am from mathematics and moved to computers, right? Started in IBM, doing hardware, software interactions in PowerPC, and then sustaining engineering in Canonical, doing customer kernel level debugging, right? And then I moved to Igalia in 21. I always like to say a bit about Igalia because it's a very unique place. It's a cooperative, right? Focus on free software development, upstream mainly, but the main thing is ethics and quality of life. Is a very nice place to be. And I started working to P-Store more and K-Dump and P-Store, and was kind of presented with the gaming world there in Igalia. So my first work there was on Steam Deck to collect the crash information. So the summary here, we're going to talk a bit about Deck, but I think for this audience, I don't need to present that too much, you probably know. And principles of data collection and submission, and also the crash time data, which is more my expertise, some other system events collected, and finally, how we aggregate and submit that. We have a telemetry system, right? So the Steam Deck, as we all know, is a Linux game console, and the AMD APU, etc. But the main thing is that it's the distro is Arch based, immutable one, with AB model, and we have a complex stack for games, Proton, etc. We all know that. The translations. Igari works in many fronts of that. I work more in the right? I moved different project, but worked more in the part of collecting data, low level, kernel. But there are many people working in user space graphics, FACSMU, Tony working in the few text things, etc. Right? We also work in the Steam frame. So let's talk a bit about the ideals of the data collection in the deck. We have mainly two different classes of data, right? Breakages and the regular information. The people working in bugs, they would like to see when the bug happens and understand what happened, right? The data, collect data in that respect. At the same time, we have developers doing features, like NT-Sync was a feature that comes from this kind of thing. So those would like, or SCADXT, those would like to see metrics. And we also have two realms of the data. We have system information, the infrastructure data, firmware kernel related, versus user land data, games, etc. My more high level applications. The focus here is the infrastructure data, but we can infer game issues based on the message. For example, if a game is causing something, we might correlate, right? And the most common breakages, kernel oopses, crashes, GPU hangs, etc. And informational metrics, split lock detection, despite AMD did not have that on the deck hardware. I'll talk a bit more about this. OMs, Mesa traces, etc. Right? So, and about the visualization of the data, how is it composed? We have a tool to aggregate that we'll talk a bit more later, the SteamOS log submitter called SLS, right? And we have a telemetry thing. So this tool submits that to Valve servers, and we have Sentry running there. So we can see the log statistics of the logs and alarms, etc. It's internal for Valve and some contractors. And it's important to mention that all of that is opt-in. If the user wants it, they enable that. It's very helpful, but it's definitely not mandatory or default. Right, so let's talk about bugs first. Kernel crashes, the main one, likely the most severe thing. And we have many causes for that. Of course, you all know that, no pointers, hardware issues, etc. So SteamOS is configured to crash on oopses and soft hard lockups. We thought that this kind of failure is the most severe one that really impairs the usage of the console, right? Hang tasks, for example, we don't crash on that. It's possible to still use it. So I don't know. It was kind of a judgment. And the tooling used for that is kdumpst and SKL. Kdumpst is an Arch Linux. It starts in the deck, but evolved to an Arch Linux tool. It's present in the AUR. You can use it if you are an Arch user, right? And SKL is just a glue, a layer, thin layer to enable some customizations, etc. on top of kdumpst for the deck. And the technologies behind that, pstore and kdump. So let's talk a bit about the technologies. Probably many of you know that, but let's level things a bit. So the kdump is a KSX-based solution, right? The kernel breaks, so a new kernel jumps in and collects data on the old kernel, the broken kernel, the memory, right? The Vim core. So the main advantage is the huge amount of information. You have full Vim core, full snapshot of memory, but we have plenty of cons. Pre-reserved memory is required on boot time, usually a bit of memory, right? 200 megabytes for the deck case, around that. Embedded is less, but depending on the device. There are some news on this respect. It was but based on comments even in the other presentation and the Middle East, that we can reuse user space memory for that or CMA area, but it's quite recent and still we need something to load the kernel in initrd, right? The size of the Vim core, if we collect everything, is quite big, and privacy concerns because it's all the user data there, right? Also, there are a bunch of risks coming from like server world. PCI might be a big problem. MMO access to all the regions, etc. even OEMs, if we don't properly configure the memory amount, make them file bugs if you use that tool. So there is also an alternative here, another good technology for collecting data, the lightweight way, pstore, which comes from persistent storage. So it saves the kernel log in a persistent storage, like we call it backend. In the case of DEC, is the RAM memory. So we have like a piece of RAM that's, I guess, 60 megabytes free because of some alignments in x86. So we decided to use that. It's very common in embedded devices, and Chromebooks also use that, right? The main pros here, it's very fast and should be transparent process. Should be because, well, in the cons list is a bit, there is some danger there as well. Does not require memory reservation unless you are doing RAM, as we do, but it's in the case of DEC, it is there for free, right? We have multiple front ends. Chrome OS collects also the console. We can collect F-trace data, even user space data as well. And I call it a bonus point here. We don't need KSEC. Some embedded devices, the firmware, for security reasons, they do not allow KSEC. So in pstore, we don't need it. The cons, we have less information collected, basically logs, right? And there is the case of the panic notifiers. We're going to talk a bit about that as a potential improvement here. But the notifiers are functions that run in panic time, and the pstore collection happens after them. So those functions do a bunch of stuff, so we increase the risk of failure, the collection due to them. And also, if we use the RAM as a backend, the firmware might corrupt that, retrain the memory or write stuff there. So it's kind of a risk. We have other backends, of course, like UFI or ACPI. So we can balance this risk. And in the Steam OS, we use it both. The thing is, we had that area in the memory. So why not use pstore, right? But if the user wants to collect more data, let's go with VM Core. So it's a choice. The default is pstore. And if that fails for some reason, or if the user decides tune that, we can go with kdump. In Arch Linux, it's more tricky because we don't control the full hardware like the DEC. So usually a machine can have like a case of the firmware corrupted the RAM, and the user must set by themselves the kind of the backend. So despite the pstore is the default in Arch Linux, usually it fallbacks to kdump. Right, and I put here funny story because the tool supports in CPIO and Dracut. In the beginning, SteamOS was Dracut for some reason, but then it evolved like as an Arch Linux normal thing for in CPIO. Right, and then we have the layer SKL. SKL is what it does is move some logs here and there, and we enabled extra panic information collection like the memory states, timers, test states, CPU backtraces. We use for that panic print and crash KSEC post notifiers to run the kdump after to allow the panic print functions, right? So some improvements that we can do here, some things that are still not round as we would like. So the first of all, the panic notifiers, they're tricky. They are callbacks, as I said, that runs at certain times. Panic notifiers run in the panic time, right? Long time ago, not long time, 2 years ago, we proposed a refactor of them. First, we fixed a bunch of them, like changing mutexes to other kind of locks, because it's not a good idea to have a mutex on the panic time, one CPU, right? Only. But then we decided to split this list in multiple ones according to the complexity and the necessity, let's say like this, of the notifiers. Some are very simple and really useful and important, but some of them are too much. They should be optional, etc. There was a big discussion, even a kernel recipes presentation with some ideas to improve that, but we managed not to merge it still. It's still things to do. RAM oops in the beginning was a bit tricky to reserve the memory. And of course, there are risks of the corruption. Now it's a bit better because Steve improved it with the reserve mem parameter. It still is not deterministic due to Castler, stuff like that. It might change the region, so we can get it corrupted. One idea here is to implement a form of test I'd like to do it to just pass some parameter, so removes test it and see if it's reliable to be used as a backend. And graphical panic is always a problem. It is a long-term issue. It's better now after work of Jocelyn that with the DRM panic handler, but it's very difficult to make a GPU to properly work in the panic time. It's improved for AMD GPU, and Intel is more tricky still. It's not implemented on DEC. When the DEC crashes, it's a dark screen, and then it reboots. One idea was the UEFI notifier. The UEFI maintainer didn't really like that, but it's a very simple idea. I still like it. It's basically a notifier that tells to the UEFI that we crashed, and the UEFI can plot a new funny, like a Tux doing some stuff with a screwdriver. I don't know when the panic happens. It's very simple, and we delegate to the firmware to plot that. It's not the driver like in GPU, but Ard didn't like too much. I managed not to convince him, so here it is. Okay, so back to the bugs we collect in the deck besides a crash, right? The GPU resets, they are very interesting type of failure and very tricky as well, because the driver provides some level of information, but it's difficult to map one-to-one with the user space portion of graphics MESA, right? I'm not an expert here, far from it. Tony worked on that, Siqueira, in Gali as well, a lot of AMD people, and of course in other drivers. But we collect the data there, also MESA things, to help to debug, to try to correlate with potential problems in Proton, like in the XVK, etc. Right, and that's about the bugs, but now about the metrics, what we collect that, like in the normal usage cases, so to help optimize things, etc. Right. Two main interesting things that we collect is the OMs and split locks. There's no event sender for OMs in the kernel, I think, right? And at least when we implemented that. And so we have a trace event for that, mark victim. And for split locks is the same. We don't have it's just in the message, right? The story behind the split locks, it started with Intel, the detection, and then AMD got this capability recently in the Zen 5, I guess. It's a very severe condition, because if you want to atomic access something in different cache lines, you need to buzz lock. So performance drop. And I called here funny story in LWN link. The kernel developers added the misery factor. So if you have if you are to perform by accident a split lock, the kernel introduces some slowness. So the tool super slow as a punishment. And some users of from God of War started to complain about this. We end up having a CCTL for them to disable that, because God of War is quite legacy. God of War 1. It's very difficult to ask the developers to fix the game. So it's a Windows game, so etc. The vehicle we use to collect that is tracing. Basically, we have like a block trace pipe reading, and we collected the OM through the event, and the split lock through just the function split lock detect. And Steven also gave me an idea today in his presentation, was discussing the kind of stuff. I think it's a good idea to also add hung tasks here. Maybe we could also, it's a good event to collect here instead of crashing the machine, right? Because it can continue running. So another type of data we collect, it's very interesting for the developers to understand what their people are connecting like to the deck, right? So the peripherals, the systemd journal, it contains information about that when you plug things, but it's not much detailed. So we have a different tool. It's not my work. It's a very interesting tool, SteamOS System Report. So it collects PCI data, USB, audio, network stuff, displays, because people connect monitors, right, in the deck. And it also collects the systemd journal. On top of that, we also collect core dumps and mini dumps. Mini dumps are a special format for Steam and games. It's kind of a core dump. I don't know really how they work much. And core dumps, we all know, right? And we also collect GPU traces and game scope traces, the composer of the deck. We have a different tooling to collect them in a tracing instance as well. So we collect all of that, and it's time for the aggregation. They are different form of data, like textual files or core dumps. And how do we aggregate it, right? We have the SLS. SLS is work from Wiki, right? From Valve, etc. And it's a Python tool that runs as a systemd thing with hooks. And these hooks, they are for each tool. For example, KDumps has its own hook. It provides a summary of the crash, like the stack trace, the tool that crashed, and of course the data itself. It communicates with the SLS, and in the end, SLS by time it communicates using an API with Valve servers and feed Sentry. So then the developers can see data in a friendly way, like with statistics, smart search, and etc. Right? And that's all I get. If you have suggestions about other data we should do here, we should collect for helping debug games or that kind of thing, it's much appreciated, right? And regarding KDumps, there's a big chunk of things to improve still, like support to Btrfs file systems or other bootloaders. So it's an ongoing thing, right? Thank you.
Just one question here. This is related to your UEFI notifier work. So is that Pat, my suspicion, and I haven't seen the review, was the main pushback that Pat for drawing after notifying the UEFI, that's not like standardized in the UEFI standard, right? Was that the main pushback in the review?
No, it wasn't, because yeah, I understand what you say. Of course, it's not always that we have boot logos, etc. Depends, right? But my idea was basically to have it's very simple, is to have an UEFI variable, right? And we write in that variable, we panic it when the panic happens, and then it's up to the firmware what they want to do with this data. In the Steam Deck, we have the control of the firmware. So it's easy to make use of that and plot. The pushback was related to nobody is going to use it, basically. So who will maintain it? Okay.
Yeah, so I guess my perspective is if you're interested in that path, if you go through the UEFI consortium, and instead of this being something that's just utilized by the SteamOS UEFI firmware, if you say like in the spec, with them, writing to this specific UEFI variable creates this path. If chosen to implement, it doesn't have to be required, but if that's part of the spec there, I think that might open more appetite if it's available there in the core upstream. That might be interesting.
It's a very good idea. So it's a different path of getting that merged, right? First, I can hijack the spec, and then the implementation is the detail, right? It's
right,
a good idea.
Because then Valve is not the only implementer potentially. It's part of spec, and it's more universal that way.
That's a great idea. Thank you.
Yeah, of course.
Yeah. Okay, dinner time. Thank you, folks, for the attention.
I'll leave up the Igalia ad there too. Well, thank you everybody for joining. First year for Gaming on Linux. Yeah, I think this is awesome. I hope we get to do it again in the future.
Yeah, thank you everyone. See you next year, maybe. Yeah.
Yeah. Adios.